So today's session, what all things we are basically going to discuss. So first of all, we are going to discuss about different types of machine learning algorithm, like how many different types of machine learning algorithm are there. Understand the purpose of taking this session is to clear the interviews. Okay, clear the interviews. Once you go for a data science interviews and all, the main purpose is to clear the interviews. I've seen people who knew machine learning algorithms in a proper way. Okay, they were definitely able to clear it because they just explain the algorithms in a better way to the recruiter so that they got hired. First of all is the introduction to machine learning. Here I'm just specifically going to talk about AI versus ML versus DL versus data science. Then the second thing that we are going to talk about over here is the difference between supervised ML and unsupervised ML. The third thing that we are probably going to discuss about is something called as linear regression. So we are going to clearly understand the maths and geometric intuition. The next thing that we are probably going to discuss about is R square and adjusted R square. The fifth topic that we are going to discuss about is ridge and lasso regression. The first topic that we are going to discuss about is AI versus ML versus DL versus data science. So this is the first topic that we are probably going to discuss. If you really want to understand the difference between AI versus ML versus DL versus data science, we will go in this specific format. So just imagine the entire universe. So this entire universe, I will probably call it as an AI. Now, specifically when I say AI, this basically means AI, artificial intelligence. Whatever role you are in, you are as a machine learning developer, you're working as a deep learning developer, vision developer, or a data scientist, or an AI engineer. At the end of the day, you are actually creating AI application. So if I really want to define what is this artificial intelligence, you can just say that it is a process wherein we create some kind of applications in which it will be able to do its task without any human intervention. So that basically means a person need not monitor this AI application. Automatically, it will be able to take decisions. It will be able to perform its task and it will be able to do many things. So this is what an AI application is. Some of the examples that I would definitely like to consider. So the first example that I would like to consider, AI application, AI module. Netflix has an AI module. Suppose if you see a kind of action movie for some time, then the kind of AI work or AI work that is basically implemented over here is something called as recommendation. So here, through this application, what happens is that when you're continuously seeing the action movies, then automatically the AI module that is present inside Netflix will make sure that it gives us recommendation on action movies. Second, if I take an example of comedy movie, if I continuously see comedy movie, then also it will give us the recommendation of the comedy movie. So through this what happens is that it understands your behavior and it is being able to do its task without asking you anything. The second example that I would like to take up in is Amazon.in. Now Amazon.in, again, if you buy an iPhone, then it may recommend you headphones. So this kind of recommendation is also a part of AI module that is integrated with the Amazon.in website. The ads that you see probably when you're opening my channel, through which I get paid a little bit from my from the hard work that I do in YouTube, right? So through that ads, how that is recommended to you, that is also an AI engine that is included in the YouTube channel itself, which really plays. It is a business driven goal. Understand, it is a business driven things that we basically do with the help of AI. One more example that I would like to give you is, if I consider it, self-driving cars. So here you'll be able to see self-driving cars. If you take an example of Tesla, so self-driving cars, what happens? Based on the road, it is able to drive it automatically. Who is doing that? There is an AI application integrated with the car itself, right? So if I consider all these things, these all are AI application. At the end of the day, whatever role you do, you are going to create an AI application. This is the common mistake what people do, like our CEO Sudhanshu Kumar, he has written in his profile that he is an AI engineer. That basically means his goal is to create an AI application. So probably in a product based companies, you'll be seeing this kind of roles called as AI engineer. Now let's go to the next role, which is called as machine learning. So where does machine learning comes into existence? So if I try to create this, machine learning is a subset of AI. And what is the role of machine learning? It provides stats tools to analyze the data, visualize the data, and apart from that, to do predictions and forecasting. So you will be seeing a lot of machine learning algorithms. So internally, those machine learning algorithms, the equation that we are basically using, it is basically using, it is having a kind of stats tool, stat techniques, because whenever we work with data, statistics is definitely very much important. So this exactly is called as machine learning. So it is a subset of AI. This is very much important to understand. ML is a subset of AI. So here you can see that it is a part of this. Now let's go to the next one, which is called as deep learning. Deep learning is again a subset of ML. Now let's consider why deep learning came into existence, because in 1950s, 60s, scientists thought that can we make machine learn like how we human being learn. So for that particular purpose, deep learning came into existence. Here, the plan is to basically mimic human brain. So when I say mimicking human brain, that basically means we are trying to mimic the human brain to implement something, to learn something. So for this, you use something called as multi-layered neural networks. So this is what deep learning is. It is a subset of machine learning. Its main aim is to mimic human brain. So they actually create multi-layered neural network, and this multi-layered neural network will basically help you to train the machines or applications, whatever we are trying to create. And deep learning has really done an amazing work. With the help of deep learning, we are able to solve such a complex use cases that we will be probably discussing as we go ahead. Now, if I come to data science, see, this is the thing, guys. If you want to say yourself as a data scientist, tomorrow you are given a business use case, and situation comes that you probably have to solve that use case with the help of machine learning algorithms or deep learning algorithms. Again, the final goal is to create an AI application, right? You cannot say that I am a data scientist and I'll just work in machine learning, or I'll work in deep learning, or I don't know how to analyze the data. No, you cannot do that. When I was working in Panasonic, I got various different kind of tasks. Sometimes I was told to use Tableau, Power BI to visualize, analyze the data. Sometimes I was given a machine learning project. Sometimes I was given a deep learning project. So as a data scientist, if I consider where does data scientist fall into this, it will be a part of everything. So if I talk about machine learning and deep learning, with respect to any kind of problem statement that we solve, the majority of the business use cases will be falling in two sections. One is supervised machine learning, one is unsupervised machine learning. So most of the problems that you are basically solving, this is with respect to this two problem statement, two different types of machine learning algorithms, that is supervised machine learning and deep learning. If I talk about supervised machine learning, two major problem statements that you are basically solving here also. One is regression problem, and the other one is something called as classification problem. And in the case of unsupervised machine learning problem statement, you are basically solving two different types of problem. One is clustering and one is dimensionality reduction. And there is also one more type which is called as reinforcement learning. Reinforcement learning, I will definitely talk about this, not right now. Right now we are just focusing on all these things. Now understand what happens in supervised machine learning. Let's consider a data set. So here I have a data set which says this is my age and this is my weight. Suppose I have these two specific features. Let's say that I have values like 24, 62, 25, 63, 21, 72, 25, 7, 62, and many more data. Over here, let's say that my task is to basically take this particular data and create a model wherein, so suppose my task is that I need to create a model whenever it takes the new age. First of all, we train this model with this data, and whenever we take age, a new age, it should be able to give us the output of weight. This particular model is also called as hypothesis. Okay, I'll discuss about this today whenever we're discussing about linear regression. Now, what are the important components whenever we have this kind of problem statement? First of all, you need to understand there are two important things. One is independent features and the other one is something called as dependent features. Now let's go ahead and discuss what is independent feature. Independent feature basically means in this particular case, since the input that I'm basically training in, all those features becomes an independent feature. Now in this particular case, my age is independent feature. And whatever I'm actually predicting. So when I say predicting, I know this is my output. Okay, this is the what I have to basically make my model give this as an output. So in this particular case, my dependent feature becomes weight. Why we specifically say dependent feature? Because this is completely dependent on this value. Whenever this is increasing or decreasing, this value is basically getting changed. So that is the reason why we basically say this as independent and dependent feature. Whenever we are solving a problem, right, in the case of supervised machine learning, remember there will be one dependent feature and there can be any number of independent features. Now let's go ahead and let's discuss about regression and classification. What is the difference between them? Now let's go ahead and let's discuss about two things. One is, let's say I want a regression problem statement. Suppose I take the same example as age and weight. So I have values like, as discussed, 24, 72, 23, 71, 24 or 25, 71.5. Okay, so this kind of data I have. See, this is my output variable, which is my dependent feature. Now in this particular dependent feature, now whenever I'm trying to find out the output, and in this particular output you have a continuous variable. When you have a continuous variable, then this becomes a regression problem statement. Now one example I would like to give, suppose this is my data set, right? This is my age, this is my weight. Suppose I am populating this particular data set with the help of scatter plot. Then in order to basically solve this problem, what we'll do, suppose if I take an example of linear regression, I will try to draw a straight line, and this particular line is my equation which is called as y is equal to mx plus c. And with the help of this particular equation, I will try to find out the predicted points. So this will be my predicted point, this will be my predicted point, this, any new points that I see over here will basically be my predicted point with respect to y. So in this way, we basically solve a regression problem statement. So this is very much important to understand. Let's go to the, always understand, in a regression problem statement, your output will be a continuous variable. The second one is basically a classification problem. Now in classification problem, suppose I have a data set, let's say that number of hours study, number of study hours, number of play hours. So this is my independent features, let's say, and number of sleeping hours. And finally I have my output, which will be pass or fail. So in this, I have all this as my independent features and this is my dependent feature. So I will be having some values like this. And here either you will be pass or fail or pass or fail. Now whenever you have in your output fixed number of categories, then that becomes a classification problem. Suppose it just has two outputs, then it becomes a binary classification. If you have more than two different categories, at that time it becomes a multi-class classification. So this is the difference between regression problem statement and the classification problem statement. Now let's go ahead and let's discuss about something called as unsupervised machine learning. Now in unsupervised machine learning, which is my second main topic, over here I'm just going to write unsupervised machine learning. Now what exactly is unsupervised machine learning? Here, whenever I talk about, there are two main problem statements that we solve. One is clustering, one is dimensionality reduction. Let's take one example of a specific data set. Over here, let's say that my data set is something called as salary and age. Now in this scenario, we don't have any output variable, no dependent variable. Then what kind of assumptions were that we can take out from this particular data set? Suppose I have salary and age as my values. So in this particular case, I would like to do something called as clustering. Now why clustering is used? Just understand, let's say I am going to do something called as customer segmentation. Now what does this customer segmentation do? Clustering basically means that based on this data, I will try to find out similar groups of people. Suppose this is my one group, this is my another group, this is my third group. Let's say that I was able to create this many groups or clusters. I'll say cluster 1, 2, 3. Each and every cluster will be specifying some information. This cluster may specify that this person, he was very young, but he was able to get some amazing salary. This person, it may specify that these people are basically having more age and they are getting good salary. These people are like middle class background where with respect to the age, the salary is not that much increasing. So here, what we are doing clustering. We are grouping them together. Main thing is grouping. This word is very much important. Now, why do we use this? Suppose my company launches a product and I want to just target this particular product to rich people. So let's say product 1 is for rich people, product 2 is for middle class people. So if I make this kind of clusters, I will be able to target my ads only to this kind of people. Let's say that this is the rich people, this is the middle class people. I will be able to target this particular ads or this particular product or send this particular things to those specific group of people. By that is basically called as ad marketing, and this uses something called as customer segmentation, a very important example. And based on this customer segmentation, we can later apply any regression or classification kind of problem statement. Now, coming to the second one after clustering, which is called as dimensionality reduction. Now, in dimensionality reduction, what we are focusing on, suppose if we have 1000 features, can we reduce these features to lower dimensions? Let's say that I want to convert this 1000 feature to 100 features, lower dimension. So can we do that? Yes, it is possible with the help of dimensionality reduction algorithm. There are some algorithms like PCA. So I'll also try to cover this as we go ahead. Understand, clustering is not a classification problem. Clustering is a grouping algorithm. There is no output feature, no dependent variable in clustering. Sorry, in unsupervised ML. So yes, I will also try to cover up LDA, will cover up PCA and all as we go ahead. So with respect to supervised and unsupervised. So first thing that we are going to cover is something called as linear regression. The second algorithm that we will try to cover after linear regression is something called as Ridge and Lasso. Third that we are going to cover is something called as logistic regression. The fourth that we are basically going to cover is something called as decision tree. Decision tree includes both classification and regression. Fifth that we are going to cover is something called as Adaboost. Sixth that we are going to cover is something called as random forest. Seventh that we are going to cover is something called as gradient boosting. Eighth that we are going to cover is something called as Xgboost. Ninth that we are going to cover is something called as naive bias. Then when we go to the unsupervised machine learning algorithm, the first algorithm that we are going to do is something called as k-means. K-means algorithm. Then we also have Dbscan. Then we are also going to do hierarchical clustering. There is also something called as k nearest neighbor clustering. Fifth, we'll try to see about PCA, then LDA. So different things we will try to cover up. Yes, SVM I have missed. Here I'm going to include SVM. KNN will also get covered. So I have that in my list. Probably I may miss one or two, but we are going to cover everything. So let's start our first algorithm, linear regression. So let's go ahead and discuss about linear regression. Linear regression problem statement is very simple, guys. So suppose let's say I have two features. One is my X feature and one is my Y feature. Let's say that X is nothing but age and Y is nothing but weight. So based on these two features, I have some data points that has been present over here. So in linear regression, what we try to do is that we try to create a model with the help of this training data set. So this will be my training data set. What I am actually going to do is that I'm going to basically train a model. And this model is nothing but a kind of hypothesis testing, or it is just kind of hypothesis which takes the new age and gives the output of the weights. And then with the help of performance metrics, we try to verify whether this model is performing well or not. Now in short, what we are going to do in linear regression is that we'll try to find out a best fit line which will actually help us to do the prediction. That basically means if I get my new age over here, then what should be my output with respect to Y? Okay, so with respect to this, what should be my output over here? In this particular case, whenever we are drawing a diagram like this, I can basically say that Y is a linear function of X. So this is what we are going to do. Now understand how we are going to create this best fit line. This is very much important. Whenever we say linear regression, it basically means that we are going to create a linear line over there. You may be thinking, sir, why to create linear line? Why not non-linear line? That I'll discuss about it as we go ahead see other algorithms. So to begin with, let's consider this line that you see over here, right? This line equation can be given by multiple equations. Some people write y is equal to mx plus c. Some people write h Some people write y is equal to beta 0 plus beta 1 into x. Some people write h theta of x is equal to theta 0 plus theta 1 into x. Many equations are there for this straight line. This straight line, many equations are there with respect to many different kind of notations. But the first algorithm that I have probably learned of linear regression is from Andrew Ng. Definitely I would like to give him the entire credits, and based on his notation, whatever he has explained, I'll try to explain you over here. So the credits for this algorithm specifically goes to Andrew Ng. So let's consider this one. Over here, in order to create this straight line, I will basically use an equation which is called as h theta. So this is the equation of a straight line. If I know the equation of the straight line, whatever I can write many things. Y is equal to mx plus c, y is equal to beta 0 plus beta 1 multiplied by x. And then I can also write one more, that is h theta of x is equal to theta 0 plus theta 1 into x of I. Here also you can basically say x of I. Here also you can say x of I. Now let's go ahead and let's take this equation for now. Let's take this equation of now. So I'm going to take out this equation and just write one equation through which I have also studied, but I will definitely be adding some points which probably Andrew Ng could not mention in his video. But I'll try my level best. Obviously, he is the best. I cannot even compare myself to him. So theta 0 plus theta 1 into x. Now let's understand what is theta 0, theta 1. As I said that, let's say I have a problem statement over here. Let's say this is my x and this is my y. This is my data points. Now what I'm doing, I'm trying to create a best fit line like this. Now what is this best fit line? What is, when I say this best fit line is basically given by this equation. What does theta 0 basically indicate? Theta 0 over here is something called as intercept. Now what exactly is intercept? Intercept basically means that when your x is 0, then h theta of x is equal to theta 0. So in this particular case, intercept basically indicates that at what point you are meeting the y-axis. So this particular point is basically your intercept. When your x is equal to 0, at that point of time you will be seeing that this line is intersecting the y-axis. Whatever value this will be, that is your intercept. Now the second thing is about your theta 1. What is theta 1? This is nothing but slope or coefficient. Now what does this basically indicate? This indicates that, let's say that this is the unit, 1 unit in the x-axis, and probably with respect to this I can find 1 point over here, 1 point over here. And if I try to draw this over here to here, this is the unit movement in y. So what does it basically say? Slope. With the unit movement, one unit movement towards the x-axis, what is the unit movement in y-axis? That is basically slope or coefficient. Theta 0 and theta 1, two things, and x of I is definitely your data points. Now our main aim is to create a best fit line in such a way that I'll just try to show it to you. What is our main aim? Let's understand what is the aim of a linear regression. So if I take an example of linear regression, I need to find out the best fit line in such a way that the distance between this data points that I have and the predicted points should be very less. Suppose I'm creating a best fit line. Okay, I'm creating a best fit line. So with respect to this data points, initially was this, right? But my predicted point is this point. In this particular case, my predicted point is this point. So, and if I do the summation of all these points, those distance should be minimal. Then only I'll be able to say that this is the best fit line. So I cannot definitely say that this is exactly the best fit line or not. How will I say? When I try to calculate the difference between this point and the predicted point, these are my predicted point, right? If I try to calculate the distance between them, then I will basically have an aim to, it should be minimal. If I do the summation of all the distance, it should be minimal. So for that, what I can do is that, see, you may be also thinking, Krish, why not just do one thing? Okay, suppose if these are my data points, why not just play and create multiple lines and try to compare? What we can do is that we can compare we can create multiple lines, right? Like this. And then whoever is giving the best minimal point, I will go and select that. But how many iterations you will do? How you will come to know that, okay, this line is the best line. So for that specific purpose, we should start at one point and we should lead towards finding the best fit line. Start at one point and then we should go towards finding the best fit line. So for this particular purpose, what we do is that we create a something called as a cost function. I have already shown you what is my hypothesis function. My best fit line equation is basically given as h theta of x is equal to theta 0 plus theta 1 multiplied by x. This is my hypothesis, right? Now coming to the cost function, which is super important. Why it is super important? Because cost function basically, what is cost function over here? I told right this distance, when I do the summation, this distance that when I'm doing the summation, it should be minimal. So if I really want to find out this particular distance, I will be using one more equation. How can I use a distance formula between the predicted and the real point? I will just say that h theta of x minus y. So when I say h theta of x minus y, what does this basically mean? This is my real point and this is my predicted point. Predicted point is basically given by h theta of x. And what I'm going to do, I'm going to basically do the squaring because I may get a negative value. So because of that, I really want to do the squaring part. Now, understand one thing. I need to also do the summation. I is equal to 1 to complete m. Let's say that I'm taking the number of data points over here as m. Because I need to calculate the distance between all the points, right? With respect to the predicted and the with respect to the real points. So, after this, I also need to divide by 1 by 2m. The reason why I am dividing by, first of all, let me show you why we are dividing by 1 by m. 1 by m will give us the average of all the values that we have. The specific reason why we are dividing by 1 by 2 is for the derivation purpose. It helps us to make our equation very much simpler so that later on when I am updating the weights, when I say weights, I am basically updating theta 0 and theta 1. Theta 0 and theta 1, at that point of time, you will be able to see that this particular value, when we probably do the derivative, it will help us to do it. Again, I'm going to repeat it. I'm going to write it down for you. First of all, now in order to find out the best fit line, I need to keep on changing theta 0 and theta 1 unless and until I get the best fit line. Unless and until I don't get the best fit line, I need to keep on updating theta 0 and theta 1. Now, if I need to keep on updating theta 0 and theta 1, I probably require a cost function. Okay, what this cost function will do, I'll just tell you. So, cost function over here, I will specify as j of theta 0 comma theta 1 is equal to, now what is cost function over here? What this distance I told, right? This distance between the h theta of x and y. If I do the summation of all these things, it needs to be minimal. It needs to be less. Because with respect to an x point, this is my y point, right? Similarly, with respect to this x point, this is my y point. So what I'm actually going to do, I'm going to use a cost function. Now in this cost function, my main aim is to basically write h theta of x minus y whole square. This will be with respect to I. Why I am saying I? Because this will be moving from I is equal to 1 to all the points, that is m. M is basically all the points over here. Now, apart from this, what I am actually going to do, I am going to divide by 1 by 2m. I'll tell you why I am specifically dividing by 1 by 2m. First of all, by dividing by m, I will be getting an average output, average cost function, because here I am iterating through m. The reason why I am dividing by 2, because it will help us in derivation. Why? Let's say that I have x square. If I try to find out derivative of x square with respect to x, then what will I get? I will basically get 2x, right? That is what is the formula. What is the derivation of x of n? It is nothing but nx of n minus 1. So that is the reason why I am actually making it 1 by 2, so that when 2 comes over here, this 2 and 2 will get cancelled. So I hope everybody is able to understand. So this is my cost function. Now, understand what is this called as. This entire equation is basically called as squared error function. Yes, mathematical simplicity basically means, because when we are updating theta 0 and theta 1, we basically find out derivation in the cost function. So that is the reason why we are specifically doing it. Squaring off is basically done because so that we don't get any negative values here. Squared error function. Now, let's go towards the what we need to solve. This is my cost function, okay? So I need to minimize this particular value, that is 1 by 2m summation of I is equal to 1 to m, and then this will basically be h theta of x of I minus y of I whole square. We need to minimize this by adjusting parameter theta 0 and theta 1. This entirely is what? This is nothing but j of theta 0 comma theta 1, and we really need to minimize this. So this is our task. Okay, this is our task. Now let's go ahead and let's try to compare with two different things. One is the hypothesis testing and one is with respect to the cost function. Okay, let's take an example. So right now my equation of the hypothesis is nothing but h theta of x is equal to theta 0 plus theta 1 multiplied by x. If theta 0 is 0, then what does this basically indicate? Can I say that it basically the best fit line passes through the origin, and this is nothing but h theta of x is equal to theta 1 multiplied by x? Can I say like this? Obviously I can definitely say like this, right? So my equation will be like this. So for right now, let's consider that your theta 0 is equal to 0. So this is what it is. We have done till here. We have minimized, we have written the equation, everything. Yes. So it is passing through the origin, and this is what is the equation I am actually getting. Now let's take one example and let's try to solve this. If I have h theta of x, so this is my new hypothesis, considering that my intercept is passing through the origin. So with respect to this, let's say that I will create one line over here. Let's say this is my data points like x1, y1. I have 1, 2, 3. I have 1, 2, 3. Now let's consider that if I have data points like what? I have data points like, let's say I have 3 data points, 1 comma 1, 2 comma 2, 3 comma 3. So 1 comma 1 is nothing but this is my data point, 2 comma 2 is nothing but this is my data point, and 3 comma 3 is this is my data point. So these are my data points from the data set that I have. So 2 comma 2 is this point, and 3 comma 3 is basically this point. Let's consider that these are my points that I have. These are my data points. Now, if I consider theta 1 as 1, where do you think the straight line will pass through? Where do you think the straight line will pass? The straight line will definitely pass like this, right? My straight line will definitely pass through all the points. This same point becomes a prediction point also, right? Same point. Let's consider that this is also getting passed through this. It passes through all the points when theta 1 is equal to 1. Theta 1 is nothing but slope. When slope is equal to 1 in this scenario, it passes through all the points. Now go ahead and calculate your j of theta. So what will the formula of j of theta 1 become? Because theta 0 is 0. Okay. We can basically write 1 by 2m summation of I is equal to 1 to 3. How many points are there? 3. Right. And here I have j of h of theta of x1. Sorry. X of theta of xi minus yi whole square. Right. Now let's go ahead and compute. Now in this particular scenario, what will happen? 1 by 2m. Then what is this point minus y of I? See, h theta of x is also 1, y of I is also 1. Both the point are 1. So this will become 1 minus 1 whole square. Plus, because we are doing summation, the next point is also falling in 2 comma 2. So this will become 2 minus 2 whole square plus 3 minus 3 whole square. So in total, this will become 0. So when your j of theta, when theta 1 is 1, so j of theta 1 is how much? It is 0. Right? So what is this j of theta 1? It is the cost function. So let me draw the cost function graph over here. Let's say that this is my theta and this is my. So here I have 0.5, here I have 1, here I have 1.5. So this is my theta. Here I have 2, then I have 2.5. Okay. Then similarly I have 0.5, then I have 1, 1.5, 2, 2.5. This is my j of theta 1. So right now, what is my theta 1? My theta 1 is 1. At this particular point, what did I get? J of theta 1 is nothing but 0. So this will be my first point. This will be my first point. Guys, I have discussed why the value will be 1 by 2m. Basically, to make the calculation simpler, we are dividing by 1 by 2. M is basically used to average the summation that we are actually doing over here. Now let's go ahead and let's take the second scenario. In the second scenario, let's consider my theta 1. Let's say that my theta 1 over here is now 0.5. If my theta 1 is 0.5, then tell me what are the points that I will get. For x is equal to 1, 0.5 multiplied by 1. So it will come as 0.5 over here. Right? Then similarly, when x is equal to 2, 0.5 multiplied by 2 is nothing but 1 over here. And then similarly, when for x is equal to 3, 0.5 multiplied by 3. See, we are multiplying here, right? 0.5 multiplied by 3 is 1.5. So the next point will come over here. Now when I create my best fit line, what will happen? So here is my next best fit line, which I will probably create by green color. Okay, so this is my second one, which is green color. Here definitely slope is decreasing. So if I go ahead and calculate my j of theta, let's see what I'll get. So j of theta 1 is nothing but 1 by 2m. Again same equation, summation of I is equal to 1 to 3 h theta of x of I minus y of I whole square. So what we have for over here? We have nothing but 1 by 2m. Now let's do the summation. What is this point? This point is nothing but the predicted point. And this point is the real point, right? So in this particular scenario, the first point that I will get is nothing but 0.5 minus 1 whole square. How I am getting 0.5 minus 1 whole square? This is 1. This is the real point 1. This is the predicted point 0.5. So here I am getting 0.5 minus 1 whole square. The second point will be 1 minus 2 whole square, right? 2. So 1 minus 2 whole square. And then I will finally get 1.5 minus 3 whole square. So finally, if I do this calculation, how much I am actually getting? 1 by 2 multiplied by 3, which is 6. Here I am getting 0.25, 0.5 square. Here I am getting 1. Here I am getting 1.5 whole square. So my final output will be, which I have already calculated, it is nothing but it will be approximately equal to 0.58. So 0.58, now with theta as, this is nothing but theta 1 as 0.5, right? That is what theta 1 as 0.5. We are able to get 0.58. So theta 1 is 0.5 over here and 0.58 will be coming somewhere here, right? So this is my next point, which will be again in green color. Now let's go ahead and calculate the third condition. Now in third condition, what I am actually going to write, I am going to basically say theta 1 as 0. At that point of time, just go and assume what is 0 multiplied by x, it will obviously be 0. So I will be getting 3 points and my next line will be in this line, that is the x-axis. And this is basically all my points. Now, if I go ahead and calculate this, what is j of theta 1 now? What is j of theta 1? Now, in this particular case, when my theta 1 is equal to 0, 1 by 2m. Now, this part you will be able to see, this is 0 minus 1, 0 minus 2, 0 minus 3. Okay. So, it will become 0 minus 1 whole square, 0 minus 2 whole square and 0 minus 3 whole square. Okay. So this will become 1 by 6 multiplied by 1 plus 4 plus 9, which will not be, it will be nothing but 2.3, which is approximately equal to 2.3. Then what will happen? With respect to theta 1 as 0, we are getting 2.3. So if I draw this, it is nothing but with respect to 0, I am getting 2.3. This is my point. So similarly, when you start constructing with theta 1 is equal to 2, I may get some point over here. So here, when I join these points together, you will be seeing that I will be getting this kind of curve. Okay, and this curve is something called as gradient descent. And this gradient descent will play a very, very important role in making sure that you get the right theta 1 value or right slope value. Now, which is the most suitable point? The most suitable point is to come over here, because this point is basically called as global minima. Because see, out of all these three lines, which is the best fit line? This is the best fit line, right? This is the best fit line. When I had this best fit line, my point that came over here was here itself. This was my point that came over here, right? And I want to basically come to this region because this is my global minima. When I basically am over here, the distance between the predicted and the real point is very, very less, right? So this specific point is basically called as global minima. But still I did not discuss, Krish, you have assumed theta 1 as 1, theta 1 as 0.5, theta 1 as 0. Here also you are assuming many things, right? And then you are probably calculating and you are creating this gradient descent. But the thing should be that probably you come to one point over here and then you reach towards this. So for that specific reason, how do you do that? How do I first of all come to a point and then move towards this global minima? So for that specific case, we will be using one convergence algorithm, because if I come to one specific point, after that I just need to keep on updating theta 1 instead of using different theta 1 value. So for this, we use something called as convergence algorithm. So here the convergence algorithm basically says repeat until convergence. That basically means I am in a while loop, let's say. And here I am basically going to update my theta value, which will be given by this notation, which is continuous updation, where I'll say theta j minus, I'll talk about this alpha, don't worry. And then it will be derivative of theta j with respect to this j of theta 0 and theta 1. So this should happen. That basically means after we reach to a specific point of theta, after performing this particular operation, we should be able to come to the global minima. And this specific thing that you are able to see is called as derivative. This is called as derivative. Derivative basically means I am trying to find out the slope. Derivative, which I can also say it as slope. This equation will definitely work, guys. Trust me, this will definitely work. Why it will work? I'll just draw it, show it to you. Let's say that this is my cost function. Let's say that I've got this gradient descent. And let's say that my first point is somewhere here. But I have to reach somewhere here, right? Now when I reach this is my theta 1 and this is my j of theta 1. Suppose I reach at this specific point and I will also have another gradient descent which looks like this. Let's say that in the initial time I reach the point over here. How we will be coming to this minimal global minima? By using this equation. I'll talk about alpha also, don't worry. Now this is also my theta 1, this is also my j of theta 1. Now let's say, suppose I came to this particular point, right? After coming to this particular point, I will basically apply this derivative on this j of theta 1. Okay. Now when I find out a derivative, that basically means we are trying to find out the slope. And in order to find the slope, we just create a straight line like this, which will look like this. I'll just try to create. So I'll try to create a slope like this. This slope, so if you try to find out with respect to this is a positive slope. How do we indicate it? Because understand, the right hand side of the line of this is pointing on the topwards direction. This is the best easy way to find out whether it is a positive slope or negative slope. Now in this particular case, this is a positive slope. Now when I get a positive slope, that basically means I will update my weights or theta 1 as theta 1. Let's say I'm writing it over here. So I will just apply this convergence algorithm. See, theta 1 colon theta 1 minus this learning rate, which is called as alpha, This is my learning rate. I'll talk about learning rate, don't worry. Then this derivative value, in this particular case, since I'm having a positive slope, I will be getting a positive value. So let's say that for this theta value, I got this slope initially. Now I need to come to this location. So for that, I have to reduce theta 1 so that I come to this main point. Now here you can see that I am subtracting theta 1 with something which is a positive number. Right? This is a positive number. So definitely I know that after some n number of iteration, I will be able to come to the global minima. Similarly, if I take the right hand side and if I try to draw the slope, in this particular case, my slope will be negative. So similarly, I can write the equation as theta 1 equal to theta 1 minus learning rate multiplied by a negative number. So minus into minus will be positive, right? Suppose initially my theta 1 was here. My theta 1 was here. Now I'll keep on updating the weight to come to this global minima. So minus into minus is positive. So I will basically get theta 1 plus alpha by a positive number, because minus into minus is plus. So this will definitely work so that we will be able to come over here to the global minima, whether it is a positive slope or a negative slope. Now, what is this learning rate? Now, learning rate, based on this learning rate, suppose I want to come from this point to the global minima. By what speed I should be coming? What speed? If my learning rate value is bigger, what speed I may be coming? Suppose if I say, usually we select learning rate as 0.01. If I select a small number, then it will start taking small steps to move towards the optimal minima. But if I take a alpha value, a huge value, if it is a huge value, then what will happen? This updation of the theta 1 will keep on jumping here and there, and the situation will be that it will never reach the global minima. So it is a very good decision to take our alpha as small value. It should also not be a very small value. If it becomes a very small value, then what will happen? Very tiny steps. It will take forever to reach the global minima. That basically means my model will keep on training itself. So definitely this algorithm is going to work. Now let me talk about one scenario. One scenario will be that what if my cost function has a local minima? What if I have a local minima? Because here if I come, this is a local minima. Suppose one of my points come over here and finally I am reaching over here. What will happen in this particular case? Because in this case, you will be seeing that what will be my equation? My equation will be simply theta 1 minus alpha. In this point, in this local minima, slope will be 0. So in this particular case, my theta 1 will be equal to theta 1. Now you may be thinking, what is, if this is the scenario, then we will be stuck in local minima. This is called as local minima. But usually with respect to the gradient descent and the equation that we are using here, we do not get stuck in local minima, because our gradient descent in this particular scenario will always look like this. But yes, in deep learning, when we are learning about gradient descent and ANN, at that point of time, we have a lot of local minima. And because of that, we have different gradient descent algorithm like RMS prop. We have Adam optimizers, which will solve that specific problem. So this one point also I wanted to mention, because tomorrow if someone asks you as an interview question that what if in your, do you see any local minima in linear regression? You could just say that the cost function that we use will definitely not give us local minima. But if in deep learning techniques with that we are trying to use like ANN, we have different kind of optimizers which will solve that particular problem. So that is the answer you basically have to give. Now let me go ahead and write with respect to the gradient descent algorithm. So here again I'm going to write the gradient descent algorithm. So this will be my gradient descent algorithm. And remember guys, gradient descent is an amazing algorithm and you will definitely be using it. So please make sure that you know this perfectly. Now some questions are there, when will convergence stop? Convergence will stop when we come to near this area where my j of theta will be very less. Now in gradient descent algorithm, I will again repeat it. So what did I say? I said repeat until convergence. I told you, right? Here we have written this algorithm. And now let's take it for theta 0 and theta 1. So here I will write theta 0 j equal to theta j minus learning rate of derivative of theta j of theta 0 and theta 1. So this is my repeat until convergence. Now we really need to find out what we'll try to equate. We'll try to first of all find out what is this. Now if I really want to find out derivative of theta j with respect to j of theta 0 and theta 1. So how do I write this? I can definitely write this in an easy way. Okay, so this will be derivative of theta j, and remember j will be 0 and 1, right? Because we need to find out for 0, theta 0 and theta 1. So this will be 1 by 2m. What is j of theta 0 comma theta 1? Obviously my cost function. So I will write summation of I is equal to 1 to m, and here I will basically write j of theta of x of I minus y of I whole square. So if my j is equal to 0, so what will happen for this? So here I can specifically say that derivative of theta 0, j of theta 0 comma 1. Now it's simple. Here what I will be doing is that I will be simply applying derivative function. See guys, what is this derivative? Let's consider this is something like this, 1 by 2m x square. So if I try to find out the derivative, this will be 2 by 2m x. So 2 and 2 will get cancelled. So similarly I will have 1 by m, and here I will specifically be writing summation of I is equal to 1 to m h theta of x of I, which will be my x, minus y of I whole square. So this will be my derivative with respect to theta 0. This is what I got. Now the second thing will be that when j is equal to 1, derivative of theta 1, j of theta 0 comma theta 1. In this particular case I will be having 1 by m summation of I is equal to 1 to m. Then again, see, in this particular case theta of 1 is there, right? Theta of 1 basically means what? If I try to replace this, let's say that I am trying to replace this h theta of x with something else. What is h theta of x? I know that, right? It is theta 0 plus theta 1 multiplied by x. So theta 0 plus theta 1 multiplied by x. So after this, if I am trying to find out the derivative with respect to theta 0, this will obviously become, I will be able to get this much, right? Now with respect to the second derivative, what I will be writing? I will again be writing h theta of x of I minus y of I whole square multiplied by x of I. So this square also went off. Understand, this h theta of x is what? See, dekho, h theta of x is nothing but theta 0 plus theta 1 multiplied by x. So if I am trying to find out derivative with respect to theta 0, nothing will be going to come. Okay, theta 1 of x will become a constant in this particular case. In this case, because theta 1 of x is there, so if I try to find out derivative of theta 1 into x, only I will be getting x. Why square will not be there? It's easy, right? X square means 2x. This is the derivative of x square, right? So that square went, and 1 by 2 by 2 got cancelled. So this will be now my convergence algorithm. So here we have discussed about linear regression. Oh, sorry, I have to remove square here also. So let me write it again. Okay. Repeat until convergence. Let me write it down again. Repeat until convergence. Finally, your two updates will be happening. One is theta 0. So here it will be theta 0 minus alpha, that is my learning rate, 1 by m summation of I is equal to 1 to m, and this will basically be h theta of x of I minus y of I. Okay? And similarly, if I want to update theta 1, it will be minus alpha 1 by m summation of I is equal to 1 to m h theta of x of I, oh my god, y of I multiplied by x of I. Alpha is a learning rate, guys. Alpha is nothing but it is learning rate. Here we have to initialize some value like 0.001. See, what is h theta of x? Theta 0 plus theta 1 into x, right? if I do derivative of theta 1 into x, what is derivative of theta 1 with theta 1 x? It is nothing but x. So this x will come over here. Now let's discuss about two important things. One is r square and adjusted r square. Now similarly, what will happen? You will have a lot of convex functions now. See, if I talk about like if you have multiple features like x1, x2, x3, x4, at that point of time, you will be having a 3D curve which looks like this. Gradient descent आपका ऐसा दिखेगा, देखिए, which will be something like this. Gradient descent आपका ऐसा दिखेगा, ठीक है, यहाँ से भी आ रहा होगा, यहाँ से भी आ रहा होगा, एक अलग स्लोप आ रहा होगा, फाइनली इधर नीचे आना है. It's just like coming down a mountain. Now let's discuss about two performance metrics which is important in this particular case. One is r square and adjusted r square. We usually use this performance metrics to verify how our model is and how good our model is with respect to linear regression. So r square is basically given. R square is a performance metrics to check how good this specific model is. So here we basically have a formula which is like 1 minus sum of residual divided by sum of total. Now this is the formula of r square. Now what is this sum of residual? I can basically write like this: summation of yi minus yi hat whole square. This yi hat is nothing but h theta of x. Just consider in this way. Divided by summation of y of I minus y mean y whole square. तो ये formula है. This is the formula. I'll try to explain you what this formula definitely says. Okay. So first thing first, let's consider that this is my problem statement that I'm trying to solve. Suppose these are my data points. And if I try to create the best fit line, this yi hat basically means this specific point. We are trying to find out the difference between these things. Let's say that these are my points. I'm trying to find out the difference between this predicted. This is my predicted. The point in green color are my predicted points, which I have denoted as yi hat. And always understand, this is what sum of residual is. Sum of residual is nothing but difference between this point to this point, this point to this point, this point to this point, this point to this point. And I am doing all the summation of those. Now, the next point which is very much important, here is my x and y. What is this? yi minus y bar. Y bar is nothing but mean of y. If I calculate the mean of y, then I will probably get a line which looks like this. I'll get a line something like this. And then I will probably try to calculate the distance between each and every point and this specific point with respect to the distance between this point and this point. The denominator will definitely be high, right? This value, obviously this value will be higher than this value, right? The reason why it will be higher, because the mean of this particular value distance will obviously be higher. So this 1 minus high, this will be a low value and this will be a high value. When I try to divide low by high, then obviously this entire number will become a small number. When this is a small number, 1 minus small number will be a big number. So this basically shows that our r square has fitted properly, right? It has basically got a very good r square. Now tell me, can I get this entire r square a negative number? Let's say that in this particular case, I got 90%. Can I get this r square as negative number? There will be situation, guys. What if I create a best fit line which looks like this? If I create this best fit line which looks like this, then this value will be quite high. It is only possible when this value will be higher than this value. Okay, but in a usual scenario, it will not happen, because obviously we'll try to fit a line which will be at least good. It's not just like pulling one line somewhere. We don't want to create a best fit line which is worse than this, right? Worse than this. So in this particular scenario, you will be saying that in r square, now here you will be able to see one amazing feature about r square is that, let's say one scenario. Suppose I have features like, let's say that my feature is something like, let's say I have a price of a house, okay? So suppose this is my bedrooms, how many bedrooms I have, and this is basically the price of the house. Now, if I probably solve this problem, I'll definitely get an r square value. Let's say the r square value is 85%. Let's say that my R square is 85%. Now what if I add one more feature? The one more feature basically says that, okay, if I add location of the house will be definitely correlated with price. So there is a definite chance that the R square value will increase. Let's say that R square will become 90%. If I probably have this two specific feature, and obviously it is basically increasing the R square because this is also correlated to price. And let me change the example. See, first case I got my R square as 85%, let's say. Now as soon as I added location, I got a 90%. Now let's say that I added one more feature which gender is going to stay. Gender like male or female is going to stay. You know that gender is nowhere correlated to price. But even though I add one feature, there is a scenario that my R square will still increase and it may become 91%. Even though my feature is not that important. Even gender is not that important. The R square formula works in such a way that if I keep on adding features and that are nowhere correlated, this is obviously nowhere correlated. This is not correlated with price. Then also what it does is that it is basically increasing my R square. So this specific thing should not happen. Whether a male will stay or female will stay, that does not matter at all. Still, when you do the calculation, the R square will still increase. So in order to not impact the model, because see, now right now with this particular model where I have got 90%, now as soon as I see R square as 91%, because it is considering this particular gender, so this model will be picked, right? Because it is performing well and is giving you a better R square value. But this should not happen because that is not at all correlated. This model should have been picked. So in order to prevent this situation, what we do, we basically use something called as adjusted R square. Now what is this adjusted R square and how it will work? I'll also show it to you. Very, very nice concept of adjusted R square. So adjusted R square adjusted is given by the formula 1 minus R square multiplied by n minus 1, where n is the total number of samples, n minus p minus 1. This p is nothing but number of features or predictors, we'll also say, or predictors. Suppose initially my number of predictors were in this particular scenario, where I saw this, my number of predictors was 2, and in this particular case my number of predictors were 3. Now if my predictor is 2, I got the R square as 90%. So in this particular scenario, what? All the calculation will happen. Okay, all the calculation will happen. And let's say that my R square adjusted, it will be little bit less. Let's say 86%. Let's say that my R square adjusted is 86% based on this predictor 2. Now when I use my predictor 3, predictor basically means number of features that I'm going to use. And now in this one feature is nowhere related like gender. But what we are getting, we were basically getting R square increased to 91%. Now for the R square adjusted, this will not increase. This will in turn decrease. Right now it will become 82%. How it will become, I'll show you. I've just considered some value 86, 82. Here you can see that there is an increase. Here an increase is there. Here decrease is there. Now how this is basically happening? See, this p value that I will be putting, okay, if I put a p is equal to 3, obviously with n minus p minus 1, this will become a little bit smaller number, smaller number, right? So now in this particular case, if it is not correlated, obviously this will be high. When I'm increasing this, so this will also be high. Let me write the equation something like this, just a second. So this will basically be, okay. Now, why probably this value may have decreased? Let me talk about this one. What is R square? I hope everybody understood. N is the number of data points. P is the number of predictors. If P is increasing, then what will happen? As P keeps on increasing, this value will keep on decreasing. This value will keep on decreasing. If this values keep on decreasing, this will be a bigger number. This will obviously be a big number. A big number divided by a small number, what it will be? Obviously, this will be a little bit bigger number. 1 minus bigger number, we will basically get some values which will be decreasing. If my P value is 2, in this particular case, it will be less smaller than this. right? At least it will be greater than this particular value, right? When P is equal to 3. So with the help of P, obviously R square is there to support you, okay, whether it is correlated or not. Always remember, when the features are highly correlated, your R square value will increase tremendously. If it is less correlated, then there will be a small increase, but there will not be a very huge increase. Now if I consider P is equal to 2, obviously when I am trying to find out this calculation n minus P minus 1, it will obviously be greater than P is equal to 3. When P is equal to 3, then this value will be still more smaller. And when we are dividing a bigger number by a smaller number, obviously we are subtracting with 1. So that basically means, even though my R square is 86 over here, there may be a scenario, since this is nowhere correlated, I'm basically getting an 82% because of this entire equation. So I hope you are understanding this. This is very much important to understand. A very, very important property. Simple way to define is that as my P value keeps on increasing, the number of predictors keeps on increasing, my R square gets adjusted. Whatever R square I am getting with respect to this, it will always be less than this particular R square. There was one interview question that was asked to one of my students. Between R square and adjusted R square, which will always be bigger? Definitely the student said R square. Then he told him to explain about adjusted R square. Why does that specific happen? Agenda 1 is about ridge lasso regression. Second is assumptions of linear regression. The third point that we are probably going to discuss about is logistic regression. Then the fourth thing that we are going to discuss about is something called as confusion matrix. The fifth thing that we are going to consider about is practicals for linear, ridge, lasso, and logistic. So first topic that we are probably going to discuss is something called as ridge and lasso regression. So let's understand about ridge and lasso regression. If you remember, in our previous session, what all things we discussed? Linear regression. And then we had discussed about the cost function. We have discussed about R square adjusted R square. Sorry, R square and adjusted R square. We have discussed about it. Gradient descent, we had discussed about it. It was nothing but 1 by 2m summation of I is equal to 1 to m h theta of x I minus y I whole square. So this is the cost function that we had discussed, right, yesterday. And this cost function was able to give us a gradient descent with respect to the j of theta 0 or theta naught. So I can also write this as j of theta 0 theta 1. Now let me give you a scenario. Let's say that I have a scenario over here and I have this specific scenario. Let's say that I just have 2 points, which looks like this. Okay. Now if I have these 2 specific points, what will happen? I will probably try to create a best fit line. The best fit line will definitely pass through all the points like this. If I try to calculate the cost function, what will be the value of j of theta 0 theta 1? Let's say that in this particular case, since it is passing through the origin, my theta 0 will be 0. Okay. So what will be the value of theta 0 theta 1? So here obviously you can see that there is no difference. So it will obviously become 0. Now understand this data that you see, right? This data is basically called as training data. So this data that I have actually plotted with 2 points, these are specifically called as training data. Now, what is the problem in this data right now? See, right now, exactly whatever line is basically getting created over here, which is through the hypothesis. Over here, you can see that it is passing through every point. So that is the reason your cost is 0. And our main aim is to basically minimize the cost function. That is absolutely fine. Now, in this particular case, in which my model, if this model is getting trained, initially this data is basically called as a training data. Now, just imagine that tomorrow new data points comes. So if my new data points are here, let's consider that I want to basically come up with this new data point. Now in this particular scenario, if I want to predict with respect to this particular point, Let's say my predicted point is here. Is this the difference between the predicted and the real point quite huge? Yes or no? So this is basically creating a condition which is called as overfitting. That basically means even though my model has given or trained well with the training data, or let me write it down properly over here. So this condition, since you can see that over here, my each and every point is basically passing through the best fit line. So because of that, what happens? It causes something called as overfitting. So you really need to understand what is overfitting. Now, what does overfitting mean? Overfitting basically means my model performs well with training data, but it fails to perform well with test data. Now, what is the test data over here? The test data is basically this points. The real test data answer was this points. But because my line is like this, I'm actually getting the predicted point over here. So this distance, if I try to calculate, it is quite huge. So in this scenario, whenever I say my model performs well with training data and it fails to perform well with test data, then this scenario we say it as overfitting. So this scenario, when the model performs well with training data, I have a condition which is called as low bias. And when it fails to perform with the test data, then it is basically called as high variance. Very important. Okay, I will make each and everyone understand one by one. If it is performing well with the training data, that is basically low bias. And whenever it performs well with the fails to perform well with the test data, then it is basically high variance. Now, similarly, I may have another scenario which is called as underfitting. So let's say that I have something called as underfitting. Now, in this underfitting, what is the scenario? The model fails to perform. It gives bad accuracy. I'll say that model. Always remember, whenever I talk about bias, then you can understand that it is something related to the training data. Whenever I talk about test data, at that point of time, you talk about variance. And that specifically, whenever you talk about variance, that basically means we are talking about the test data. So for an overfitting, you will basically have low bias and high variance. Low bias with respect to the training data and high variance with respect to the test data. Now, if the model accuracy is bad with training data and the model accuracy is also bad with test data, in this scenario, we basically say it as underfitting. So these are the two conditions that are with respect to underfitting. That basically means that both for the training data also the model is giving bad accuracy, and again for the test data also it is basically having a bad accuracy. So in this particular scenario, we can definitely say two things out of underfitting. One is high bias and high variance. So this is the condition with respect to underfitting. Very super important. Let me just explain you once again. Suppose let's consider I have one model. I have model 2. This is model 1. This is model 1. This is model 2. And this is model 3. Okay guys, so suppose let's say that I have my model. My training accuracy is, let's say, 90%. And let's say that my test accuracy is 80%. Now in this particular case, let's say that my training accuracy is 92% and my test accuracy is 91%. And let's say my model 3 is basically having training accuracy as 70% and my test accuracy is 65%. So if I take this particular case, it is basically overfitting. If I take this particular thing, this basically becomes my generalized model. And when I talk about this is my, I'll just say that, okay, I'll also put nice colors so that you will be able to understand this. This becomes our generalized model. And this finally becomes our underfitting, right? Underfitting. So here is my red color. I will just say it as underfitting. What are the main properties of this? Overfitting, as I said, in this scenario, since it is performing well with the training data, so it will be low bias, high variance. In this particular case, it will be low bias, low variance. In this particular case, it will be high bias and high variance. Understand in this terminology, In this particular way, you will be able to understand. So why do we require always a generalized model? Because whenever our new data will definitely come, generalized model will be able to give us very good output. Let's go back to this particular example. Here you will be able to see this straight line, the red line that I have actually created is basically overfitting. So that whenever I probably get the new points, which is having this real value and the predicted points, here you'll be able to see the difference is quite huge. So because of this, it will definitely be a scenario of overfitting where it has low bias and high variance. So again, let me go ahead and take this example. So this was my line which I have actually drawn. I had 2 points, and when I draw this line, which was a best fit line which is passing through both the points, this scenario is basically causing a overfitting problem. And I have also shown you my j of theta 1 will be 0 in this scenario, since it is passing exactly and the predicted point is also over there. Now understand one thing is that what can we take out from this? What assumptions we can take out from this? Definitely, if I talk about our cost function here is nothing but 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I whole square. Now let's consider that I am going to use this h theta x and I'm going to basically write it as y hat. Okay, let's focus on this specific point. So when I take this, I'm just going to focus on this particular point. So here I will definitely write it as y hat minus y of I whole square. So this is my y hat of I minus y hat yi whole square. So this is nothing but the difference between the predicted value and the real value. Okay, this is what I'm actually trying to get. Now in this scenario, if I am adding these values, obviously I'm going to get the value as 0. Now I have to make sure that this value does not come to 0 because this is still overfitting. So that is where your ridge regression will come into picture. Ridge and lasso will come into picture. Now when I use ridge and lasso, suppose if I use ridge. Now in ridge, what we'd say this is also called as L2 regularization. Now L2 regularization, what it does is that it basically adds a unique parameter or add a one more sample value, which is like lambda multiplied by slope square. Now what is this slope? Whatever slope of this particular line it is, we are just going to square it off. Now suppose if I take my equation which looks like this, h theta of x is equal to theta 0 plus theta 1x. Now in this particular case my theta 0 was 0. So my h theta of x is nothing but theta 1. What is theta 1? This is specifically called as slope. And I am basically taking this theta 1, I'm actually making it as a square. So always understand, I don't want to make this as 0 because if it becomes 0, it may lead to overfitting condition. Now what will happen? If I add this particular equation, this will obviously come as 0. Let's consider my lambda value over here. My lambda value is 1. I'll talk about how do you set up lambda value. Okay, let's consider that I'm initializing it to 1. Let's say my lambda value is 1. Now, what I will do is that this lambda value is 1. Let's consider our slope value initially is 2. And because of this 2, I got this best fit line. I'm just going to consider it. So if I do the total sum over here, if I'm just considering this value is 3. Now the cost function will not stop over here because still it has to minimize. It has to reduce this 3 value. So what it will do? It will again change the theta 1 value, and let's say that my theta 1 value has changed. Now it got another best fit line which looks something like this. This is my next best fit line. I'll talk about lambda. Lambda is a hyperparameter, guys. What exactly is lambda? I'll just talk about it. Now when I basically change this line, now see why I'm getting this line. Let's consider I've changed my theta 1 value since we need to minimize. Now when we need to minimize, what it will do, we'll again calculate the slope of this particular line and then we will try to create a new line. When we, sorry, it is 2, not 3. Just a second, guys. 0 plus 1 multiplied by 2 square, which is nothing but 4. So now my cost function will not stop over here. So we are going to still reduce this. Now in order to reduce this, again theta 1 value will get changed and then we will get a next best fit line for this point. Now what will happen in this scenario once we have this best fit line? We will definitely get a kind of small difference. So now if I go ahead and consider the new equation, my y hat I minus yi whole square plus lambda of slope square, this value will be a small value now because I have some difference, and then plus again 1 multiplied by, now understand whether the slope will increase in this particular case or whether it will decrease in this particular case. There will be some slope value. Let's say that I have got some slope of this particular line. In this particular scenario, again your slope will definitely decrease. So let's say in the case of 2 initially it was, now it is basically 1.36 whole square. Now this small value plus 1 plus 1.3 square, or let me consider that my slope is now one simple value, that is 5. So if I get this, it is 2.25. 2.25 plus small value, it will be less than 3 only, right? It will obviously be less than 3 or equal to 3. But understand what is happening. The value is getting reduced from 4 to 3. So this is the importance of ridge. Now what will happen is that you will try to get a generalized model which has low bias and low variance instead of this overfitting condition. You know why specifically we are adding ridge L2 regularization? It is basically to prevent overfitting, because here you are not stopping here. You are trying to reduce it unless and until you get a line, which will be able to handle as a generalized model. Now here you can see, now if I have my new points like how I drew over here, now the distance will be less. So now you will be able to see that it will be able to create a generalized model. Guys, this will be a small value only. See, initially when we have this line, obviously we have 0. If we try to slightly move here and there, so here you will be able to see that it will just a slight movement. But what this movement is basically specifying, it is specifying that the slope should not be steep. If we probably have a steep slope, it obviously leads to most of the time overfitting condition. It should not be steep. It should be it should be less steeper, but it should actually help you to create a generalized model. So you will be seeing that after playing for some amount of time, this value will not reduce after some point of time. It will get almost, it will be a minimal value, it will be a smaller value. And for this also you have to specify iterations. How many times you probably have to train them. Now this iterations is also a hyperparameter. Based on number of iterations, you will probably see your R square or adjusted R square over here. So this iterations, based on the number of iterations, it will never become 0, guys. Understand? Because 0, it is not possible. If it becomes 0, trust me, it is an overfitting model. You cannot get that is something 0 over here. Now what is lambda? Coming to this lambda is a hyperparameter. This is basically to check how fast you want to lessen the steepness or how fast you want to make a steepness grow higher, right? And this lambda will also be selected by using hyperparameter. And this also I'll show you today in practical. What do you mean by iterations? Iteration basically means how many times I want to change the theta 1 value. How many times you want to change the theta value. That is the convergence algorithm, right? Convergence algorithm. Over here, L2 regularization or ridge is basically used in such a way that you should never overfit. Why we assume theta 0 is equal to 0? Because I am considering that it passes through a origin, right? Origin over here. Lambda is a hyperparameter. Steep basically means how steep the line is. If I have this line is quite steep. If I have this line, this is less steep. Now, if I go to the next regularization, which is called as Lasso regression, this is also called as L1 regularization. Now here the formula will be changing little bit. Here you will be having y hat of minus of y whole square. Here you will be adding a parameter lambda. But understand, here you will not be adding slope square. No. Here you will be adding mode of slope. Here you will be adding mode of slope. And this mode of slope, the work is that it will actually help you to do feature selection. Now you may be thinking, how feature selection, Krish? Let's consider an equation over here. Let's say that I have many features. I have many features, okay? So my h theta of x, which I'm indicating here as y hat, let's say that I'm writing this equation. Apart from preventing for overfitting, it will also help you to do feature selection here. Let me just show you over here with an example. This h theta of x, which I'm probably writing as y hat, will basically be indicated by something. Over here, you'll be able to see that it is nothing but, let's say that I have multiple features like this. Now in this particular features, obviously there are so many coefficients over here, so many slopes over here. Now mod of slope will be what? It will be nothing but mod of x1 plus x2 plus x3 plus x4 plus x5 like this up to xn. Now in this particular case, how it is basically helping you to, sorry, not x1, sorry, just a second. This mod of, I have taken the data points. This is not data points. This should be your mod of theta 0 plus theta 1 plus theta 2 plus theta 3 plus theta 4 plus theta 5 like this up to theta n. So here you will be able to see that this is how I will basically be calculating the slope. Now, as we go ahead, guys, whichever features are probably not playing an amazing role, the theta value, the coefficient value, the slope value will be very, very small. It is just like that entire feature is neglected. That entire feature is neglected. Now, in this particular case, we were doing squaring. Because of this squaring, that value was also increasing. But here, because of the mode, that value will not increase. Instead, it will be a condition wherein we are basically neglecting those features that are not at all important in this specific problem statement. So with the help of L1 regularization, that is Lasso, you are able to do two important things. One is preventing overfitting, and the second case is that if you have many features and many of the features are not that important, okay, in basically finding out your slope or your line or the best fit line, in that particular case, it will also help you to perform feature selection. So this is the importance of the entire, what is the importance of this? This is the importance of the ridge and the lasso regression that we are doing. Here I'm just going to write L1 regularization, and obviously we have discussed about L2 regularization also. Now you have probably understood lambda is one hyperparameter, okay, which we will specifically using, okay, and based on this lambda, this will be found out through cross validation. Cross validation is a technique wherein we will try to probably train our model and try to find out this specific things, okay, what should be the exact value, and there also we play with multiple values. In short, what we are doing, we are just trying to reduce the cost function in such a way that it will definitely never become zero, but it will basically reduce based on the lambda and the slope value. In most of the scenario, if you ask me, we should definitely try both the regularization and see that wherever the performance metrics is good, we should use that. What is cross validation basically means? I will try to use different lambda value and basically use it. So in a short, let me write it down again. For ridge regression, which is an L2 norm, here I'm simply writing my cost function in this particular case will be little bit different. Here I can definitely write my cost function as h theta x of I minus y of I whole square plus lambda multiplied by slope square. What is the purpose of this? The purpose is very simple. Here we are preventing overfitting. This was with respect to the ridge regression, that is L2 norm. Now if I go ahead and discuss about the next one, which is called as lasso regression, which is also called as L1 regularization. In the case of lasso regression, your cost function will be h theta of x of I minus y of I whole square plus lambda multiplied by mode of slope. So here you have this specific thing, and what is the purpose? The purpose are two. One is prevent overfitting, and the second one is something called as feature selection. So these two are the outcomes of the entire thing. See, with respect to this lasso, right, you have slopes. Slopes here you will be having theta 0 plus theta 1 plus theta 2 plus theta 3 like this up to theta n. Now when you will have this many number of thetas, when you have many number of features, and when you have many number of features, that basically means you'll have multiple slopes, right? Those features that are not performing well or that has no contribution in finding out your output, that coefficient value will be almost nil, right? It will be very much near to zero. In short, you are neglecting that value by using modulus. You're not squaring them up. You're not increasing those values. Now I will continue, and probably I will also discuss about the assumptions of linear regressions. So what are the assumptions of linear regression in this particular scenario? So assumption is that, number one point, linear regression, if our features are in normal or Gaussian distribution, if our features follows this particular distribution, it is obviously good, our model will get trained well. So there is one concept which is called as feature transformation. Now in feature transformation, always understand what will happen if a model does not follow a Gaussian distribution. Then we apply some kind of mathematical equation onto the data and try to convert them into normal or Gaussian distribution. The second assumption that I would definitely like to make is that standard scalar or standardization. Standardization is nothing but it is a kind of scaling your data by using z-score. I hope everybody remembers z-score. This is what we basically apply. There your mean is equal to 0 and standard deviation equal to 1. See guys, wherever you have gradient descent involved, it is good to basically do standardization. Because if our initial point is a small point somewhere here, then to reach the global minima, our training will happen quickly. Otherwise, what will happen if your values are quite huge, then your graph may be very big and the point can come over there. And the third point is that this linear regression works with respect to linearity. It works if your data is linearly separable. I'll not say linearly separable, but this linearity will come into picture. If your data is too much linear, it will obviously be able to give a very good answer. Like logistic regression also, which we are going to discuss today, this also has the same property. Now, you may be asking, is it compulsory to do standardization? Guys, if you want to increase the training time of your model, or if you want to optimize your model, I would suggest go ahead and do standardization. Now, coming to the fourth point, here you really need to check about multicollinearity. This is also one kind of check we basically do. What is multicollinearity? Let's say I have x1, I have x2, and this is my output feature. I have, let's say, x3 also. Now let's say that if I try to see the collinearity of this two feature, how correlated these two feature are. Let's say that these two feature are 95% correlated. Is it a wise decision to use both the features? And let's say that let's say that these two features are 95% correlated, but it is highly correlated with y. Is it necessary that we should use both the feature in this particular scenario? The answer should be no. We can drop this particular feature. Okay, we can drop this particular feature. Any one of the feature we can definitely drop it. And based on that, I can just use one single feature and basically we do the prediction. There is also a concept which is called as variation inflation factor. I will try to make a dedicated video about this. Multicollinearity is also solved with the help of variation inflation factor. One more term is there, homozoidicity. So that kind of terminology is also we use one more condition in this. But if you are almost satisfied with this assumptions, you will definitely be able to outperform in linear regression. So you have got an idea of the assumptions. You have also got an idea of multiple things. Okay. Now let's go towards something called as logistic regression. Now logistic regression. What logistic regression is the first type of algorithm that we are going to learn in classification. Let's say that in classification, I have one example. Suppose I have say number of hours, study hours, and number of play hours. Based on this, I want to predict whether a child is passing or failing. Suppose these two are my features. I want to predict whether it is pass or fail. So here you'll be able to see that I have some fixed number of categories. Specifically in this particular scenario, I have two categories. Binary logistic regression works very well with binary classification. Now the question comes that can we solve multi-class classification using logistic? The answer is simply yes, you can definitely do it. So let's go ahead and let's try to discuss about logistic regression. Now, what is the main purpose of the logistic regression? First of all, let's understand one scenario. Okay, suppose I have a feature which basically says number of study hours, and this is like 1, 2, 3, 4, 5, 6, 7, and let's say that I have pass. This point is basically pass, and this point is basically fail. So I have these two conditions. These are my outcomes. Now what I'll do, I will just try to make some data points. Let's say that if I study less than 3 hours, I will probably be fail. If I study more than 3 hours, then probably I will pass. This I'll make it as fail, and this I will make it as pass. So I will be having points over here after this 1, 2, 3. Let's say that this is my training data set. Now the first question says that, okay, Krish, fine, you have some data over here. Whenever it is less than 3, you are basically, the person is failing. If it is greater than 5, greater than 3, it is basically showing data points with respect to pass. Now, can't we solve this problem first with linear regression? Now, with the help of linear regression, here the first point will be that yes, I can definitely draw a best fit line. My best fit line in this particular scenario may be something like this. It may look something like this. So here fail is nothing but 0, pass is 1. The middle point is basically 0.5. So obviously with the help of linear regression, I'm able to create this best fit line. And I'll put a scenario that whenever the value is less than 0.5, whenever the value is less than 0.5, whenever the output is less than 0.5, let's say that new data point is this. And based on this, I will try to do the prediction. I'm actually able to get the output over here. Now, when I'm getting the output over here, this basically is 0.25. Now, in this particular scenario, obviously, I'm able to say that, yes, the person, I'll write a condition over here saying that if my h theta of x value is less than 0.5, then my output should be 0. Let's say less than 0.5, I'll say not less than or equal to, less than 0.5, then my output will be 0, right? So in this particular case, 0 basically means fail. Similarly, I'll have a scenario when I'll say that if my h of theta of x is greater than or equal to 5, then this will basically be 1, which is nothing but pass. So this two condition I can definitely write over here. This is my center point. So that any point that will probably come over here, let's say that this point is coming over here, right? Let's say new data point is somewhere coming over here with this red point. Now what I'll do, I will basically draw a straight line. It will come over here. I will just extend this line long. I will extend this line over here, and I will extend this line over here. And here you can see that based on this, I'm actually getting this particular prediction, which is greater than 0.5. So I will say that, okay, the person has passed. Obviously, this is fine. This is obviously working better. This is obviously working better. So what is the problem? Why we are not using linear regression? Okay, in order to solve this particular problem, why you are specifically having logistic regression? The answer is very much simple, guys. The answer is that whenever, let's say that if I have an outlier which looks something like this. Suppose I have an outlier which comes like this over here. And what is this value? Let's say that this value is nothing but 7, 8, 9, 10. Let's say that the number of study hours when I'm studying for 9, it is obviously pass. Now in this particular scenario, when I have an outlier, this entire line will change. Now I will probably get my line which looks something like this. Okay, my line will basically move something like this. It will now get moved something like this. Now when it gets moves completely like this, now for even 5, or even at any point that I am actually predicting, let's say that at this particular point, if I try to find out, it will be showing less than 0.5. So here this particular value or answer will be wrong, right? Because if we are studying more than 5 hours, obviously based on the previous line, the person had to pass. But in this scenario, it is failing. It is coming less than 0.5. But the real value for this is basically passed. So I hope you are understanding. Because of the outlier, the entire line is getting changed. So how do we fix this particular problem? Now in this, two scenarios are there. First of all, obviously because of just an outlier, your entire line is getting shifted here and there. The second point is that over here, sometimes you're also getting greater than 1. You're also getting less than 1. Suppose if I try to calculate for this particular point, if I project it in behind, I will be getting some negative value. So we have to squash this function. If I squash this function, then it will become a plain line, right? How do we squash it? And for this, we use something called as sigmoid activation function or sigmoid function. If somebody asks you, why don't you use linear regression in order to solve this classification problem? Then your answer should be very much simple. You should say these two specific points. So we will try to go ahead and solve some linear regression now with the help of cost function, everything as such. And we'll try to understand how the cost function will look for logistic regression. Second reason I told you, right? It is greater than 0. Over here, the line is going greater than 0, right? Greater than 0. I have only 0 and 1, and it is becoming greater than 0. But I have already told that our maximum and minimum value are 1 and 0. So I hope you have understood why linear regression cannot be used. Okay, I showed you all the scenarios why linear regression should not be used. Now we'll continue and probably discuss about the other things over here. And we will now try to understand, fine, what exactly logistic regression is all about and how the decision boundary is basically created. Now we'll go ahead and discuss about that specific thing. So let's go ahead. Our values should be always between 0 to 1 over here in this particular case, because it is a binary classification problem. Only this should be the answer. So let's go ahead and let's define our decision boundary. So my decision boundary in the case of logistic regression. First of all, as usual, in logistic regression, we defined our hypothesis. Okay, guys, first of all, let's see. If I'm writing my h of theta, my h theta of x as theta 0 plus theta 1 into x plus theta 2 into x, like this, x1, x2 plus theta n into xn. Now in this scenario, can I write this entire equation as theta transpose x? Obviously, I can definitely write this way, right? And this is what is the notation that you will probably seeing in many places. So with respect to the decision boundary of logistic regression, our theta, see, like this we can write, I'm saying, okay? But since we have to consider two things, one is squashing the line, okay? How that squashing will basically happen. See, if I have this line, we saw in the above, right? If I have this line, suppose I have some data points over here and I have some data points over here. So if I want to create the best fit line, how will I create? I will basically create like this. But I have to also do two things. One is squash over here and squash over here, right? Squash over here and squash over here. Now, in order to squash, I'm saying squash. Squash means सीधा कर दो, ठीक है? सीधा कर दो. Now, in order to do this, I use a function which is called as sigmoid activation function. That basically means what happens. Obviously, you know this line is basically denoted by h theta of x is equal to, how do you denote this straight line? Let me write it down nicely for you. So how do you denote this straight line? This straight line is obviously denoted by theta 0 plus theta 1 multiplied by x1. Let's say. Now on top of this, I have to apply something. On top of this value, I have to apply something so that I can make this line straight instead of just expanding in this way. So my hypothesis will basically be now g is basically a function on theta 0 and theta 1 multiplied by x1. So here I'm trying to basically, what I'm trying to do, I will apply a mathematical formula on top of this linear regression to squash this line. Now let's go ahead and let's try to find out what is this g. Okay, what is this g? I will say let z is equal to theta 0 plus theta 1 multiplied by x. I'm just initializing this. Now my h theta of x is nothing but g of z. Now we need to understand what is this g of z and how do we basically specify what is the g function. So my g function is nothing but h theta of x is equal to 1 by 1 plus e to the power of minus z, which in short, if I try to initialize z now, it is 1 to the power of e to the power of minus theta 0 plus theta 1 multiplied by x. So this is what is my h theta of x, which is my hypothesis. And this obviously works well because it is being able to squash the function. So this is basically my hypothesis, which I am definitely trying to use it. And this function that you are actually able to see is called as sigmoid or logistic function. Now you need to understand what does this sigmoid function look like in graph. In graph, it looks something like this. So this is my z value and this is my g of z. This is my 0.5. Your sigmoid function will have this curve. So this is your 1, this is 0. Your value, now from this, we can make a lot of assumptions. What are the assumptions that we can basically make? Your g of z is greater than or equal to 0.5, is obviously greater than or equal to 0.5 when your z value is greater than or equal to 0. This is the major assumptions that we can basically make. That is, whenever your g of z is greater than or equal to 0.5, whenever your z is greater than or equal to 0. So obviously, whenever your z value is greater than 0, it is greater than 0.5. If your z value is less than 0, what it will become? It will basically be less than 0.5. So you can write that specific condition also you want. So this is the most important condition over here. Why it is called as logistic regression? See guys, with the help of regression, you are creating this straight line, and with the help of the concept of sigmoid, you are able to squash it. So they have probably combined that name and basically have written in this way. Will squashing of the best fit line help to overcome the outlier issues? Yes, obviously it will be able to help you. So let's go ahead and let's try to solve the problem statement. Now usually let's consider my training set. Let's consider my training set. Suppose I have some training points like this: x of 1 comma y of 1. Let's say x of 2 comma y of 2. Okay, x of 3 comma y of 3. Like this, I have a lot of training points, and finally x of n comma y of n. Let's say that this is my training data. So here my y will belong to what? 0 or 1, because I will only have 2 outputs since we are solving a binary classification problem. Here is my training set with 2 outputs, and I hope everybody knows about j theta of z. It is nothing but 1 plus e to the power of minus z. Here your z is nothing but theta 0 plus theta 1 multiplied by x1. So this is your theta 0. Now what we have to do, we have to select this theta. Now in this particular case, let's consider that my theta 0 is 0 because it is passing through the origin. Just for time pass sake, suppose my z is theta 1 into x. So now I need to change, what is my parameter? My parameter is theta 1. I have to change parameter theta 1 in such a way that I get the best fit line, and along that I apply the sigmoid activation function. Now let's go ahead and let's first of all define our cost function, because for this we definitely require a cost function. Now everything will be same. Obviously you know the cost function of linear regression, because the first best fit line that you are probably creating is with the help of linear regression. Now in this particular case, in the case of linear regression, so here you can basically write j of theta 1 is nothing but 1 by m summation of I is equal to 1 to m 1 by 2, and here you have h theta of x minus y of I whole square. So this is your entire thing of, if you remember, linear regression, whatever things we have discussed yesterday. Okay, so this is the cost function. Let's consider that for linear regression, this is for the linear regression. Now for the logistic regression, what will happen? For your logistic regression, I will take the same cost function h theta of x. Now you know what is h theta of x? It is nothing but 1 plus e to the power of minus theta 0 plus theta 1 multiplied by x, right? This is my, with respect to logistic regression, this is my entire equation. Now similarly, I will try to only put this h theta of x. Let's consider that this is my cost function. Only my h theta of x is changing in this particular case. So if I go ahead and write my cost function, I can basically say 1 by 2 h theta of x of I minus y of I whole square. And in this particular scenario, what is h theta of x? It is nothing but 1 plus e to the power of minus theta 1x. So this is what this is getting replaced, and this is my logistic regression cost function. I'm just considering this cost function part, this part. Later on, if you replace this to this, see, if I replace this to this, and if I replace this to this, it becomes a logistic regression cost function. Intercept, I'm considering it as 0, guys. Now when I'm replacing this to this to this, then it becomes a logistic regression cost function. But there is one problem. We cannot use this cost function. There is a reason for this, because this equation that you are seeing, 1 divided by 1 plus e to the power of minus theta 1 multiplied by x, this is a non-convex function. Now you may be considering, what is a non-convex function? So let me write it down. So here, this terminology, right? It is a non-convex function. Now what is this non-convex function? Let me show you, and let me differentiate it with convex function. Okay, we'll try to understand what is the difference between non-convex function and convex function. This is related to gradient descent. Very important. This is related to gradient descent. If you remember, with the help of linear regression, whatever gradient descent we are actually getting, it is a convex function like this. This is the convex function, which looks like a parabola curve. Parabola curve. Because of this parabola curve, whenever we use this linear regression cost function, specifically because here my h theta of x is what? It is nothing but theta 0 plus theta 1 into x. Because of this equation will always give you a parabola curve. This kind of cost function or convex function you can say. But here your h theta of x is changing. So in the case of, if I use that cost function, you will be getting some curves which looks like this. Now what is the problem with this curve? Here you have a lot of local minima. If local minima is there, you will never reach this global minima. So that is the reason we cannot use that cost function. Now mathematically you can also go and probably search in the Google what is the what is the graph or what is the convex or non-convex function. But always remember, whenever we updates theta 1 with this within this particular equation by finding the slope, then this way it will not be differentiable, and here you have lot of local minima, and because of this local minima you will never be able to reach the global minima. This is your global minima, right? In case of linear regression, you will reach this global minima, but in this case you will never reach. Never. You'll be stuck over here, or you may get stuck over here, you may get stuck over here. Okay, so this has a local minima problem. So how do we solve this? Understand, in local minima, these are my points, right? I have to come over here. This is my deepest point. In this particular case, I don't have any local minima. Now, in local minima also, you'll get slope is equal to 0. So that is the reason your theta 1 will never get updated. So in order to solve this problem, you can see this diagram. We have something called as logistic regression cost function. So I can now write my logistic regression cost function in a different way. So this researcher thought of it and basically came up with this proposal that the logistic cost function should look something like this. So the entire cost function of logistic regression, that is specifically h theta of x of I comma y, this should be written something like this, and it should be written like this. See, here I'm just going to write cost function of j of theta 1. Let's say that I'm writing j of theta 1. Okay, so j of theta 1, what are the different output that I'll be getting? I'll be getting y is equal to 1 or y is equal to 0. So based on these two scenarios, our cost function will look something like this: minus log of h of theta of x. And I hope you all know what is h theta of x. H theta of x is nothing but 1 plus 1 to the power of minus theta 1 x. So this is what is my h theta of x, and whenever y is 0, then you basically have minus log multiplied by 1 minus h theta of x of I. Okay, so this is how you basically write your cost function in this particular scenario. Now with the help of this cost function, it is always possible, since it is getting log is basically getting used. In this scenario, you will always get a global minima. That is the reason why they have completely neglected this cost function and utilized this cost function. Now what does this cost function basically mean? Two scenarios. If y is equal to 1, let's consider this is my cost function graph. I have h theta of x, and you know that h theta of x value will be ranging between 0 to 1, since it is a classification problem. So it will be ranging between 0 to 1, and this is basically of j of theta 1, which is my cost function. So if y is equal to 1, this specific equation will be used, and whenever this equation is basically used, you get a curve. See, minus log h theta of x of I, you get a curve which looks something like this. Okay, which you'll get a curve which looks like this. Now what does this curve basically specify? The curve come up with two assumptions. The cost will be 0 if y is equal to 1 and h theta of x is equal to 1. That basically means when your h theta of x is 1 and the y's output is 1, that basically means you are going to assign over here 1, right? So in this particular case, you will be seeing that your cost function will be 0. Cost is 0. So here is my 0. It is meeting over here. If your h theta of x is equal to 1 and y is equal to 1. So this is again a convex function. Then the next point that you can probably discuss over here is with respect to y is equal to 0. If your y is 0, then what kind of curve you will be getting? You will get a different kind of curve which will look like this: h theta of x. Here your value will be 0 to 1, and here you will be having a curve which looks like this. So when you combine these two, you'll be able to see that you are able to get a kind of gradient descent. So this will definitely help us to create a cost function. So I hope everybody is able to understand till here with respect to this, and this will definitely work. So finally, I can also write my cost function in a different way. The cost function that I will probably write over here. So this will be my j of theta 1. So I can come up with a cost function which looks like this. Cost of h of theta of x of I comma y minus log of h theta of x if y is equal to 1, and then minus log 1 minus h theta of x if y is equal to 0. Now I can combine this both and probably write something like this. I can combine this both and I can basically write cost of h theta of x of I comma y is equal to minus y log h theta of x of I minus log 1 minus y, okay, 1 minus y log of 1 minus h theta of x. So this will be my final cost function. And here also you can see that if I replace y with 1, then what will remain? Only this particular value will remain, right? This value. When y is equal to 1, this thing only will come. You see over here. Replace y with 1, probably replace y with 1, and then you'll be able to see. So here I can now write if y is equal to 1, my cost function will look something like this, which is nothing but see, y is 1, then what will happen? My log of h theta of x of I will come. And this 1 minus 1 is 0. So 0 multiplied by anything will be 0. If y is equal to 0, then what will happen? My cost function will be, so when it is 0, this will minus y will become 0. 0 multiplied by 0, anything is 0. So here you will be able to see that I'll be having minus log 1 minus h theta of x of I. So this both the condition has been proved by this cost function. So this is my cost function. Yes, cost function and loss function with respect to the number of parameters will be almost same. So finally, if I try to write j of theta, because I have that 1 by 2m also, right? So 1 by 2m also I have. So what I'm actually going to do here, you will be able to see that I can write j of theta 1 is equal to 1 by 2m summation of I is equal to 1 to m, and then write down the entire equation that you have probably written over here. So here you have minus y, or I'll just remove this minus and put it over here, and this will become plus, sorry, y of I multiplied by log h theta of x of I 1 minus y of I y log 1 minus h theta of x of I. So this becomes my entire cost function. And obviously you know what is h theta of x. H theta of x of I is nothing but 1 plus 1 e to the power of minus theta 1 multiplied by x. And finally my convergence algorithm, I have to repeat this to update theta 1. Repeat until this updation, that is theta j is equal to theta j minus learning rate derivative with respect to theta j, and this will be my j of theta 1. This is my repeat until convergence. So this is my cost function, this is my repeatance algorithm, and here I will be updating my entire theta 1, and this solves your problem with respect to logistic regression. Simple questions may come, like how it is different from linear regression, how it is not different from linear regression. Can we say log likelihood a topic from probabilistics? Yes, this is log likelihood. Now I will discuss about performance metrics, and this is specific to classification problem and binary classification I'm talking. Let's consider I have a data set which has x1 x2 and this is y. And obviously in logistic classification you have outputs like 0 1 0 1 1 0 1, and your y hat is basically the output of the predicted model. Now in this particular scenario my y hat will probably be 1 1 0 1 1 1 0. So in this particular scenario, this is my predicted output and this is my actual output. So can we come to some kind of conclusions wherein probably we will be able to identify what may be the accuracy of this specific model with respect to this many data points? Because confusion matrix is all dealt with. This is called as, we will first of all have to create a confusion matrix. Now for a binary classification problem, the confusion matrix will look like this. So here you have 1, 0, 1, 0. Let's say that this is prediction. Let's say that these are my actual value and these are my prediction value. Okay, this both are prediction value. These are my output value. When my actual value is 0, my predicted value is 1. What does this mean? Wrong prediction, right? So when my actual value is 0, my predicted value is 1. So here my count will increase to 1. Let's go to the second scenario. When the actual value is 1 and my predicted value is 1, that basically means 1 and 1. So here I'm going to increase my count. Similarly, when my actual value is 0, my predicted value is 0. So that basically means when my actual value is 0, my predicted value is 0, I'm going to increase the count by 1. If I go over here 1, 1, again it is, so instead of writing 1 now, this will become 2. I'm going to increase the count. Similarly, I'll go over here, one more 1 is there, so I'm going to increase the count 3. Then I have 0, 1. 0, 1 basically means when my actual value is 0, I'm actually getting it as 1. So I'm also going to increase this particular value as 2. And then finally I have 1 and 0 where I'm going to increase like this. Now what does this basically mean? See, with respect to this kind of predictions, whenever we are discussing, this basically says, so this is my actual values and I have 1 and 0, and this is my predicted values. I also have 1 and 0. This value when 1 and 1 are there, this is called as true positive. This value when 0 and 0 are there, this is called as false negative. Whenever your actual value is 0 and you have predicted 1, this becomes false positive. And whenever your actual value is 1, you have predicted 0, this becomes false negative. Now, coming to this, I really need to find out the accuracy of this model. Now, if I really want to find out, and this is what is called as confusion matrix. Now, in this confusion matrix, if I really want to find out the accuracy of this model, it is very much simple. This middle elements that you are able to see will basically give us the right output. So this and this, if I add it up, it will give us the right output. So here I'm going to get TP plus TN divided by TP plus FP plus FN plus TN. So once I calculate this, so I have 3 plus 1 divided by 3 plus 2 plus 1 plus 1. So this is nothing but 4 by 7. What is 4 by 7? 0.57. So am I getting 57% accuracy? So I'm actually getting 57% accuracy over here with respect to the accuracy. So this is how we basically calculate with respect to basic accuracy with the help of the confusion matrix. Okay, so this is specifically called as confusion matrix. Now there are some more things that you really need to specify. Always remember, our model aim should be that we should try to reduce false positive and false negative. Now let's say that I want to discuss about two topics. One is, suppose in our data set I have zeros and 1 category, let's say in my output. If I say zeros are 900 and ones are 100, this becomes an imbalanced data, very clear, right? So this becomes an imbalanced data set. It is a biased data. Suppose if I say zeros are probably 600 and ones are probably 400. In this particular scenario, I will say that this is a balanced data, because yes, you have 100 less, but it's okay. It may not impact many of the algorithm. Now see guys, most of the algorithm that we will be probably discussing, if we have an imbalanced data set, it will obviously affect the algorithms. Let me talk about this. Let's say that I have number of zeros as 900 and number of ones as 100. Now let's say that my model I have created, which will directly predict 0. I'll just say that all my inputs that it is probably getting with respect to this training data, it will just output 0. Now in this particular scenario, what will be my accuracy? My accuracy will be 900 divided by 1000, right? So this is nothing but 90%. So is this a good accuracy? Obviously it is a good accuracy, but this is a biased data. If my model is basically just outputting 0, 0, 0, 0, 0, if it is outputting 0, 0, 0, obviously most of the answer will be zeros, but this will be a scenario like, where it is just outputting one thing. Then also it is able to get 90% accuracy. So you should only not be dependent on accuracy. So there are a lot of terminologies that we will basically use. One terminology that we specifically use is something called as precision. Then we'll also use recall. What is precision? What is recall? I'll write the formula over here. In precision, what do we need to focus? And then finally, we will discuss about F-score. So we have to use different kind of parametrics, different kind of formulas whenever you have an imbalanced data set. You can also do oversampling, but again, understand in most of the scenarios, in some of the scenarios, oversampling may work, but we have to focus on the type of performance metrics that we are focusing on. Right now, I'll not say F1 score, I'll say F score. The reason why I'm saying, I'll just let you know. So let's talk about recall. Recall formula is basically given by true positive divided by true positive plus false negative. Precision is given by true positive divided by true positive plus false positive. And then I will probably discuss about F score also, or we basically say F beta also. Now I'll just draw this confusion matrix again, okay, which is having true positive, true negative. So let me draw it over here. So this is my ones and zeros. These are my actual values and these are my predicted values. I have true positive, I have true negative, false positive and false negative. Now in this particular scenario, when I'm actually discussing, understand what is recall and what focus it is basically given on. So here, whenever I talk about recall, recall basically says that TP divided by TP plus Fn. So I am actually focusing on this. So what does this basically say? True recall. Out of all the actual true positives, how many have been predicted correctly? That is basically mentioned by TP. Out of all the positive values, how many of them have predicted as positive? So this is what it is basically saying. And this scenario is called as recall. In this, the false negative is basically given more priority. And our focus should be that we should try to reduce false negative. We should try to reduce this. Now let's go ahead and let's discuss about precision. In precision, what we are doing, we are basically taking out of all the predicted values, out of all the predicted positive values, how many of them are actual true or positive. Okay, this is what precision basically means. Now suppose if I consider spam classification, suppose this is my task. Tell me in this particular case, should we use precision or recall? And one more use case, I'm saying that whether the person has cancer or not. In which case we have to support recall and in which case we have to go ahead with precision. Has cancer or not. In spam, what is important? Okay guys, the recall is also called as true positive rate. I can also say recall as sensitivity. So if I go with spam classification, it should definitely go with precision. Why it should go with precision? If I probably get a spam mail, the main aim should be that whenever I get a spam mail, it should be identified as spam. Okay. In that specific scenario, my false positive, we should try to reduce. And in this scenario, my false positive talks about the spam classification a lot in a better way. In the case of cancer, I should definitely use recall. Let's focus on the recall formula. TP divided by TP plus Fn. If a person has a cancer, see 1. Actually, he has a cancer. It should be predicted as 1. Otherwise, if we have Fn, it is basically predicting it does not have a cancer. That is really a big situation in this case. If a person does not have a cancer and if the model predicts, okay, fine, he has a cancer, he may go and further do the test and then he'll come to know whether he has a cancer or not. But this scenario is very dangerous if a person has a cancer, but he is being indicated that he does not have that cancer. So here, false negative is given more priority over here. In the case of spam classification, false positive is given more priority. So this is something important over here and you really need to understand with respect to different problem statement. Let me give you one more example. Tomorrow, the stock market is going to crash. In this, what we need to focus on? Should we focus on precision or should we focus on recall? Now here, two things are there. Who is solving what kind of problem? See, many people will say recall or precision, but here two things are there. On whose point of view you are creating this model? Are you creating this model for the industry or are you creating this model for the people? For the people, he should definitely get identified that, okay, in this particular scenario, you need to sell your stock because tomorrow's stock market is going to crash. But for companies, this is very bad. Okay, I hope everybody is able to understand. For companies, it is very bad. So in this particular case, sometimes we need to focus both on false positive and false negative. And again, I'm telling you, for which problem statement you are solving, that indicates. If you are solving for people, then they should be able to get the notification saying that it is going to crash. If you are probably doing it for companies, at that time, your precision recall may change. But if I consider for both the scenarios, at that point of time, I will definitely use something called as F score. F score, or I'll also say it as F beta. Now, how is F beta formula given as? I will talk about it. And here in the F score, you have three different formulas. The first formula I will say basically as when your beta value is 1. Okay, first of all, I'll just give a generic definition of F score or F beta. Here you are basically going to consider 1 plus beta square precision multiplied by recall divided by beta square multiplied by precision plus recall. Whenever your both false positive and false negative are important, we select beta as 1. So if I select beta as 1, it becomes 1 plus 4 precision multiplied by recall. Then you have precision plus recall. So here, 1 plus 1. So this becomes 2 multiplied by precision into recall divided by precision plus recall. So here you have, this is basically called as harmonic mean. Harmonic mean. Probably you have seen this kind of equation where you have written 2xy divided by x plus y. Same type you are able to see this. This is called as harmonic mean. Here the focus is on both false positive and false negative. Let's say that your false positive is more important than false negative. At that point of time, you will try to decrease your beta value. Let's say that I'm decreasing my beta value to 0.5. Then what will happen? 1 plus 0.5 whole square. And then you have P multiplied by R, precision and recall. And here also you have 0.25 P plus R. Now in this particular scenario, I am decreasing my beta. Decreasing the beta basically means that you are providing more importance to false positive than false negative. And finally, you'll be able to see that if I consider beta value as, let me just say my notes. If I consider beta value as 2, that basically means you are giving more importance to false negative than false positive. So with this specific case, you can come up to a conclusion what value you basically want to use. Now, whenever I use beta is equal to 1, it becomes F1 score. If I use beta as 0.5, then this basically becomes F0.5 score. And this becomes your F2 score. So based on which is important, okay, which is important, whether your precision or false positive or false negative is important, you can consider those things. F score will have different values. If you are using beta is equal to 1, that basically means you are giving importance to both precision and recall. If your false positive is more important, then at that point of time you reduce your beta value. If false negative is greater than false positive, then your beta value is increasing. Beta is a deciding parameter to decide your F1 score or F2 score or F point score. Now, first thing first, what is the agenda of today's session? First of all, we will complete practicals for all the algorithms that we have discussed. These all algorithms that we have discussed, we will cover the practicals. Probably we will be doing hyperparameter tuning, everything. The second thing, and again, here we are going to take just simple examples. So yes, so today's session, as said, practicals with simple examples where I'll probably discuss about all the hyperparameter tuning. Then the second one, the second algorithm that I'm going to discuss about is something called as naive Bayes. This is a classification algorithm, so we are going to understand the intuition. And the third one that we are going to probably discuss is KNN algorithm. So KNN algorithms is definitely there. So this are today's plan. I know I've written very less, but this much maths is involved in naive Bayes, right? We'll understand the probability theorem again over there. There is something called as Bayes theorem we'll try to understand, and then we'll try to solve a problem on that. So let's proceed and let's enjoy today's session. How do we enjoy? First of all, we enjoy by creating a practical problem. So I am actually opening a notebook file in front of you. So here we will try to solve it with the help of linear regression, Lasso, and try to solve some problems. Let's see how much we will be able to solve it. But again, the aim is that we learn in a better way, okay, so that everybody understands some basic things, okay. So first of all, as usual, everybody open your Jupyter notebook file. The first algorithm that I'm going to discuss about is something called as sklearn linear regression. So everybody, I hope everybody knows about this sklearn. Let's see what all things are basically there in this. We will be using fit intercept, everything as such. But here the main aim is to find out the coefficients, which is basically indicated by theta 0, theta 1 and all. The first thing, we'll start with linear regression, and then we will go ahead and discuss with Ridge and Lasso. I'm just going to make this as markdown. How many different libraries of for linear regression? You can do with stats, you can do with SciPy, you can do with many things. Okay. So first thing first, let's first of all, we require a data set. So for the data set, what we are going to do is that we are going to basically take up some smaller data. Just let me do this. So for this, we are going to take the house pricing data set. So we are going to solve house pricing data set problem, a simple data set which is already present in sklearn only. Now in order to import the data set, I will write a line of code which is like from sklearn dot datasets import load underscore Boston. So we have some Boston house pricing data set. So I'm just going to execute this. I'm also going to make a lot of cells so that I don't have to again go ahead and create all the cells again. Some basic libraries that I probably want is import numpy as np, import pandas as pd, okay, import cbon as sns, and then I will also import matplotlib dot pyplot as plt, and then percentile matplotlib dot inline, and I will try to execute this. See this, my typing speed has become a little bit faster by executing these queries again and again. And let's go ahead. So I have imported all the necessary libraries that is required, which will be more than sufficient for you all to start with. Now in order to load this particular data set, I will just use this library called as load underscore Boston, and I'm going to just initialize this. So if you press shift tab, you will be able to see that load and return the Boston house prices data set. It is a regression problem, it is saying. And then probably I'm just going to execute it. Now once I execute it, I will go and probably see the type of df. So it is basically saying sklearn.utils.bunch. Now if I go and probably execute df, you'll be able to see that this will be in the form of key value pairs. Okay, like target is here, data is here. Okay, so data is here, target is here, and probably you'll be able to find out feature names is here. So we definitely require feature names, we require our target value and our data value. So we really need to combine this specific thing in a proper way in the form of a data frame so that you will be able to see. So what I'm actually going to do over here, I'm just going to say pd dot data frame. I'll convert this entirely into a data frame, and I will say df dot data. See, this is a key value pair, right? So df dot data is basically giving me all the features value. So if I write df dot data and just execute it, you will be able to see that I will be able to get my entire data set in this way. My entire data set in this way. This is my feature 1, feature 2, feature 3, feature 4. This feature 12, I have 12 features over here, and based on that I have that specific value. Now the next thing that I am going to do, probably I should also be able to add the target feature name over here. So what I will do, I will just convert this into df, and then I will also say df dot columns, and I'll set it to df dot target. Okay, and let me change this to data set. So I'm going to change this to data set, and I'm going to say dataset dot columns is equal to df dot target. So if I execute this, and now if I probably print my dataset dot head, you will be able to see this specific thing. Okay, it is an error. Let's see, expected axis has 13 element, new values has 506. So target, okay, I should not use target over here. Instead I had a column which is called as feature names. Like if I go and probably see df over here, you'll be able to see there is one thing which is called as feature names. So I'm going to use df dot feature names over here. So here it is, df dot feature names. I'm just going to paste it over here. And now if I go and write, here you can see print df dataset dot head. If I go and execute without print, you will be able to see my entire dataset. So these are my features with respect to different things. And this is basically a house pricing data set. So initially I have these features: CRIM, ZN, Indus, CHAS, NOx, RM, age, distance, radius, tax, PT ratio, B, L stat. So I have my entire data set over here. The same data set I have basically put it over here. Now here also you will be able to see what all this feature basically means. This is showing weighted distance to 5 Boston Employment Center. RAD basically means index of accessibility to radial highway. Tax basically means full value property tax rate this much. PT rate basically means pupil teacher ratio. I don't know what the hell it means, but it's fine. We have some kind of data over here properly in front of you. So these are my independent features. What are this? These all are my independent features. If you want the features detail, here you can see it, right? Everything. What is CRIM? This basically means per capita crime rate by town, which is important. ZN, it is proportional of residential land zoned for lots over 25,000 square feet. So this is my DF. I did not do much. I'm just using data frame, df.data, column features name. I'm getting this value. Very much simple. Now let's go a little bit slowly so that many people will be able to also understand. Now this is my dataset.head. Now the thing is that I obviously have taken all these particular values, but this is my independent feature. I still have my dependent feature. So what I'm actually going to do, I will create a new feature which is like dataset of price. I'll create my feature name price of the house. And what I will assign this particular value, this value will be assigned with this target value. This target value is basically the the price of the houses, right? It is again in the form of array. So I'm going to take this and put it as a dependent feature. So here you'll be able to see that my price will be my dependent feature. So here I'll basically write df.target. So once I execute it, and now if I probably go and see my dataset.head, you will be able to see features over here, and one more feature is getting added, that is price. Now this price may be, the units may be in millions. Somewhere target should be here or there. It should be probably in millions, or I cannot see it, but it should be somewhere here. It should have definitely said that it is probably in millions, or okay, but that is not a problem, I think, but mostly it will be in millions. Somewhere I think it should be here. Okay, I cannot see it, but probably if I put more time, I'll be able to understand it. Okay. So over here, what is the thing, main thing? These all are my independent features, and this is my dependent feature, right? So if I'm trying to solve linear regression, I have to divide my independent and dependent features properly. Now let's go to the next step, that is dividing the data set, dividing the, oh my god, dividing the data set into train into, first of all, I'll try to divide into independent and dependent features. So I want my entire features dataset divided into independent and dependent features. X I will be using as my independent feature. So I will write dataset dot, I will use an ilock which is present in data frames, and understand from which feature to which feature I will be taking as my independent feature to this feature till lstat. So the best way, that basically means that I just need to skip the last feature. In order to skip the last feature, what I'm actually going to do, from all the columns, I will just skip the last column. So this is how you basically do an indexing with respect to just skipping the last feature, and this will basically be my independent features. And here I will basically say y is equal to dataset dot ilock, and here I just want the last feature. So I will write colon all the records I want, and see the first term that we are probably writing over here, this basically specifies with respect to records. Here this specifies with respect to columns. From all the columns I'm taking the last column. Here I will just take the last column, and this will basically be my dependent features. So here I have basically executed. Now if you can go and probably see x.head, here you'll be able to find all my independent features. In y.head you'll be able to find a dependent feature. Now let's go to the first algorithm, that is called as linear regression. Always remember, whenever I definitely start with linear regression, I'll definitely not go directly with linear regression. Instead, what I will do is that I'll try to go with ridge regression and lasso regression, because there are a lot of options with respect to hyperparameter tuning. But I will just show you how linear regression is done. So basically, you really need to use a lot of libraries, okay, over here, and based on these libraries will try to install, okay. And what are these libraries? These are basically the linear regression library. So here I'm basically going to use two specific thing. One is linear regression library. So I will just use from sklearn dot linear underscore model import linear regression. Do you need to remember this? The answer is no, because I also do the Google and I try to find out where in sklearn it is present. Okay, so here is my linear regression. So I will try to initialize linear reg is equal to initialize with linear regression. And then here what I'm actually going to do, I'm going to basically apply something called as cross validation. The cross validation is very much important, because in cross validation we divide our train and test data in such a way that every combination of the train and test data is basically taken by the model, and whosever accuracy is better, that all entire thing is basically combined. So here what I'm going to do, I'm going to say mean square error is equal to, here I will import one more library, let's say from sklearn dot model selection. I'm going to import cross val score. So cross validation score basically means it is going to do a lot of train and test split. It's something like this. One example I will show it to you here only. So what does cross validation basically do? Okay, so in cross validation what happens, what you do, suppose this is your entire data set. Suppose this is 100 records. If you do 5 cross validation, then in the first, this will be your test data and remaining all will be your training data. If in the second cross validation, this will be your test data and remaining all will be your test training data. Like this 5 times you will be doing cross validation by taking the different combination of train and test. But I'm not going to discuss much about it in the future. If you want a separate session, I will include that in one of the session itself. So this was basically the plan with respect to cross validation or cross val score. So here I'm going to basically take cross val score, and here the first parameter that I give is my model. So linear regression is my model, and here I will take x and y. I'm not doing a train test splits specifically over here. I'm giving the entire x and y, and probably based on that I'm going to do a cross validation over here. You can also do train test split initially and then just give the x train and y train over here to do the cross validation. It is up to you, but the best practices will be that first you do the train test split and then only give the train data over here to do the cross validation. I'm just going to use scoring is equal to, you can use mean squared error, negative mean squared error. Let's say that I'm going to use negative mean squared error. Again, where do you find all these things? You will be able to see in the sklearn page of linear cross val score. And then finally in the cross val score, you give cross validation value as 5, 10, whatever you want. So after this, what I'm actually going to do, I'm just going to basically from this, how many scores I will get? The mean squared error will be 5 since I'm doing 5 cross validation. If you don't believe me, just see over here, print MSC. So here you'll be able to see 5 different values, 1, 2, 3, 4, 5, right? 5 different mean values because we are doing five cross validation. So here what I'm going to write, I'm just going to say np.mean. I want to take the average of all the 5. So here will basically be my mean underscore MSC. Okay, and then probably I will print my mean underscore MSC. So this will be my average score with respect to this. The negative value is there because we have used negative mean squared error. But if you just consider mean squared error, then it is only 37.13. Okay, so this I have actually shown you how to do cross validation. See, with respect to linear regression, you can't modify much with the parameter. So that is the reason why specifically in order to overcome overfitting and do the feature selection, we use ridge and lasso regression. So here I will show you how to do ridge regression now. Now, in order to do the prediction, all you have to do is that just go over here, take the model. Okay, what is the model? Linear underscore reg, and just say dot predict. So here you can see you will be getting a function called as dot predict, and give the test value whatever you want to predict. Automatically the prediction will be done. So I'm just going to remove this and focus on ridge regression right now, because I want to show how hyperparameter tuning is done in ridge regression. So for ridge regression, the simple thing is that I'll be using 2 different libraries from sklearn dot linear underscore model. I'm going to import ridge. So for the ridge, it is also present in linear underscore model. For doing the hyperparameter tuning, I will be using from sklearn dot model underscore selection, and then I'm going to import grid search CV. So these are the 2 libraries that I'm actually going to use. Grid search CV will be able to help you out with I will be able to help you out with hyperparameter tuning. and then probably you'll be able to do that. Difference between MSE and negative MSE, not big thing, guys. If you use MSE here, mean squared error, you'll be getting 37. I've just used negation of MSE. It's okay. Anything is fine. You can go with MSE also. Mean squared error. There is also another scoring area which focuses on root mean square error. Okay, so there are different things which you can basically focus on. Okay, now in order to give you this specific good value, I'm actually going to do hyperparameter tuning. Now let's go ahead with Regressor CV. So here what I'm going to do, again I'm going to basically define my model, which will be Ridge. Okay, so this is what I have actually imported. Now let me open the Ridge sklearn. So sklearn Ridge. We need to understand what all parameters are basically used. Do you remember this alpha value, guys? Do you remember this alpha value? Why do we use alpha? I told you, now alpha multiplied by slope square. If you remember, in Ridge, we specifically use this, right? Ridge and Lasso regression, alpha. So this is the alpha. This is probably the best parameter we can just perform hyperparameter tuning. The next parameter that we can probably perform is basically this max iteration. Okay, max iteration basically means how many number of how many number of times we may probably change the theta1 value to get the right value. So we can do this. So what I'm actually going to do, I'm going to select some alpha values. I'm going to play with this. Apart from that, if I want, I can also play with the other parameters which are like kind of probably you can also play with the iteration parameter. It is up to you. Try whichever parameter you want to change. You can go ahead and change it. Now let me show you how do we write this and how do we make sure that the specific thing is done. Now before doing grid search CV, let me do one thing. I will define my parameters. Okay, so here is my ridge. Now what I'm going to do, I'm going to say parameters, and in this parameter, two important value that I'm probably going to take is this one, that is my C value, and I will try to define this in the form of dictionaries. So here the C value that not C, just a second guys, my mistake, it is not C, it is alpha. Let's see. So how do I define my alpha value? We'll try to see. So here the parameters will be alpha. C is basically for logistic regression. I'll show you. So the alpha value, I will just mention some values like 1 e to the power of minus 15. That basically means 0.000000000000001. Similarly, I can write 1 e to the power of minus 10. That again means 0.000000000 10 times 0 1. I'm just making fun. Okay, so that you will also get entertained. 1 e to the power of minus 8. Okay, similarly I can write 1 e to the power of minus 3. From this particular value, now I'm increasing this value. See, 1 e to the power of minus 2, and then probably I can have 1 5 10 20, something like this. So I'm going to play with all these particular parameters for right now, because in grid search CV what they do is that they take all the combination of this alpha value, and wherever your model performs well, it is going to take that specific parameter and it is going to give you that, okay, this is the best fit parameter that is got selected. So here I have got all these things. Now what I'm going to do, I'm going to basically apply the grid search CV. So here I have ridge underscore regressor. So I'm going to use grid search CV, and here I'm basically going to take the parameters ridge. Okay, ridge is my first model, and then I will take up all these params that I have actually defined. See, in grid search CV, if I press shift tab, I have to first of all execute this, then only it will be able to press shift tab. So here if I press shift tab, here you will be able to see estimator and parameter grid is my second parameter, then scoring, and then all the other parameters. So here the first thing that goes is your model, then your parameters what you are actually playing, then the third parameter is basically your scoring, and again here I'm going to use negative mean squared error. Some people are saying that mean squared error is not present, so that is the reason why negative mean squared error is done. Why it may not be present? Because they try to always create a generic library. Probably this kind of scoring parameter may also get used in other algorithms, so that is the reason they may not have created. But if you want to deep dive into it, Google, गूगल करो, पता लगाओ. Then what is ridge regressor dot fit on x comma y? Again, I'm telling you, you can first of all do train test split on x and y, and then probably only do this on x train and y train. Parameter is not, oh sorry, okay, I get this. Okay, parameter is not, and why it is not an, oh yeah, it has become a list. I'm going to make this as dictionary. Right now I'm fully focused on implementing things. If I get an error, I'll definitely make sure that it will get fixed anyhow. If I get an error, I will not say, oh Krish, why this error came, why this error came. I'll not get worried. I'll get the error down only. You cannot give this as this one. Okay, so try to understand. Okay, so this is your grid search CV. I've also done the fit, and let's go and select the best parameter. So what I can do, I will write print ridge underscore regressor dot params. Sorry, there will be a parameter called as best params. I'm going to print this, and I'm going to print ridge underscore regressor dot best score. So these are all the values that are got selected. One is alpha is equal to 20, and the best score is minus 32. So initially I got minus 37, but because of ridge regression, you can see that our negative mean squared error has definitely become better. There is a minus sign, don't worry, but from 37 it has come to 32. Cross validation, guys, over here inside grid search CV also, when it is probably taking the entire combination, over there the CV value cross validation also we can use. So probably if I am probably considering all these things, many people has a question, Krish, is this minus value increased? That basically means you cannot use ridge regression. You're right. In this particular case, ridge regression is not helping you out. So guys, let me again write it down. Everybody, don't worry. Previous I got minus 32. Right now I'm getting minus 37. Right? Sorry, previously I got what? Minus 37. Minus 37. Now I got minus 32. So here you can see this I got it from linear regression. This I got it from what? Ridge. Which one should I select? I should select this model only because it is performing well than this. But again, understand ridge also tries to reduce the overfitting. So probably in this particular scenario, we cannot use ridge because the performance is becoming more bad. So what I will do, I will go and try with lasso regression now. I'll copy and paste the same thing. So linear model, import lasso. Then this will basically be my lasso. Let's see with lasso whether it will increase or not. Let's see. This is my parameter that got selected. Now let me write lasso regressor dot best params. So this is alpha is equal to 1 is got selected over here. I'm just going to print it. Okay. And then I'm going to print with lasso regression dot score will be the best. So here I'm actually getting minus 35. Minus 35. Here I'm actually getting minus 32. So minus 35. Still I will focus on linear regression. Now see what will happen. If I add more parameters, see what will happen. So now I'm going to take alpha different values. See this. I'm just going to remove this and probably add alpha value in this way. See here I have added more values 1, 5, 10, 20, 30, 35, 40, 45, 100. Okay. Let's see whether our performance will increase or not. So here, first of all, let me remove from here in ridge. Just take it down, guys. I'm adding more parameters like this. Just take it down. Yeah, CV is equal to 5. Nobody. Okay, you're not able to see it. CV is equal to 5. Now here it is. What you can basically focus on. So here you can see I have added some values like this. You can also add and just try to execute. And now if I go and probably see, this is my. See, first I have tried for ridge. I'm getting minus 29. Do you see after adding more parameters what happened in ridge? After adding more parameters what happened in ridge? You can see over here minus 29. And the alpha value that is got selected is 100. If you want, try with cross validation 10 and just try to execute now. So these all are some hyperparameters that we will definitely play with. Here you can see minus 29. So here you can see minus 29. You can also increase the cross validation value. over here also, and probably execute it. But with Lasso, I don't know whether it is improving or not. It is coming to minus 34. You just have to play with these parameters. As now for a bigger problem statement, the thing is not limited to here, right? We try to take multiples and many parameters, and try to do these things. It is up to you. We play with multiple parameters. Whichever gives us the best result, we are basically taking it. It's okay. Error is increased. I know that. No, error is increasing. Definitely error is increasing. Even though by trying with different parameters. But about most of the scenario, see here, I got minus 37. Probably what I can actually do is that try to get better one with respect to this. Now the best way, what I can also do is that I can basically take up train and test split also and probably do these things. Let's see one example. So how do we do train and test? From sklearn dot, I think model selection, import train test split. Okay, it's okay guys, you may get a different value. Okay, let's do one thing. Okay, let's make your problem statement little bit simpler. Now what I'm going to do, just tell me in train test split what we need to do. So I'm going to take the same code, I'm going to paste it over here. Or let me do one thing, let me insert a cell below and let me do it for train test split. So in train test split, what we can do, so I'm just going to take the syntax, paste it over here. Let's say that I'm taking X train, Y train, and then I'm using train test split with 33%. Now if I execute with respect to X train and Y train, so here is my, you can see this, I've written this code from sklearn.model selection, train test split. Random state can be anything, whatever you write, it is fine. Then you basically give X and Y with test sizes 0.33. This is basically saying that the test will have 33% and the train data will be 77%. So this is what I'm actually getting with respect to X train and Y train. Here, what I'm going to do, I'm going to basically take X train comma Y train. And now if I go and probably see this, here you can see minus 25. Understand this value should go towards 0. If it is going towards 0, that basically means the performance is better. Now similarly, I do it for Ridge. In Ridge, what I'm actually going to do, here I'm going to write X train and Y train. And if I go and probably select the best scores and this, here you will be able to see I'm getting, how much I'm getting? Minus 25.47. Okay, here I'm getting 25.18, here 25.47. That basically means now still the improvement is little bit bad because here we are not going towards 0. So the next part, again here also you can basically do it for X train and Y train. X train and Y train. So here you have this one and let's go and execute this. So here you can see minus 25.47. Now what you can also do is that you can use this Lasso regressor dot predict and you can basically predict with respect to X test. So this is your Y test value. Suppose let's say that this is my Y pred, Y underscore pred. Then what I can do from sklearn, I will be using R square and adjusted R square. If you remember sklearn R square. So this is my R2 score. So where it is present in sklearn.metrics. So I'm going to write from sklearn import, let's say I'm saying from sklearn.metrics import R square, R2 score. Now what I'm going to do over here, I'm basically going to say my R2 score, which is my variable. I'll say this is nothing but R2 score. Here I'm just going to give my Y pred comma Y underscore test. So if I go and probably see the output, here I will be able to see print R2 score. This is all I have discussed, guys. See, there is also adjusted rand score is there. Where is R2? R2 score 1, adjusted R square. Okay, R2 score is there, but adjusted R square should be here somewhere in some manner. So this is how your output looks like with respect to by using this Lasso regressor. Okay, which is very good. Okay, it should be, I told it should be near 100%. Right now I'm getting 67%. If I want to try with Ridge, you can also try that. So you can say Ridge regressor dot predict, and here you can see 68%. Then you can also try linear regressor and predict. What is the error saying the linear regression is not fitted yet? Why it is not fitted? Why it is not fitted? Let's say that I have fitted here linear regressor dot fit on X train and Y train. X train and comma Y train. So I'm just going to fit it. Now if I go and probably try to do the calculation, so if I go and see my R2 score, it is also coming somewhere around 68%, 67%. Now, since this is just a linear regression, you won't be able to get 100% because you are drawing a straight line, right? So for that, you basically have to use other algorithms like Xgboost and all, naive Bayes. So many algorithms are there. It's okay. See, you give Y test over here, Y pred over here, both are same, right? They're comparing. Bhai, see, at one limit you can increase the performance. After that, you cannot. See, again, I'm telling you, in linear regression, what we do, these are my points, right? I will be only able to create one best fit line. I cannot create a curve line right over here. So obviously my accuracy will be only limited. Let's go and do it logistic practical quickly. And here in logistic also we can do grid search CV. Now what I'm actually going to do, first of all, let's go ahead with the data set. So I will quickly implement logistic. So from sklearn.linear_model, I'm going to import logistic regression. So I'm going to use logistic regression, and apart from that, we know that let's take a new data set, because for logistic we need to solve using classification problem. So this is basically my logistic regression. I'll take one data set. So from sklearn.datasets import, we'll take a data set which is like breast cancer data set. So that is also present in sklearn. With respect to the breast cancer data set, I'm just going to use this. See, load breast cancer data set. I'm loading it, and all the independent features are in data, and my columns are feature names. The same thing like how we did previously. Okay, so this will basically be my complete independent feature. So if I go and probably see this x.head, here you will be able to see that based on this input features or independent feature, we need to determine whether the person is having cancer or not. These are some of the features over here, and this is like many features are actually present. So next thing, that was my independent feature. Now I'll take my dependent feature. Dependent feature will already present in df.target. Okay, this particular data set that we have taken in df. In df.target, we will basically have all our dependent features. These are my independent features. So what I'm actually going to do, I'm going to create y, and I'm going to say pd dot data frame, and here I'm going to say df.target target, and this column name should be target, right? So this will be my column name. And now if I go and see my y is basically having zeros and 1 in the target feature. Now the next thing that we are going to do is that apply the, first of all, we need to check whether this data set is this particular y column is balanced or imbalanced. Okay, in order to do that, I will just write f target. If the data set is imbalanced, definitely we need to work on that and try to perform upsampling. So if I write y target dot value underscore counts, if I execute this, so here you will be able to see that value underscore counts will basically give that how many number of ones are and how many number of zeros are. So now total number of ones are 357 and total number of zeros are 212. So is this a imbalanced data set? Probably this is a balanced data set. So here I'm actually going to now do train test split. Train test split I will try to do. Again, train test split, how do we do? We can quickly copy the same thing entirely. I'll copy this entirely over here, and then I will get my x and y. So here is my x train, x test, y train, y test. So train test split, obviously I'll be doing it. Now in logistic regression, if I go and search for logistic regression sklearn, I will be able to see this, what all parameters are there. This is basically the L1 norm or L2 norm or L1 regularization or L2 regularization with respect to whatever things we have discussed in logistic. And then the C value, these two parameter values are very much important. If I probably show you over here, the penalty, what kind of penalty, whether you want to add an L2 penalty, L1 penalty, you can use L2 or L1. The next thing is C. This is nothing but inverse of regularization strength. This basically says 1 by lambda, something like that. This parameter is also very much important, guys, class weight. Suppose if your data set is not balanced, at that point of time you can apply weights to your classes. If probably your data set is balanced, you can directly use class weight is equal to balanced. Other than that, you can use other weights which you basically want. So this is specifically some of this, right? No, this is not Ridge or Lasso. Okay, this is logistic. In logistic also you have L1 norm and L2 norms. Understand, probably I missed that particular part in the theory, but here also you have an L2 penalty norm and L1 penalty norm. I probably did not teach you in theory, because if you look, see, logistic regression can be learned by two different ways. One is through probabilistic method and one is through geometric method. If you go and probably see my video that is present with respect to logistic regression right now in my YouTube channel, there I have explained you about this L1 and L2 norms also over there. So in this also it is basically present. It is a kind of penalty, again, just for using for this kind of classification problem. So what I am actually going to do, let's go and play with the parameters that I am looking at. So I will play with two parameters. One is params C value. Here I am defining 1, 5, 10, 20, anything that you can define. One set of values you can define. And there was one more parameter which is called as max iteration. This is specifically for Regressor CV. Okay, that I am specifically going to apply. So I will just try to execute this. This will be my params. Now I'm going to quickly define my model 1, which will be my logistic regression model. So my logistic regression here, by default, one value I'll give for C and max iter. Let's say I'm giving this value. Later on, what I will do for this model, I'll apply it to Regressor CV. So I'm just going to say Regressor CV, and I'm going to apply it for model 1. Param grid is equal to params, this parameter that I'm specifically trying to apply. Since this is a classification problem and I am not pretty sure that whether true positive is important or true negative is important, I'm going to use F1 scoring. Okay, F1 scoring is basically again the parametric term which we discussed yesterday, which is nothing but performance metrics. And then I'm going to use CV is equal to 5. So this will be entirely my model with respect to Regressor CV, and I'll be executing this. Then I will do model.fit on my Xtrain and Ytrain data. So once I execute it, here you can see all the output along with warnings. A lot of warnings will be coming, I don't know, because this many parameters are there. And finally, you can see that this has got selected. Now, if you really want to find out what is your best param score, model dot best params. So here you can see max iteration as 150, and what you can actually do with respect to your best score, model dot best score is 95 percentage, but still we want to test it with test data. So can we do it? Yes, we can definitely do it. I'll say model dot score, or I'll say model dot predict on my X test data, and this will basically be my Y pred. So this will be my Y pred, all the Y prediction that I'm actually getting. So if you go and see Y pred, so these are my ones and zeros with respect to the Y prediction. And finally, after getting the prediction values, I can apply confusion matrix. I hope I have taught you about confusion matrix. So from sklearn.confusion matrix, sklearn.metrics, I'm going to import confusion matrix, classification report, and the next thing that I would like to do is this two. I will try to import confusion matrix and classification report. Now if you want to see the confusion matrix with respect to your, I can just write y underscore pred or y underscore test, whatever you want, go ahead with it. And this is basically my confusion matrix. If I put this forward, no difference will be there, only this thing will be moving. That also I showed you, 63, 118, 3 and 4. Now finally, if I want a accuracy score, I can also import accuracy score over here. So here you can see accuracy score is imported. I can also find out my accuracy score, which is the total accuracy with respect to this. We can give y test and y underscore pred, which we have discussed yesterday. This is giving 96%. If you want detailed precision recall all the score, then at that point of time I can use this classification report, and here I can give y test and y pred. Here is what I'm actually getting. So here you can see with respect to F1 score, precision recall, since this is a balanced data set, obviously the performance will be best. Yes, you can also use ROC. See, I'll also show you how to use ROC, and probably you'll be able to see this. You have to probably calculate false positive rate, true positive rate, but don't worry about ROC. I will first of all explain you the theoretical part. Now let's go ahead and discuss about naive Bayes. Naive Bayes is an important algorithm. So here I'm just going to go ahead. So now let's go ahead and discuss about naive Bayes, and here we are going to discuss about the intuition. So naive Bayes is another amazing algorithm which is specifically used for classification. and this specifically works on something called as Bayes theorem. Now what exactly is Bayes theorem? First of all, we need to understand about Bayes theorem. Let's say that, guys, I have Bayes theorem. Let's say that I have an experiment which is called as rolling a dice. Now in rolling a dice, how many number of elements I have? So if I say what is the probability of 1, then obviously you'll be saying 1 by 6. If I say probability of 2, then also here you'll say 1 by 6. If I say probability of 3, then I will definitely say it is 1 by 6. So here you know that this kind of events are basically called as independent events. Now rolling a dice, why it is called as an independent event? Because getting 1 or 2 in every experiment, 1 is not dependent on 2, 2 is not dependent on 3. So they are all independent. That is the reason why we specifically say is an independent event. But if I take an example of dependent events, let's consider that I have a bag of marbles, okay? In this marble, I basically have 3 red marbles and I have 2 green marbles. Now tell me, what is the probability of, suppose I have an event, in the first event I take out a red marble. So what is the probability of taking out a red marble? So here you can definitely say that it is 3 by 5. Okay, so this is my first event. Now in the second event, let's say that in this you have taken out the red marble. Now what is the second time again you are taking out the second red marble, or forget about second red marble. Now you want to take out the green marble. Now what is the probability with respect to taking out a green marble? So here you will be definitely saying that, okay, one red marble has been removed, then the total number of marbles that are left are 4. So here you can definitely write that probability of getting a green marble is nothing but 2 by 4, which is nothing but 1 by 2. So here what is happening? First element you took out, first marble that you took out, first event from the first event you took out red marble. From the second event you took out green marble. These two are dependent events because the number of marbles are getting reduced as you take out from them. So if I tell you what is the probability of taking out a red marble and then a green marble. So it's the formula will be very much simple, right? Which we have already discussed in stats. It is nothing but probability of red multiplied by probability of green given red. So this specific thing is called as conditional probability. Here understand what is happening. Probability of green marble given the red marble event has occurred. Here both the events are independent. Now let me write it down very nicely. So I can write probability of A and B is equal to probability of A multiplied by probability of B divided by probability of A. Let's go and derive something. Can I write probability of A and B is equal to probability of B and A? So our answer is yes. We can definitely say. If you go and do the calculation, you'll be able to get the answer. You should not say no. Now, what is the formula for probability of A and B? So here you can basically write probability of A multiplied by probability of B given A. If I take out probability of green, what is probability of green in this particular case? 2 by 5. What is probability of red? 3 by 4. For right now, let's consider this. Now this part I can definitely write as probability of B multiplied by probability of B, probability of B, probability of B, and this will be probability of A given B. So I can definitely write this much with respect to all this information. Now can I derive probability of A is equal to probability of B multiplied by probability of A divided by B, means probability of A given B divided by probability of, I'll write this as probability of B given A divided by probability of A. And this is specifically called as Bayes theorem. And this is the crux behind naive Bayes. Understand, this is the crux behind the Bayes theorem. Now, let's go ahead and let's discuss about how we are using this to solve. Let's take some examples and probably make you understand. Let's say that I have some features like x1, x2, x3, x4, x5, like this till xn, and I have my output y. So these are my independent features. These all are my independent features. So here I'm going to write independent features, and this is my output feature, which is also my dependent feature. Now what is happening? If I say probability of B or A, what does this basically mean? I need to really find what is the probability of Y, and you know that, right, guys, I will have some values over here, and basically I will have some output value over here. So based on this input values, I need to predict what is the output. Initially on a training data set, I will have your input and then your output. Initially my model will get trained on this. Now let's consider what this entire terminology is I will try to write in terms of this equation. So I will say probability of y given x1, x2, x3 up till xn. Then this equation will become probability of y. See, probability of y given x1, x2, x3, xn. This a is nothing but x1, x2, x3, xn. And I am trying to find out what is the probability of y. And then I will write probability of b. B is nothing but y. But before that, what I will write? Probability of a divided by b. Right? A given b. Or probability of b. Probability of b is nothing but y multiplied by probability of a given b. Probability of a given b basically means probability of x1, x2, xn given b. B is given, right? So I am able to find this entire value. Now just a second, I made some mistakes, I guess. Now it is correct. Sorry, I just missed one term. That is this given y. This is how it will become. And this will be equal to probability of a. That is x1, x2 like this up to xn. So probability of y multiplied by probability of a given y. Now if I try to expand this, then this will basically become something like this. See, probability of y multiplied by probability of x1 given given y, given y multiplied by probability of x2 given y, probability of x3 given y, and like this it will be probability of xn given y. So this will also be y1, y2, y3, yn. This I can expand it like this, and then this will basically become probability of x1 multiplied by probability of x2 multiplied by probability of x3 like this up to probability of xn. So this is with respect to all the probability. Y will be different. See here, for this particular record y will be different, for this y will be different, for this y will be different. But y output, it may be yes or no, right? It may be yes or no. Okay, I'll solve a problem. It will make everything understand. And this will probably be probability of y. It can be binary, multi-class, whatever things you want. I'll solve a problem in front of you. Now let's say that I have my y as, let's say that I have a lot of features, x1, x2, x3, x4. With respect to this, let's say in my one of my data set, I have this many x1s, this many features, and this is my y. So these are my feature number and this is my y. Let's say that in y I have yes or no. So how I will probably write? We really need to understand this, okay? I will basically say, what is the probability of y is equal to yes given this x of i's. This is my first record of x of i's. This is my second record of x of i's. So I may write like this. What is the probability of y being yes if x of I is given to you? X of I basically means x1, x2, x3, x4. So here you'll obviously write what kind of equation? You'll basically say probability of yes multiplied by probability of yes multiplied by probability of x of 1 given yes multiplied by probability of x2 given yes, probability of x3 given yes, and probability of x4 given yes, divided by probability of x1 multiplied by probability of x2 multiplied by probability of x3 multiplied by probability of x4. Y is fixed. It may be yes or it may be no. But with respect to different records, this value may change. Similarly, if I write probability of y is equal to no given x of I, what it will be? Then it will be probability of no multiplied by probability of x1 given no, then probability of x2 given no, probability of x3 given no, and probability of x4 given no. So here, because any input that I give, any input x of I that I give, I may either get yes or no. So I need to find both the probability. So probability of x1 multiplied by probability of x2 multiplied by probability of x3 multiplied by probability of x4. See, with respect to any x of I, the output can be yes or no. And I really need to find out the probability. So both the formula is written over here. What is the probability of with respect to yes and what is the probability with respect to no? Now in this case, one common thing you see that this denominator is fixed. This is definitely fixed. It is fixed. It is not going to change for both of them. And I can consider that this is a constant. So what I can do? I can definitely ignore. So here I can definitely ignore these things. Ignore this also, ignore this also. Because see, this is constant. So I don't want to consider this. In the next time, I'll just use this specific formula to calculate the probability. Now let's say that if my first probability for a specific data set, yes, of x of I is, let's say that I'm getting as 0.13. And similarly, probability of no with respect to x of I, if I get 0.05. You know that in a binary classification, any values, if we get greater than or equal to 5, we are going to consider it as 1. And if it is less than 0.5, I'm going to consider it as 0. Now, I'm getting values like this 0.13 and 0.05. Obviously, I'm getting 0.13, 0.05. So, we do something called as normalization. It says that if I really want to find out the probability of x with x of I, if I do normalization, it is nothing but 0.13 divided by 0.13 plus 0.05, 0.72. This is nothing but 72%. And similarly, if I do for probability of no given x of I, here obviously it will say 1 minus 0.72, which will be your remaining answer, that is 0.28, which is nothing but 28%. So your final answer will be this one. This formulas you have to remember. Now we'll solve a problem. Let's solve a problem. This will be a very, very interesting problem. Let's say I have a data set which has like this feature, day. Let me just copy this data set, okay, for you all. Now, in this data set, I want to take out some information. Let's take out Outlook table. Now, based on this Outlook feature, see over here, Outlook, my day, Outlook, temperature, humidity, wind are the input features, independent features. This is my output feature. This one that you are probably seeing, play tennis, is my output feature, which is specifically a binary classification. So what I'm actually going to do, I'm basically going to take my Outlook feature, and based on this Outlook feature, I will just try to create a smaller table which will give some information. Now, based on Outlook, first of all, try to find out how many categories are there. In Outlook, one is sunny, one is overcast, and one is rain, right? 3 categories are there. So I'm going to write it down over here: sunny, overcast, and rain. So these 3 are my features with respect to sunny. With Outlook, I have 3 categories. One is sunny, one is overcast, and one is rain. Here I'm going to basically say, with respect to sunny, how many yes are there and how many no are there, and what is the probability of yes and probability of no. So I'm going to again write it over here. So this is my Outlook feature, and then I have categories. First, yes, no, sunny, overcast, rain. Yes, no, then probability of yes and probability of no. Now, the next thing that we need to find out is that with respect to sunny, how many of them are yes? See, yes we have. So when we have sunny over here, the answer is no. So I will increase the count over here, 1. Then again I have sunny, again the answer is no. So I'm going to increase the count to 2. With this sunny, this is basically no. Okay, so again I'm going to increase the count to 3. Now with sunny, how many of them are yes? 1 and 2. So I have this one and this one. So I have 2. So I'm going to say with respect to sunny, I have 2 yes. Understand, Outlook is my x1 or x1 feature. Let's consider. Now the next thing is that, let's say with respect to overcast. With overcast, how many of them are yes? So this overcast is there, yes, 1, 2, 3 and 4. So total 4 yes are there with respect to overcast. Then with respect to overcast, how many are on no? You can go and find out. It is basically 0 no's. Then with respect to rain, how many of them are yes? So here you can see with respect to 1 rain, yes, yes, no, no. So this is nothing but 3, 2. Just try to find out there are 3's, 2 or not. 1, here also 1 yes is there, right? So 3 yes, 2 no's. So the total number of yes and no's, if you count it, there are 9 yes and 5 no's. This is my total count. So if you totally count this, 9 plus 5 is 14. You will be able to compare that. There will be 9 yes and 5 no's. What is the probability of yes when sunny is given? So here you have 2 by 9. Here you have 4 by 9. Here you have 3 by 9. Now if I say what is the probability of no given sunny? Now see, Probability of yes given sunny, probability of yes given forecast, probability of yes given rain. So it is basically that I will just try to write it in a simpler manner so that you will not get confused. Okay, so this is my probability of yes and this is my probability of no. But understand, what does this basically mean? This terminology basically means probability of yes given sunny, probability of yes given overcast, probability of yes given rain. Similarly, what is probability of no? Probability of no, obviously you know that 3 by 5 is my first probability. Then you have 0 by 5 and then you have 2 by 5. Now with respect to the next feature, let's consider that I'm going to consider one more feature, and in this feature I will say let's consider temperature. Okay, let's consider temperature. Now in temperature, how many features I have or how many categories I have? I have hot, you can see hot, mild and cold. Now with respect to hot, mild, cold, here also I will be having yes, no, probability of yes and probability of no. Now try to find out with respect to hot, how many are yes. So here no is there, here also no is there. 2 no's, 1 yes, 2 yes. So 2 yes and 2 no's probably. Then similarly with respect to mild, how many are there? 1 yes, 1 no, 2 yes, 3 yes, 4 yes, 4 yes and 2 no's. Okay, so here you basically go and calculate 4 yes and 2 no's. With respect to cold, how many are there? Cool or cold, 1 yes, 1 no, 2 yes, 3 yes, 3 yes and 1 no. So here I have specifically have 3 yes and 1 no. Again the total number is 9 and 5, which will be equal to the same thing that what we have got. Now really go ahead with finding probability of yes given hot. So it will be 2 by 9 over here. Then here it will be how much? 4 by 9. Here it will be 3 by 9 again. Here what will be the probability of no given hot? So it will be 2 by 5, 2 by 5, 1 by 5. So these two tables has already been created. And finally with respect to play, the total number of plays are yes is 9, no is 5 and the answer is total 14. If I say what is the probability of yes, only yes, then it is nothing but 9 by 14. What is the probability of no? It is nothing but 5 by 14. Okay, so these two values also you require. Now let's say that you get a new data set. You need to get a new data set. Let's say you get a new test data where it says that suppose if you are having sunny and hot, tell me what is the output. So this is my problem statement. So let me write it down. So here I will write probability of yes given sunny comma hot. Then here I will write probability of yes multiplied by probability of, so here I will write probability of sunny given yes multiplied by probability of hot given yes divided by, what is it? Probability of sunny multiplied by probability of hot. ये रहा आपका इक्वेशन और ये पूरा का पूरा कैंसिल हो जाएगा. क्यों कैंसिल हो जाएगा? बिकॉज इट इज अ कांस्टेंट. Because probability of no also I will be getting the same value, 9 by 14. So probability of yes I am going to replace it with 9 by 14 multiplied by 2 by 9. Then probability of hot given yes क्या है? So I am going to get 2 by 9. So यहाँ हमारा हो जाएगा 9 9 cancel और ये हो जाएगा 2 1 7 then this is nothing but 2 by 63.031. I read this statement little bit wrong. It should be probability of sunny given yes. Now go ahead and calculate. What is probability of no given sunny and hot. So here you have probability of no multiplied by probability of sunny given no multiplied by probability of hot given no divided by probability of sunny multiplied by probability of hot. This will get cancelled. Denominator is a constant, guys. This is a constant. So what is probability of no? So probability of no is nothing but 5 by 14. So I will write over here 5 by 14 multiplied by probability of sunny given no. What is probability of sunny given no? What is probability of sunny given no is nothing but probability of sunny given no is nothing but 3 by 5. So here I am going to get 3 by 5 multiplied by Probability of Hot given no. It is nothing but 2 by 5. So 2 by 5 is here, 3 by 5 is there, 5 and 5 will get cancelled, 2 ones are 2 sevens are, and then I'm getting 3 by 35, which is nothing but calculator. If I'm actually getting 3 divided by 35, it's nothing but 0.0857. I will write it down again. Probability of yes given sunny, comma, hot, which is my independent feature, is nothing but 0.031, 0.031, and this is probability of no given sunny, comma, hot, 0.085. Now we'll try to normalize this. 0.085 plus point divided by 0.031 plus 0.085, 0.73. This is nothing but 73%. And here I can basically say 1 minus 0.73, which is my 0.27, which is nothing but 27%. If the input comes as sunny and hot, if the weather is sunny and hot, what will the person do? Whether he will play or not? The answer is no. Okay, now my next question will be that if your new data is overcast and mild, now tell me what will be the probability using Naive Bayes. Now you can add any number of features. Let's say that I will say that, okay, let's say that I will probably say we can consider humidity and wind also. You basically create this kind of table to find it out. But this will be an assignment. Just do it. Overcast and mild, if it is with respect to Naive Bayes, try to solve it. So the second algorithm that we are going to discuss about is something called as KNN algorithm. KNN algorithm is a very simple problem statement, okay, which can be used to solve both classification and regression problem. So KNN basically means K nearest neighbor. Let's first of all discuss about classification problem. Number 1, classification problem. Let's say that I have a binary classification problem which looks like this. I have 2 data points like this one, and this is another one. Suppose a new data point which comes over here. Then how do I say that whether this belongs to this category or whether it belongs to this category? If I probably create a logistic regression, I may divide a line. But in this particular scenario, how do we define or how do we come to a conclusion that whether this will belong to this category or this category? So for here, we basically use something called as K nearest neighbor. Let's say that I say that my K value is 5. So what it is going to do, it is going to basically take the 5 nearest closest point. Let's say from this you have 2 nearest closest point, and from here you have 3 nearest closest point. So here we basically see from the distance that which is my nearest point. Now in this particular case, you see that maximum number of points are from red categories. From red categories, I'm getting 3 points, and from white categories, I'm getting 2 points. Now in this particular scenario, maximum number of categories from where it is coming, we basically categorize that into that particular class just with the help of distance. Which all distance we specifically use? We use 2 distance. One is Euclidean distance and the other one is something called as Manhattan distance. So Euclidean and Manhattan distance. Now what does Euclidean distance basically say? Suppose if this is your 2 points, which is denoted by x1, y1, x2, y2. Euclidean distance, in order to calculate, we apply a formula which looks like this: x2 minus x1 whole square plus y2 minus y1 whole square. Whereas in the case of Manhattan distance, suppose these are my 2 points, then we calculate the distance in this way. We calculate the distance from here, then here. Right? This is the distance we calculate. We don't calculate the hypotenuse distance. So this is the basic difference between Euclidean and Manhattan distance. Now you may be thinking, Krish, then fine, that is for classification problem. For regression, what do we do? For regression also, it is very much simple. Suppose I have all the data points which looks like this. Now for a new data point like this, if I want to calculate, then we basically take up the nearest 5 points. Let's say my k is 5. K is a hyperparameter which we play. Now suppose let's say that k, it finds the nearest point over here, 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 here and here. So if we need to find out the point for this particular output with respect to the k is equal to 5, it will try to calculate the average of all the points. Once it calculates the average of all the points, that becomes your output. So regression and classification, that is the only difference, because this k is actually an hyperparameter. We try with k is equal to 1 to 50 and then we probably try to check the error rate. And if the error rate is less, then only we select the model. Now 2 more things with respect to k nearest neighbor. K nearest neighbor works very bad with respect to 2 things. One is outliers and one is imbalanced data set. Now if I have an outlier, Let's say I have an outlier over here. This is one of my categories like this, and this is my another category. Let's consider that I have some outliers which looks like this. Now, if I'm trying to find out the point for this, you can see that the nearest point is basically blue only and it belongs to the blue category. But because this is outlier, it will consider that the nearest neighbor is this. So then this will be basically treated in this group only. Formula for Manhattan distance, it uses modulus x2 minus x1 plus y2 minus y1. Mod x2 minus x1, y2 minus y1. This was it from my side, guys. And yes, I've also made detailed videos about whatever topics we have discussed today. You can directly go and search for that particular topic. So this is the agenda of this session. We will try to complete this all things. Again, here we are going to understand the mathematical equations and all. So today's session, we are basically going to discuss about decision tree. Okay. And in this session, we are going to basically understand what is the exact purpose of decision tree. With the help of decision tree, you are actually solving two different problems. One is regression and the other one is classification. So we'll try to understand both this particular part. We'll take a specific data set and try to solve those problems. Now coming to the decision tree, one thing you need to understand. I'll say that if age is less than 8, let's say I'm writing this condition. If age is less than or equal to 18, I'm going to say print go to college. Here I'm printing print college. And then I'll write else if age is greater than 18 and age is less than or equal to 35. I'm say print work. Then again I'll write else if age is let me put this condition little bit better. Then I will write here L if age is greater than 18 and age is less than or equal to 35. I'm going to say print work. Basically people needs to work in this age. Else I'm just going to consider print retire. So here is my if else condition over here. Now whenever we have this kind of nested if else condition, what we can do is that we can also represent this in the form of decision trees. We can actually form this in the form of decision tree. And the decision tree here, first of all, we will have a specific root node. Let's say this is my root node. Now in this root node, the first condition is less than or equal to 18. So here, obviously, I will be having two conditions saying that if it is less than or equal to 18, and one condition will be yes, one condition will be no. So if this is yes, and if this is no, right? If this condition is true, that basically means we'll go in this side. If it is true, then here we will basically have something like college. So this is your leaf node. Similarly, when I have no, okay, no in this particular case, we will go to the next condition. In this next condition, I will again create a node and I'll say that, okay, this is less than 18 and less than or equal to 35. So if this is also there, then again I'll have two conditions, which is basically yes or no. Now when I create this yes or no over here, you'll be able to see that basically means here again two condition will be there. If it is yes, I will say print work. So this will again be my leaf node. And again for no, again I will do the further splitting, which is retire. So here you can see that this entire algorithm, this entire code that I've actually written, you can see that it has got converted to this kind of trees where you are specifically able to take decisions yes or no. So can we solve a classification problem? Sorry, this is greater than 18. Again, if it is greater than 18 and less than or 35. So can we solve a regression and a classification problem? Regression and classification problem using this decision trees by creating this kind of nodes. So in short, whenever we talk about decision trees, you will be seeing that decision trees are nothing but by using this nested if else condition, we can definitely solve some specific problem statement. But here in the visualized way, we will specifically create this decision tree in the form of nodes. Now you need to understand that what type of maths we will probably use. Okay, so let's do one thing. Let's take a specific data set, which I will definitely do it over here in front of you. Okay, and we will try to solve this particular data set, and this will basically give you an idea like how we can probably solve these problems. So let me just open my snippet tool. So this is my data set that I have. Let's consider that I have this specific data set. Now this data set are pretty much important because this probably in research papers also, probably people who have come up with this algorithm, they usually take this thing. But right now this particular problem statement, if I talk about, this is a classification problem statement. Okay, but don't worry, I will also help you to explain. I'll also explain you about regression also, how decision tree regression will definitely work. So let's go ahead and let's try to understand. Suppose if I have this specific problem statement, how do we solve this? This is my output feature, play tennis, yes or no. Okay, whether the person is going to play tennis or not, yesterday or day after yesterday or whenever you want. So if I have this input features like outlook, temperature, humidity, and wind, is the person going to play tennis or not? This is what my model should predict with the help of decision tree. So how decision tree will work in this particular case? First of all, let's consider any specific feature. Let's say that outlook is my feature. So this will be my first feature, which is specifically outlook. Now just tell me how many are basically having no's and how many are basically having yes in the case of outlook. There you will be able to find out there are 9 yes. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many no's are there? 1, 2, 3, 4, 5. I think 1, 2, 3, 4, 5. So 9 yes and 5 no's. What we are going to do in this specific thing, now we have 9 yes and 5 no's, and the first node that I have actually taken is basically outlook. So outlook feature, now just try to find out, we are focusing on this specific feature. Now in this feature, how many categories I have? I have one sunny category. You can see over here, I have sunny one category. Then I have another category called as overcast. Then I have another category as rain. So I have 3 unique categories. So based on these 3 categories, I will try to create 3 nodes. So here is my one node. Here is my second node. Here is my third node. So these are my 3 categories. So this category is basically called as sunny. This category is basically called as overcast. And this category is basically called as rain. Based on these 3 categories, so I am splitting it. Now just go ahead and see in sunny, how many yes and how many no are there. How many yes with respect to sunny are there? See, in sunny, I have 2 no's. See, 1 and 2 no. One more no is there, 3 no's. So here you can see this is my 1 no. Then this is my 2 no. This is my 3 no. And yes are 2. So this one and this one. So how many total number of yes? So here you can see that there are 1, 2 yes and 3 no. Let's say that I have randomly selected one feature which is outlook. Why can't I see, it is up to it is up to the decision tree to select any of the feature. Here I have specifically taken outlook. Later on I'll explain why it can basically select, how it selects the feature. Okay, I'll talk about it, don't worry. So in the outlook, we have 2 yes. Sorry, in the case of sunny, we have 2 yes and 3 no's. Now the next thing is that let's go and see for overcast. In overcast, I have 1 yes, 2 yes, 3 yes and 4 yes. I don't have any no in overcast. So over here, my thing will be that 4 yes and 0 no's. And then finally, when we go to the rain part, see in rain, how many features are there? In rain, if you go and probably see it, how many number of yes and no's are there? Go and see in one yes in rain, 2 yes, then 1 no, then again you have 1 yes and 1 no, right? So here you can basically say that in rain, in the case of rain, if I take as an example, how many number of yes and no's are there? It will be 3 yes and 2 no's. Understanding algorithm, एक बार समझ लोगे, then everything you'll be able to understand. Now let's go ahead and try to see for sunny. Sunny definitely has 2 yes and 3 no's. This has 4 yes and 0 no's. Here you have 3 y's and 2 no's. Now if I probably take overcast, here you need to understand about two things. One is pure split and one is impure split. Now, what does pure split basically mean? Pure split basically means that, now see in this particular scenario in overcast. In overcast, I have either yes or no. So here you can see that I have 4 yes and 0 no's. So that basically means this is a pure split. Anybody tomorrow in my data set, if I just take this outlook feature, suppose in one day, in day 15, the outlook is basically overcast, then I know directly it is the person is going to play. So this part is already created and this node is called as pure node. Understand this. Why it is called as pure node? Because either you have all yes or zeros no's, or 0 yes or all no's, like that. In this particular case, I have all yes. So if I take this specific path, I know that with respect to overcast, my final decision, which is yes, it is always going to become yes. So this is what it basically says. So I don't have to split further. So from here, I will probably not split. I will definitely not split more because I don't require it, because I have, it is a pure leaf node. Okay. You can also say that this is a pure leaf node. So I'm just going to mention it again. This one I'm specifically talking about. Now let's talk about Sunny. In the case of Sunny, you have 2 yes and 3 no's. So this is obviously impure. So what we do, we take next feature, and again, how do we calculate that which feature we should take next? I'll discuss about it. Let's say that after this, I take up temperature and I start splitting again, since this is impure. Okay. And this split will happen again until we get finally a pure split. Similarly, with respect to rain, we will go ahead and take another feature and we'll keep on splitting unless and until we get a leaf node which is completely pure. I hope you understood how this exactly works. Now, two questions. Two questions is that, Krish, the first thing is that, how do we calculate this purity and how do we come to know that this is a pure split? Just by seeing, definitely I can definitely say by just seeing that how many number of yes or no's are there. Based on that, I can definitely say it is a pure split or not. So for this, we use two different things. One is entropy and the other one is something called as Gini coefficient. So we will try to understand how does entropy work and how does Gini coefficient work in decision tree, which will help us to determine whether the split is pure split or not, or whether this node is leaf node or not. Then coming to the second thing. Okay, coming to the second thing, one is with respect to purity. Second thing, your first most important question which you had asked, why did I probably select Outlook? How the features are selected. And here you have a topic which is called as information gain. And if you know this both, your problem is solved. So now let's go ahead and let's understand about entropy or Gini coefficient or information gain. Entropy or Gini coefficient, Gini coefficient, I'm saying Gini impurity also you can say over here. I'll write it as Gini impurity, not coefficient also. I'll just say it as Gini impurity. But I hope everybody is understood till here. Let's go ahead and let's discuss about the first thing, that is entropy. How does entropy work and how we are going to use the formula. So entropy, here I will just write Gini. So we are going to discuss about this both the things. Let's say that the entropy formula which is given by, I will write H of S is equal to, so H of S is equal to minus P plus, I'll talk about what is P plus log base 2 P plus minus P minus log base 2 P minus. So this is the formula, and in Gini impurity, the formula is 1 minus summation of I is equal to 1 to n P square. I'll even talk about when you should use Gini impurity, when you should not use Gini impurity, when you should use entropy. By default, the decision tree regressor or decision tree classification uses Gini impurity. Now let's take one specific example. So my example is that I have a feature 1, my root node. I have a feature 1 which is my root node. And let's say that in this root node, I have 6 yes and 3 no's. Very simple. Let's say that this has two categories. And based on these two categories, our split has happened. This is C1. Let's say in this I have 3 yes, 3 no's, and here I have 3 yes, 0 no's, and this is my second category. Always understand, if I do the summation, 3 yes and 3 yes is 6 yes. See this summation. If I do 3 plus 3 is obviously 6, 3 plus 0 is obviously 3. So this you need to understand. Based on the number of root nodes only, almost it will be same. Now let's go ahead and let's understand how do we calculate. Let's take this example. How do we calculate the entropy of this? So I have already shown you the entropy formula over here. Now let's understand the components. I will write h of s is equal to, minus sign is there. What is p plus? P plus basically means that what is the probability of yes? What is the probability of yes? This is a simple thing for you all. Out of this, what is the probability of yes out of this? So obviously how you'll write if you want to find out the probability of yes out of this. See, when I say plus, that basically means yes. When I say minus, that basically means no. So what is the probability of yes? So it is be nothing but yes. Plus and minus are specifically for binary class. This can be positive, negative. So the probability with respect to yes, can I write 3 by 3? Only for this. What is the probability out of this? Total number of this is there 3 by 3. Similarly, if I go and see the next term, log to the base 2 p plus. So again, if I go ahead and write over here, log to the base 2 p plus. P plus is again 3 by 3. So then again we have minus, and this is now p minus. What is p minus? 0 by 3 log base 2 0 by 3. This obviously will become 0. This will obviously become 0 because 0 divided by anything is 0. What will this be? 1 log to the base 1. What is this? This is nothing but 0. Log to the base 1 is nothing but 0. Tell me whether this is a pure split or impure split. So this is a pure split. Whenever we have a pure split, the answer of the entropy is going to come to 0. So here I'm going to define one graph. This is h of s, and let's say this is p plus or p minus. If my probability of plus, see, when I say probability of plus is 0.5, what will be probability of minus? It will also be 0.5, right? Because it's just like p is equal to 1 minus q, right? If p is 0.5, then q will be 1 minus p. Same thing, right? So when it is 0.5, obviously my h of s will be 1. Let's say. So this is the graph that will basically get formed. Let's go ahead and try to calculate the entropy of this, guys. What will be the entropy of this node? So here I'm going to just make a graph. H of s minus, what is p plus? P plus is nothing but 3 by 6. Log base 2 3 by 6 minus 3 nodes are there, 3 by 6 log base 2 3 by 6. So if you compute this, log base 2 to the power of 1, if you do the calculation here, I am actually going to get 1. So when I'm getting 1, when I'm actually getting 1, when you have 3 yes and 3 no's, what is the probability? It is 50-50%, right? So when your p plus is 0.5, that basically means your h of s is coming as 1. So from this graph, you can see that I'm getting 1. If this is 0, this is 1. This is 0 and this is 1. I hope everybody is able to understand, guys. 0 and 1. If your p plus is 0 or if your p plus is 1, that basically means it becomes a pure split. So in h of s, you are going to get 0. So always understand your entropy will be between 0 to 1. If I have an impure, this is a completely impure split, because here you have 50% probability of getting yes, 50% probability of getting no. H of s is entropy. This is entropy for the sample. H of s, notation that I am using is H of s. So if whenever the split is happening, the first thing is done, the purity test. The purity test is done with the help of entropy right now. I'll also show Gini impurity, don't worry. So with the entropy, you will be able to find if I am getting 1, that basically means it is a impure split. And if I'm getting 0, it is pure split. So this is the graph. Okay, this is the graph, and this graph is basically the entropy graph. Again, understand, if your probability of getting yes or no is 0.5, that basically means 50-50 is there. 3 yes and 3 no's. Then your entropy is going to be 1, h of s. If your probability is completely 1, that basically means either you are getting completely yes or completely no. So your entropy will be 0. That basically means it is pure split. So in the case of probability 0.5, you are getting plus 1. Then it will keep on reducing. Now let's go ahead and let's try to understand. So here you have understood about purity test. Definitely you'll use entropy, try to find out whether it is pure or impure. If it is impure, you go ahead with the further division of the categories. Again, you take another feature, divide it, because here from this to which split you will do further? You will do this split as further. If you are getting 0.6, 0.6 is this specific value, then you probably go and draw over here. This is your entropy. If your probability is here, which is 0.3, then you will go here and create this. This may be 0.4 or 0.3, something like this. It will be between 0 to 1. Let's go ahead and discuss about the second issue. I hope everybody is we have discussed about checking the pure split or not, and we have understood this much. But the next thing is that, okay, fine, Krish, this is very good. You have explained well. I know many people will say that, but there are some people I can't help. Let's say that I have some features, okay? Now coming to the second problem. How do we consider which node to cap, which feature to take and split? Because here I may have one split. So again, let's see that what is the second problem. Which feature to take to split, right? This is the second problem that we are trying to solve. Let's say that I have one feature 1 over here, and I have two categories. Let's say this is there, C1 and C2. Here, let's say that I have 9 yes, 5 no's, and then I have 6 yes, 2 no's. Here I have basically 3 yes and 3 no's, let's say. And in my data set, I have features like F1, F2, F3. Now let's say that another split, I can actually start with feature 2 also. And in feature 2, I may have probably 3 categories like C1, C2, C3. So with respect to the root node and all the other features, because after this also I may have to split, right? I may have to take another feature and keep on splitting, right? Based on the pure or impure split. How do I decide, should I take F1 first or F2 first or F3 first or any other feature first? How should I decide that which feature should I take and probably do the split? That is the major question. So for this, we specifically use something called as information gain. So here I'm just going to say, here we basically use information gain. Now what is this information gain? I'll talk about it. So information gain, first of all, I will write the formula. We basically write gain with sample. First with feature 1 I will compute. So first with feature 1 I will compute. Suppose this is my first split of my data, and probably I'm computing over here. This can be written as h of s. I'll discuss about each and every parameter, don't worry. Summation of v belong to values s of v. Don't worry guys, if you have not understood the formula, I will explain it. Then the sample size h of sv. I'll discuss about each and every parameter. Let's say that I'm taking this feature 1 split. You have already seen what is feature 1. So this is my feature 1. I have two categories, C1, C2. This has 9 yes, 5 no's. This has 6 yes and 2 no's. And this has 3 yes and 3 no's. Now I will try to calculate the information gain of this specific split. Now I will go ahead and probably take this up. Now see, over here, we'll try to understand what is this. Now if I want to compute the gain of S of F1, first thing that I need to find out is H of S. Now this H of S is specifically of the root node. So I need to first of all calculate what is H of S. H of S is nothing but entropy. Entropy of the root node. So if I want to compute the entropy of the node, tell me how should I compute? H of S is equal to minus P plus log base 2 P plus. Calculate guys along with me. Minus P minus log base 2 P minus. So I hope everybody knows this. So here I'm going to compute by what is probability of plus over here in this specific root node. It is nothing but 9 by 14. Then I have log base 2, again 9 by 14. Then I have p minus, what is p minus? 5 by 14 log base 2 5 by 14. So this calculation I will probably get it as 0.94, approximately equal to 0.94. Just check it whether you are getting this or not. Again, you can use calculator if you want. Now, I have definitely found out this. This is specifically for the root node. Now, let's see the next thing, the next important thing, which is this part. What is S of V and what is S and what is H of SV? Now, very important, just have a look. Everybody, see this graph. Okay, see this graph. I will talk about H of SV. First of all, I'll talk about H of SV. Okay, this one. This is the entropy of category 1 you need to find and entropy of category 2 you need to find. So if I write H of SV of category 1. So what is category 1 for this? I'll write SC1, let's say. I'm going to write like this. Quickly calculate the H of SV of this and this. Separately you need to calculate. So H of SV of C1. Okay. So here again you will write minus 6 by 8 log base 2 6 by 8 minus 2 by 8 log base 2 2 by 8. I hope everybody knows this, how we got it. So H of SV basically means I am going to compute the entropy of this category and this category. So for that I will basically write H of, so here I will write minus 6 by 8 log base 2 6 by 8 minus 2 by 8 log base 2 2 by 8. So if I get it, I'm actually going to get 0.81. And similarly, if I calculate H of C2, quickly calculate how much you are going to get, guys. 6 by 8, 6 by 8. With respect to this, we need to find out. So now we have all these values. We'll start equating them to this equation. So here we have finally gain of S comma F1. So let's say that here I'm going to basically add 0.94 minus, see, minus summation of, okay, summation of. What is S of V? Understand, S of V basically means that how many samples I have over here. Let's say for category 1. How many samples I have for category 1 over here? Simple. If you really want to just calculate, it is nothing but 8. And total number of sample is how much? If I go and see over here, there are 9 yes, 5 no's. Okay, 9 yes and 5 no's. That basically means 14 total sample. Here you have 8 sample. Okay, so this will become 8 by 14. Then you multiply by what? See from this equation, you multiply by H of SV. So H of SV is nothing but the entropy of category 1. So entropy of category 1 is nothing but 0.81. Plus, then you go again back to the graph and try to see that for C2, how many total number of samples are there? 3 plus 3 is 6. So 6 by 14 it will become multiplied by 1, right? So this is your entire thing. So here, after all the calculation, you are going to get 0.041. So this is my gain with S comma F1. So here I have got this value. Amazing. I did this with feature 1 only. What about feature 2? Let's say that this was my split for feature 2. And suppose I get the gain for S comma feature 2 as 0.00051. If I get this, now tell me, in using which feature should I start splitting first? Whether it should be F1 or whether it should be F2 based on this value. You know that over here, the gain, the information gain of S comma F2 is greater than gain of S comma F1. So your answer is very much simple. We will definitely use feature 2 to start the split. The thing over here, you are trying to understand that if I really want to select which feature to select to start my splitting, then I have to basically calculate the information gain and go throughout all the paths. And whichever path has the highest information gain, then we will select that specific thing. Now the question rises, Krish, Obviously, this is good. But you had written about Guinea impurity. What is the purpose of that? Please explain us. And why Guinea impurity is basically used. So let me go ahead with Guinea impurity. I told that yes, you can obviously use entropy, but why Guinea impurity? So Guinea impurity formula, which I have specifically written as 1 minus summation of I is equal to 1 to n p square. Now what is this p square? Suppose let's say that in my n is the number of outputs. Right now, how many outputs I have? I have 2 outputs, yes or no. So I will expand this 1 minus, since this is summation I is equal to 1 to n. I'm basically going to say that, okay, fine. I will write probability of plus whole square plus probability of minus whole square. So this is the formula for Guinea impurity. Now you may be thinking, okay, fine, the calculation will be obviously very much easy, right? Suppose if I have a node, which has 2 yes, 2 no's. Now in this particular case, how do I calculate my this probability? If I have 2 yes or 2 no's, suppose let's say that I have a node over here, which is my split, and this is having 2 yes and 2 no's. So how do I calculate? I will write 1 minus, what is probability of square? 1 by 2 square. Sorry, not 1 by 2. Yeah, 1 by 2 square plus 1 by 2 square. Right? Then I will say 1 by 4 plus 1 by 4 is nothing but 2 by 4, which is nothing but 1 by 2. So I will be getting 0.5. Now here you understand. This is a complete impure split, right? If you have an impure split, in entropy, the output you are getting it as 1. Whereas in the case of Guinea impurity, as 0.5. So if I go ahead with the graph that I probably had created here, so my Guinea impurity line will look something like this. So it will be looking something like this. For 0, obviously I'll be getting 0. But whenever my probability of plus is 0.5, I'm going to get 0.5 over here. And that is the difference between Guinea impurity and entropy. But you may be saying, Krish, when to use what? Now let's understand that when to use Guinea and when to use entropy. Tell me guys, if I consider this formula of Guinea impurity, and if I consider entropy, this formula, where do you think more time will take for execution for this particular formula? Whether for entropy it will take or for Guinea impurity it will take. More time, where it will probably take for the execution purpose. See, understand, decision tree is having a worst time complexity, because if you have 100 features, probably you'll keep on comparing by dividing many features, then probably compute information gain like this. If you have just 100 features, so which is faster, entropy or Guinea impurity? Understand, in entropy you have log function, here you have log function, here you have simple maths. The more amount of time out of entropy and Guinea impurity, the more amount of time basically is taken by entropy. So if you have huge number of features like 100, 200 features and you are planning to apply decision tree, I would suggest try to use Guinea impurity, then entropy. If you have small set of features, then you can go ahead with entropy. So over here, definitely with respect to fast, Guinea is greater than entropy. Now let's go ahead and understand with respect to, you may be thinking, Krish, okay fine, you have basically explained us about categorical variables over here. See, over here you have explained about categorical variables. What if I have numerical feature? Let's say I have f1 over here, which is a numerical feature. I have an f1 feature, which is numerical feature, and I may have values. Let's say that I have sorted all the values over here. Okay, let's say that I have f1 and output. Okay, so this f1, let's say that I have values like a sorted order values. I'm sorting these features I'm basically doing this. Let's say that initially I have this features like this. And let's say I have values like 2.3, 1.3, 4, 5, 7, 3. Let's say I have these features. Now, this is a continuous feature. This is a continuous feature. So for a continuous feature, how probably the decision tree entropy will be calculated and the information gain will get calculated. So here you will be able to see that I will first of all sort these values. So in F1, the decision tree will basically first of all sort these values. So I have 1.3, then you have 2.3, then you have 4, sorry, then you have 3, then you have 4, then you have 5, and then you have 6. Now, whenever you have a continuous feature, so how the continuous feature will basically work in this case? First of all, your decision tree node will say that we'll take this only one first record and say that if it is less than or equal to 1.3. Okay, if it is less than or equal to 1.3, so here you will be getting two branches, yes or no. So yes and no, definitely your output over here will be put over here, right? And then for the no, here you will be having another node. Over here, how many number of records you will be having? In this particular case, you will be having one record. In this particular case, you will be having around 5 to 6 records. And here also you will be able to see, right, how many yes and no's are there. Definitely this will be a leaf node. So in the first instance, they will go ahead and calculate the information gain of this. Then probably once the information gain is got, then what they'll do? They will take the first two records and again create a new decision tree. Let's say that this will be my suggestion where they'll say it is less than or equal to 2.3. So I will get 1 and 1 over here. So in this now you will be having two records which will basically say how many yes and no are there, and remaining all records will come over here. Then again information gain will be computed here. Then again what will happen? They'll go to the next record. Then again they'll create another feature where they'll say less than or equal to 3 and they will create this many nodes. Again they'll try to understand that how many yes or no are there, and then they'll again compute the information gain. Like this they'll do it for each and every record. And finally, whichever information gain is higher, they will select that specific value in that feature and they'll split the node. So in a continuous feature, whenever you have a continuous feature, this is how it will basically have. And then it will try to compute who is having the highest information gain. The best information gain will get selected, and from there the splitting will happen. Now let's go ahead and understand about the next topic, is that how this entirely things work in decision tree regressor. Because in decision tree regressor, my output is an continuous variable. So suppose if I have one, feature 2, and this output is a continuous feature. It will be continuous. Any value can be there. So in this particular case, how do I split it? So let's say that F1C feature is getting selected. Now in this F1C feature, what value will come when it is getting selected? First of all, the entire mean will get calculated of the output. Mean will get calculated. So here I will have the mean, and here the cost function that is used is not Gini coefficient or Gini impurity or entropy. Here we use mean squared error, or you can also use mean absolute error. Now what is mean squared error? If you remember from our logistic linear regression, how do we calculate? 1 by 2m summation of I is equal to 1 to n y hat minus y whole square. Y hat of I minus y whole square. This is what is mean squared error. So what it will do, first based on F1 feature, it will try to assign a mean value, and then it will compute the MSE value. And then it will go ahead and do the splitting. Now when it is doing splitting based on categories or continuous variable, I will be having different categories. Now in this categories, what will happen after split? Some records will go over here. Then I will be having a mean value of this over here. That will be my output. And then again the MSE will get calculated over here. As the MSE gets reduced, that basically means we are reaching near the leaf node. And the same thing will happen over here. So finally, when you follow this path, whatever mean value is present over here, that will be your output. This is the difference between the decision tree regressor and the classifier. Here, instead of using entropy and all, you use mean squared error or mean absolute error. And this is the formula of mean squared error. Now, let's go to the one more topic, which is called as the hyperparameters. Tell me, decision tree, if I keep on growing this to any depth, what kind of problem it will face? Regressor part, you want me to explain? Okay, let's see. Okay, let's do the regression. Decision tree regressor. Let's say I have feature F1 and this is my output. Let's say I have values like 20, 24, 26, 28, 30. And this is my feature 1 with category 1, let's say. Some categories are there. Let's say I have done the division by F1. That is this feature. Initially, tell me what is the mean of this. That mean value will get assigned over here. Then using MSE, that is mean squared error, here you will try to calculate. Suppose I get an MSE of some 37, 47, something like this. And then I will try to split this. Then I will be getting 2 more nodes or 3 more nodes. It depends. Then that specific nodes will be the part of this. Again, the mean will change. Again, the mean will change over here. Suppose this 2 is there, this 2 records goes here, right? Then again, MSE will get calculated. I'm just taking as an example over here. Just try to assume this thing. Now, if I talk about hyperparameters, see, this is what is the formula that gets applied over here, MSE. Now, let's see in this. Hyperparameter, always understand decision tree leads to overfitting. Because we are just going to divide the nodes to whatever level we want. So, this obviously will lead to overfitting. Now, in order to prevent overfitting, we perform 2 important steps. One is post pruning and one is pre pruning. So this 2, post pruning and pre pruning, is a condition. Let's say that I have done some splits. Let's say over here I have 7 yes and 2 no. And again, probably I do the further split like this. Now in this particular scenario, you know that if 7 yes and 2 no's are there, there is a maximum, there is more than 80% chances that this node is saying that the output is yes. So should we further do more pruning? The answer is no. We can close it and we can cut the branch from here. This technique is basically called as post pruning. That basically means, first of all, you create your decision tree, then probably see the decision tree and see that whether there is an extra branch or not, and just try to cut it. There is one more thing which is called as pre pruning. Now, pre pruning is decided by hyperparameters. What kind of hyperparameters? You can basically say that how many number of decision tree needs to be used. Not number of decision trees, sorry. Over here, you may say that what is the max depth? What is the max depth? How many max leaf you can have? So this all parameters you can set it with grid search CV. And you can try it and you can basically come up with a pre-pruning technique. So this is the idea about decision tree regressor. Yes, it is possible your Gini value will be 1, no? This graph is there, no? Acha, Gini value. Are you talking about this Gini entropy? It will not be 1, it will always be between 0 to 0.5. So the first thing first, as usual, what we should do? We should import the libraries. So here I will go ahead and import the library. So I'll say import pandas as np, pd, import matplotlib.pyplot as plt, import. So this basic things I have with me. So I will go and take any data set that I want from sklearn.datasets, import. Let's say that I'm going to take load iris dataset, and then I'm going to upload the iris dataset. So I'm going to write load iris. This is my iris dataset. Then the next step, once you get your iris dataset, so this is my iris.data. Okay, these are all my features. The 4 features will be there. These 4 features are petal length, petal width, sepal length, and sepal width. This is my independent features. Then if I really want to apply for classifier, so decision tree classifier, so I can first of all import from sklearn dot tree import decision. Let's see where is decision tree present in sklearn. Decision tree classifier. The name is absolutely fine, but I was not getting it over here. So this is got no module sklearn. Okay, sklearn. Learn. So here you have classifier. Right now I'm just going to overfit the data. Then I'll probably show you how you can go ahead with pruning. So by default, what are the parameters over here? If you probably go and see in the classifier over here, you have criterion. See this. The first parameter is criterion. By default, it is Guinea. Then you have splitter. Splitter basically means how you're going to split. And there also you have two types, best and random. You can randomly select the features and do it. Okay, you should always go with best. Max depth is a hyperparameter. Minimum sample lift is a hyperparameter. Max features, how many number of features we are going to take in order to fix that. That is also an hyperparameter. So all these things are hyperparameter. Okay. So I will just by default executed whatever is giving me in decision tree. And the next thing that I'm actually going to do is create a decision tree. So for this, I will be using plot.figSize, plot.figure. Inside figure, I have this fixed size. Okay, and I will probably show in some better figure size so that everybody will be able to see it. So here, let me say that I'm going to take an area of 1510, and then probably I'm going to say tree dot plot, and here I'm going to say place a classifier, and it should be filled. The coloring should be filled with this. So tree, it should be classified tree dot plot. Okay, I have to also import tree. So I have to basically import tree. So from sklearn import tree. Again, I'm getting error. Has no attribute plot. Why? Let me just see the documentation, guys. So this plot function is like plot underscore tree. Dot tab plot underscore tree. Now what is the error we are getting? Okay, not fitted yet. Sorry. So I'm going to say classifier dot fit on data. What data? Iris dot data. And then I'm going to fit with iris dot target. So once this is done, I think now it will get executed. So this is how your graph will look like, guys. So here you can see this is how your graph looks like. Now, if I show you the graph, over here, see, you can see some amazing things. Over here, 3 outputs are actually there in this. When you see in this left hand side, this become a leaf node. So this first one is probably versicolor flower. Okay. If you go on the right hand side, here you can see 50-50 is there. So based on one feature, here you will be able to see that you are getting a leaf node. Based on another branch, here you are getting 0-50-50. So again, you have 2 more features getting splitted over here. So here you have 49.5. Here you have 47.1. Do we require this split? Anybody tell me. From here, do we require any more split? Just try to think. This is after post pruning. I want to find out whether more splits are required or not. Now in this particular case, you see this. After this, do you require any split? You did not require, right? Here you are basically getting 47.1. I guess after this also you require no split. So understand this. So this is basically post pruning. So you can then decide your level and probably do it. Guinea value is more than 0.5. Okay, this side, this is coming as 0.5. Greater than 0.5. It should not have. Here it is 0.5. No, maximum 0.5 can come. 0 to 0.5 only should come. I don't know why this is coming as 0.667. I'll have a look onto this, guys. But anywhere you see other than that, everywhere you are getting less than 0.5. The plotting graph is very much easy. You use sklearn import tree, then you basically do this. Get classifier and field is equal to true, and you can just do this. So the agenda, let me define the agenda, what all things are there. First, we'll understand about ensemble techniques. In this ensemble techniques, we are basically going to discuss about what is the difference between bagging and boosting. Second, what we are basically going to discuss about is the agenda of this session is ensemble techniques, bagging and boosting. Then we are probably going to cover random forest, and then probably we will try to cover Adaboost. And if I have more energy, I will also try to cover Xgboost. So all these algorithms we'll discuss about it. So let's go ahead and let's start the topics. The first topic that we are going to discuss is about ensemble techniques. Now, what exactly is ensemble techniques? And we are going to discuss about it. Okay. So ensemble techniques. What exactly is ensemble techniques? Till now, we have solved two different kind of problem statement. One is classification and regression, and we have learned about different algorithms like linear regression, logistic regression. We have discussed about KNN. We have discussed about yesterday what did we discuss about naive bias. Different algorithms we have already finished. Now, with respect to classification and regression problem, whatever algorithm we are discussing, there was only one algorithm at a time we were discussing. One algorithm at a time we are discussing, and we are trying to either solve a classification or a regression problem. Now, the next thing is over here is that can we use multiple algorithms to solve a problem? Multiple algorithms basically means can we? I'll just talk about it. Okay. Now, if I ask this specific question, can we use multiple algorithms to solve a problem? At that point of time, I will definitely say yes, we can, because we are going to use something called as ensemble techniques there. Now, what this ensemble techniques is, okay? So in ensemble techniques, we specifically use two different ways. One way is that we specifically use, and the other one, I'll just go to write it over here. So one that we basically use is something called as bagging technique. And the other one we specifically use is something called as boosting technique. So in bagging technique, what exactly we can do, and in boosting technique, what we can actually do, and how we are combining multiple models to solve a problem. So let's first of all discuss about bagging. Now, how does bagging work? Let's say that I have a specific data set. So this is my data set with features, rows, columns, everything like this. I have this specific data set. Just imagine I have many features over here like this: F1, F2, F3, and probably I have my output. So this is my data set D. Let's consider it. Now, what we do in bagging is that we create models, and this model can be anything. It can be logistic, it can be linear. For a classification problem, let's say that this is logistic model. So this is my model M1. Let's say I have another model M2. Then I may have another model M3. Let's say that this is logistic, and this is probably the other model, which is like decision tree. And then probably we use this model as KNN classification, and this model can again be decision tree. It's fine. Let's use another decision tree. So now here you can see that we have used so many models. Okay, so many models are there. Now, with respect to this particular model, what I will do is that the first step that I will do from this particular data set, I will just take up some rows. So I'll basically do row sampling, and I'll take a row sampling of D dash. D dash basically means this D dash is always less than D. Some of the rows I'll push it to M1. Okay, I can also use naive bias. Fine. So what I'll do is that some of the rows I'll push it to model 1. This model 1 will be training. Let's say that for out of this 10,000 record, 1,000 rows, I'm actually doing a row sampling of 1,000 rows and giving it to M1 to train it. Then what I'm actually going to do over here, I'm basically going to give this specific model M2, and again I'm going to do row sampling, and I'm again going to sample some of the rows and give it to model 2. And again, remember, some of the rows may get repeated from this D dash to next D double dash. Similarly, I will do row sampling and give it to this, and again I may have D triple dash and D4 dash. So different rows, data points. When I say row sampling, basically I'm talking about data points. Different data points, I will give it to separate model, and this model will specifically train. When I say D dash, that basically means suppose I say 10,000 are my total number of data points. When I say D dash, this D dash may be 1,000 points. then D double dash may be another 1000 points, and some of the rows may get repeated over here. D triple dash, here also I can basically use. So here specifically row sampling will be used. Now when I have this many specific stuffs, each and every model will be trained with different kind of data. Now how the inferencing will happen for the test data. So first thing first, let's say that I'm going to get a new test data over here. Now new test data will be passed to M1, and this M1, suppose it gives 0 as my output. Suppose let's say that I'm doing a binary classification. It gives a 0 as an output. So this is my output of 0. Next M2 for the new test data gives 1, M3 gives 1, and M4 also gives 1 as the output. Now in this particular case, what will happen? Now you can see over here, it's simple. What do you think the output may be in this particular case? Now M1 has predicted for this particular test data as 0. The model M2 has predicted 1, M3 has predicted 1, and M4 has predicted 1. So finally, all these outputs are going to get aggregated. And a simple thing that gets applied is majority voting. So tell me, what will be the output with respect to this? The output will obviously be 1, because the majority voting that you can see, 3 people are basically saying it as 1. So my output over here will be 1. Okay, this is the concept of bagging, wherein you are providing different rows with probably all the features in this case, and giving it to different model, again, which is a classification model. And then finally you are combining them based on majority voting, and you are getting the answer as 1. So this step is called as bootstrap aggregator. That basically means you are aggregating all the output that it is basically coming from all the specific models. Now many people will say, Krish, what about tie? Guys, like this kind of situation, we will be having more than 100 to 200 models. So it is very difficult that it will be a tie. Who are repeating questions, they will be put up in timeout. So what if you're saying that if the 50% of model says yes, 50% of model says no? Always understand, guys, we will be having more than 100 to 200 plus models. So in this particular case, there will be high probability that always there will be a majority voting available. It will always not be in that specific scenario. So this was the concept about bagging. Now some people will be saying that, Krish, why are you using different models? Guys, I'm not discussing about random forest over here. Random forest uses only one type of model, that is decision tree. But if we think as a concept of bagging, you can have different models over here, and you can basically combine them. So this is a technique of ensemble techniques, and this is basically called as bagging. Okay, now tell me one point I missed out. Fine, this is with respect to the classification problem. With respect to the regression problem, what will happen? In case of a regression problem, let's say that I got here 120, here 140, here 122, here 148 as my output. So in regression, what will happen is that the entire mean will be taken. The output mean will be basically taken, and that will be your output of the model. Average or mean. Very simple, right? So average or mean will be basically taken up, and here based on the average, you will be able to solve the regression problem. Great. Now let's go ahead and try to understand with respect to bagging and boosting how many different types of algorithm are there. But before that, I need to make you understand what exactly is boosting. Now here in bagging, you have seen that you have parallel models, right? 1, 1, 1. Independent, you have parallel models. You're giving some row samples in different models, and basically you're able to find out the output. Now in case of boosting is a sequential combination of models like this. You have a lot of sequential models like this, and one after the model. Like first I'll give my training data to this particular model, then it will go to this data, then this model, then this model. So this will be my M1, M2, M3, M4, and finally I will be getting my output. So here you can basically say that boosting is all about, and this M1, M2, MT, we basically mention it as weak learners. So this will be weak learner, weak learner, weak learner, weak learner, and finally when we go till here, it'll, if I combine all these weak learners, weak learner, okay, once I combine all this weak learner, it becomes a strong learner. Finally, if I try to combine this will basically become a strong learner. So here you have all the models sequentially one after the other, and then you will probably try to provide your input, from one model to the next model to the next model. And these all models will be a very simpler weak learner model, which will not be able to predict properly. But when you combine all these particular models together sequentially, it becomes a strong learner. How this specifically works, I'll take an example of Adaboost, Xgboost. I will show you that. Okay. Weak learner basically means the prediction is very bad. But as you go sequentially, you combine them, they become a strong learner. Okay. One example I want to give you, let's say that you are a data scientist, right? Let's say that this model 1 may be a teacher with respect to physics. Then this model 2 may be a teacher with respect to chemistry. Let's say model 3 is basically a teacher of maths and model 4 is a teacher of geography. Now suppose if you are trying to solve one problem, obviously if the physics teacher is not able to solve that particular problem, then probably chemistry can help, or maths can help, or geography can help, or someone can help. So when we combine this many expertise together, they will be able to give you the output in an efficient way. Sumit, I'll talk about it, whether all the features are basically passed to all the models or not. I'll just talk about it. Just give me some time, okay? But I just want to give you an idea about, in short, if someone asks you in an interview, what exactly is boosting, okay? Boosting is, you can just say that it is a sequential set of all the models combined together. And these all models that are initialized are usually weak learners, and when they are combined together, they become a strong learner. And based on this strong learner, they give an amazing output. And right now, if I say in most of the Kaggle competition, they use different types of boosting or bagging technique. So we have basically, as I said, bagging and boosting. In bagging, what kind of algorithm we specifically use? We use something called as random forest classifier, and the second model that we specifically use is something called as random forest regressor. So we specifically use these two kind of models, which I'm actually going to discuss right now after this. And then in boosting, we basically use techniques like Adaboost, gradient boost. Number 3 is extreme gradient boost, which we also say it as Xgboost, extreme gradient boost. So let's go ahead and let's discuss about the first algorithm, which is called as random forest classifier and regressor. Now, first thing first, let's understand some things from the yesterday's class. I hope what is the main problem with respect to decision tree? Whenever we create a decision tree without any hyperparameter, does it not lead to overfitting? Does it not lead to overfitting? Whenever you probably have a decision tree, right? It leads to something like overfitting. Why overfitting? Because it completely splits all the feature till its complete depth. Overfitting basically means for training data, the accuracy is high. For test data, the accuracy is low. So training data, when the accuracy is high, I may basically say it as high bias. And then I may basically say it as, sorry, not high bias, low bias and high variance. So low bias and high variance. Yes, obviously we can do pruning and all, guys. But again, understand pruning is an extensive task. Probably if you have 100 features, if you have data points which is like 1 million, to do pruning also it is very much difficult. Yes, pre-pruning can be done, but again, we cannot confirm that it may work well or not. So right now, with respect to decision tree, you have this specific problem, that is low bias and high variance. Now in low bias and high variance, you know that my model is basically the generalized model that I should get. It should have low bias and low variance. So if somebody asks you, why do you use random forest? You can basically explain about decision trees like this. Now my main aim is to convert this high variance to low variance. Now I will be able to convert this high variance to low variance using random forest classifier or random forest regressor. Now what does random forest do? Random forest is a bagging technique. Similarly, I have a data set over here. Let's say that I have this data set, and then here I will be having multiple models like M1, M2, M3, M4. Let's say I have this 4 models. Like this, we'll have many models. Now, with respect to these models, all the models are actually decision tree in random forest. All are decision trees. You don't have a different model over there. So over here, you can see that all the models are decision trees that is going to get used in random forest. So decision trees always gets used in random forest. The first thing that you should know. Now, whenever we are using decision trees, you know that decision tree, if we try to create it, it may lead to overfitting. And because of that, every decision tree will basically create low bias and high variance. But if we combine in the form of bootstrap aggregator, this high variance will be getting converted to low variance. Because why? Because majority of voting we will be taking from this particular decision trees. Like there will be many decision tree, so there lot of outputs will be coming, and with the help of majority voting classifier, this high variance will get converted to low variance. Now in random forest, how it works? In the first case, if I talk about random forest, over here, two things basically happen with respect to the D dash data set. Let's say in first model, we do some kind of row sampling plus feature sampling. That basically means we have to select some set of rows and some set of features and give it to M1. Similarly, you do row sampling and feature sampling and give it to M2. Then you do row sampling and feature sampling, you give it to M3. And then you do row sampling and feature sampling, you give it to M4. Now when you do this, so what will happen? Independently, you are giving some features along with some rows. Now there may be a situation that your features may also get repeated. It may also get repeated. Your records or data points may also get repeated. So when you are probably training your model with this specific data sets and specific features, this model become expert in predicting something, right? As I said, one example over here, I'm giving a physics model some data, I'm giving chemistry model with some data. Similarly, here I'm giving some information to some model, so the model will be an expert with respect to that specific data. So based on all this particular data, whenever I get a new test data, so what will happen? Suppose let's say that this is a classification problem. The M1 model will be predicting 0, this will be predicting 1, this will be predicting 0, and this will be predicting 0. Now in this particular case, again, the majority voting classifier or majority voting will happen in the case of classification problem. And then here you will be specifically able to get the output as 0. So I hope everybody is able to understand all the models over here are decision trees, and based on that you will be doing, see, when I'm in an interview, you should be very the things that I'm telling you over here is all the points are very much important. And similarly, if you tell the interviewer, definitely your interview is cracked in this kind of algorithm. I've seen some of my students saying that, okay, Krish, when the interviewer asked me that which is my favorite algorithm, I said random forest. I told, why did you say like that? Because he said that because that person let him ask any questions in random forest, I'm very much confident about it. And I'm also going to prove him, why they are very good. So with this specific case here, you can basically see that because of the overfitting condition of the decision tree, you're combining multiple decision tree so that you get a generalized model which has low bias and low variance. So I hope everybody is able to understand. Boost feature sampling basically means, suppose if I have 1, 2, 3, 4 feature. For the first model, I may give 2 features. For the second model, I may get 3 features. For the fourth model, I may give 4 features, or any one feature also I can give to a specific model. So internally, that random forest it take care of. Over here, these things are there, and this is how random forest works. Only the difference between random forest classifier and regression is that in regression, again, whatever output you are basically getting, you basically do the mean. That's it. Average. You just do the average, you'll be able to get the output based on all the models output that you are actually getting. Now let's talk about some of the important points in random forest. The first question is that, is normalization required in random forest? Then the next question is that in KNN, is normalization, when I say normalization or standardization, I'll just talk about standardization. Is standardization is required? So this will be my another question. So is normalization required in random forest or decision tree? You can also say it as decision tree. Is it required? So for this, the answer will be no. Because understand, decision tree will basically do the splits. If you minimize the data also, that split won't be that much important. But if I talk about KNN, either standardization, normalization required over here, the answer is yes. Because here we use two things. One is Euclidean distance and Manhattan distance. Because of this, you definitely have to apply standardization so that the computational distance becomes easy. So this is one of the most common interview questions that is basically asked in random forest. Coming to the third question, is random forest impacted by outliers? Over here, the answer will be no. Just check it out. Outside basically means Google and check it out. Check it out in Google. Okay, perfect. So I hope I've covered most of the things in random forest. Is random forest impacted by outliers? This is the third question. Is KNN impacted by outliers? Is this KNN algorithm impacted by outliers? Is KNN impacted by outliers? The answer is yes. Big yes. Perfect. So these all are the interview questions that needs to be covered. Now let's go ahead and discuss about Adaboost. Now in bagging, most of the time we specifically use random forest, or you can also create custom bagging techniques. Custom bagging techniques means whatever algorithm you want, use the combination of them and try to give the output. This also you can do it manually with the help of hands. Okay guys, so second thing we are going to discuss about is boosting technique. And this, the first thing that first algorithm that we are going to discuss about is Adaboost. So Adaboost, we are going to discuss about how does Adaboost work. Now let's solve the first boosting technique, which is called as Adaboost. Okay, and this is a boosting technique. In the boosting technique, you have heard that we have to basically solve in a sequential way. This, at least you know. I know there is a lot of confusion within you all, but we'll try to solve a problem. Let's say, so suppose I have a data set which looks like this: f1, f2, f3, f4. So these are my features, and probably these are my output. Okay, so let's say that I am having these features like this, and this is my output like yes or no, like this. So let's say that how many records I have over here: 3, 4, 5, 6, and one more is there, 7. So this 7 records are there. Now in Adaboost, the first thing is that specifically with Adaboost, you really need to understand that what all things we can basically do. How do we solve this classification problem that we are going to understand? The first thing first is that we define a weight. And the weight is very much simple. Initially, to all the records, to all these input records, we provide an equal weight. Now, how do we provide an equal weight? We just go and count how many number of records are there. Now, in this particular case, the total number of records are 1, 2, 3, 4, 5, 6, 7. Now, every record, I have to provide an equal weight, that is between 0 to 1. So, the overall sum should be 1. So, in this particular case, what I can do, if I make 1 by 7, 1 by 7, 1 by 7 to every one, this will definitely become a equal weights to all, right? And if I do the total sum, it will obviously be 1. Let's go to the next one. Now, after this, what do we do? Okay, after this, in Adaboost, the first thing that we do is that we take any of this feature. How do you decide which feature to take? Whether we should go with F1 or whether we should go with F2 or whether we should go with F3. This we can do it with the help of information gain and entropy or Gini, right? Based on this, we can definitely understand whether we should start making decision. Here also you specifically make decision trees. So here what you do is that you probably have to determine by using which feature I have to start my decision tree. So suppose out of all this feature 1, feature 2, feature 3, you have selected that, okay, the information gain and entropy of feature 1 is higher. So I'm going to use feature 1 and probably divide this into decision trees. Now, when I divide this into decision tree, let's say that I'm dividing like this into decision tree. This decision tree depth will be only one depth. And this depth, since it has only one depth, we basically call it as stumps. So what we do over here specifically, we will create a decision tree by taking only one feature and we will only divide it to one level. Okay, one level or one depth. That's it. And this is specifically called as stump. What we are going to do next is that from this particular stump, okay, the stump is basically getting created. Only one. So that is Adaboost, right? We say it as weak learners because this is weak learner. Weak learner, why? There is a reason we say this as weak learner. So only weak learner. So that is the first thing with respect to this particular Adaboost. So the first step is that this is a weak learner. So for the weak learner, we basically create a stump. Stump basically means one level decision tree. That's it. Based on the information gain and entropy, I have selected the feature and then I just made a decision tree with only one level. Why it is called as? It is called as weak learner. Okay, so that is the reason we use only stump. That is just a one level decision tree. Now the next step happens is that we provide all these specific records to this F1 and we train this specific model. Only with one level decision tree we train them. Now after we train them, let's say that we are going to pass all these particular records to find out how many are correct and how many are wrong this decision tree is basically giving. So let's say that out of this entire records, one record one record was just given as wrong. Let's say that this is the record which was given as wrong. Okay, so let's say that this record output was predicted wrong from this particular model. Only one wrong was there after training the model. Now what we need to do in this specific case, understand a very important thing. So let's say that we have done this, and probably after this what we are actually going to do, we are going to calculate the total error. So how many error this particular model made. Let's say that in this particular case only one was wrong. So this was only wrong, right? One was wrong. So if I want to calculate the total error, how will I calculate how many of them are wrong? How many of them are wrong? Only one is wrong. What is the weight of this? So I will go and write 1 by 7. So this is specifically my total error out of this specific model, which is my stump over here. Okay, which is my F1 stump. Now, this is my first step. The second step is that I need to see the performance of stump. Which stump? This specific stump. And the performance is basically checked by a formula which is 1 by log E 1 minus total error divided by total error. Why we are doing this? Everything will make sense. Okay, in just time, in just a small time, everything will make sense. The first step that we do in Adaboost is that we try to find out the total error. The second step, we try to find out the performance of stump. Now in this particular case, it will be 1 by log E 1 minus 1 by 7 divided by 1 by 7. So once I calculate it, it will be coming as 0.895. F2 and F3, see, again understand, out of all these features, I found out from information gain and entropy that this is the best feature. Let's say that I have calculated this as 0.895. So this is my second step. The first step is find out the total error. The second step is performance of stump. What is TE? TE basically means total error. TE basically means total error. Now see the steps. Okay, see the steps. Whenever I am discussing about boosting, I am going to combine weak learners together to get a strong learner. Now what is the next step out of this now? What will be my third step? Understand over here. My third step will be to update all these weights. And that is the reason why I am calculating this total error and performance of step. So my third step will basically be new sample weight from the decision tree 1, which is my stump. So I'll say new sample weight is equal to, I need to update all these weights. Why I need to update all these weights? Again, understand. I'll talk about it just a second. So if I want to update the sample weights, first update I will do it for correct records. See, for correct records, whichever are correct, like these all records are correct. These all records are correct. Now, when I update the weights of this update the weights of this particular record, it should reduce. And when the wrong records that I have, this update should increase. Why? Because if I increase these weights, then the wrong records that are there, that record should go to the next weak learner. That is the reason why I am doing it. Now, how to update this particular weights for correct records? For correct records, the formula looks something like this. Weight multiplied by e to the power of minus this specific performance. Okay, this specific performance. So e to the power of ps, I'll write performance of stump, and then I will basically be able to write 1 by 7 multiplied by e to the power of minus 0.895. If I do the calculation, everybody try to do it, the answer will be 0.05. Now this is for correct records. What about incorrect records? For the incorrect records, the weights that is going to, the formula that we are going to apply is multiplied by e to the power of plus ps, not minus ps, plus ps. So here I'll write 1 by 7 multiplied by e to the power of 0.895. So if I go and probably calculate this, I'm going to get it as 0.349. So these two are the weights that I have got. That basically means all these records now which are correct 1 by 7, the new updated weights will be 0.05, 0.05, 0.05, 0.05. Sorry, not for the wrong records. Then this will be 0.05, then 0.05 and 0.05. So let me just see what is 1 by 7. So here you can see initially it was 0.142. Now it has got reduced to 0.05 because all these records are correct. But the wrong record value is 0.349. So my weights will now become over here as 0.349. Now I will just go ahead and write over here my new weight. My new weight is nothing but 0.05, 0.05, 0.05, 0.05, 0.05, 0.05, 1, 2, how many? 1, 2, 3. Okay, fourth record is here. Fourth record is there. 1, 2, 3, 4, 0.05, 0.05. Okay, how many records are there? 1, 2, 3, 4, 5, 6, 7. So my fourth record will basically become the new value that I'm having is something called as 0.349. Now tell me guys, if I do the summation of all these weights, is it 1? So probably no, I don't think so it is 1, because if I try to add it up, it is not 1. But if I go and see over here, these all are 1. If I combine all these things, 1, 2, 3, 4, 5, 6, 7, these all are 1. So here I have need to find out my normalized weight. Now in order to find out the normalized weight, all I have to do is that, what I have to do? Because the entire summation should be 1. So we have to normalize. Now in order to normalize, all you have to do is that go and find out what is the sum of all these things. The summation of all these things will be 0.649. All you have to do is that divide all the numbers by 0.649. Divided by 0.649. 0.649. Like this, divide all the numbers by 0.649 and tell me what will be the answer that you will be getting. So here your normalized weight will now look like 0.07, 0.07, 0.07, and this value will be somewhere around 0.537, I guess. In this case, then this will be 0.07, 0.07, 0.07. Here we are going to divide by all this 0.649. Now this is my normalized weight. Now after you get a normalized weight, we will try to create something called as buckets. Because see, one decision tree we have already created, which is a stump. And you know from this particular stump what you are going to get, okay, as an output. Then in the sequential model, we will go and combine another model over here. Now it's the time that I have to create this specific model. Now in order to create this specific model, I need to provide some specific rows only to this model to train, because this model is giving one wrong. Now what I have to do is that whatever is wrong along with other data points, I need to provide this specific model with those records, so that this model will be able to train on this and probably be able to get the output. Now let's create buckets. Now based on buckets, how the buckets will be created over here, I will take 0.07 until, sorry, whatever is the value over here, normal weight value. Okay, so I will start creating my buckets. Buckets basically mean from 0 to 0.07. What did I say? Now for this decision tree or stump, I need to provide some records. So the maximum number of records that should be going should be the wrong records that should go over here. Now how do we decide that, okay, there should be a way that we should be able to say that that specific wrong number of records should go to that decision tree. So for that purpose, what we do is that this decision tree will randomly create some numbers between 0 to 1. Randomly create those numbers between 0 to 1, and whichever bucket it will come in, like 07 to 014, 014 to 07 basically means 0 to 1, then 0 to 1 to, see how the bucket is getting created, this value is getting added to this, so that becomes this bucket. 0 to 1 plus 0.537, how much it is? It is nothing but 470, 0.747, then 0.747 to 0.751. Like this you create all the buckets. Okay, you can create all the buckets. Now tell me which record is basically having the biggest bucket size. Obviously this record. So if I randomly create a number between 0 to 1, what is the highest probability that the values will be going in? So in this particular case, most of the wrong records will be passed along with the other records. Obviously other records, there are chances that other records will go to the next decision tree. But understand, maximum number will go with the wrong records because the bucket is high over here. So the bucket is high over here. So most of the time, this specific record will get selected and then it will be gone to the second tree. Now suppose I have this all records. So this is my first stump. This is my second stump. This is my third stump. Similarly, the third stump. From the second stump, whichever wrong records will be going, maximum number of records will go over here. then again it will be trained. Like this, we'll be having lot of stumps. Minimum 100 decision trees can be added. You know that every decision tree will give one output for a new test data. New test data. This weak learner will give one output. This weak learner will give one output. This weak learner and this weak learner will be giving one output. Obviously, the time complexity will be more. Now, from this particular output, suppose it is a binary classification, I will be getting 0, 1, 1, 1. So again, over here, majority voting will happen and the output will be 1. In case of regression problem, I will be having a continuous value over here. And for this, the average will be computed and that will give me an output over here. So for regression, the average will be done. For classification, what will happen? Majority will be happening. So every way that same part will be going on. Buckets is very much simple, guys. Buckets basically means based on this weights, normalized weight, we are going to create bucket so that whichever records has the highest bucket, based on this randomly creating code, it will select those specific buckets and put it into random forest. Understand why this bucket size is big. The other wrong records which are present, right? Suppose there are more than 4 to 5 wrong records, their bucket size will also be bigger. And because based on this randomly creating number between 0 to 1, most of the wrong records will be selected and given to the second stump. Similarly, this particular decision tree will be doing some mistakes, then that wrong records will get updated, all the weights will get updated and it will be passed to the next decision tree. Guys, when I say wrong record, the output will be same only, no? 0 and 1. So interesting, everyone. I hope you understood so much of maths in Adaboost and how Adaboost actually work. Three main things. One is total error, one is performance of stump, and one is the new sample weight. These things are getting calculated extensively. Max normalized weight was basically used because the sum of all these weights are approximately equal to 1. When boosting, why not take the last output? No. We have to give the importance of every decision tree output. Every decision tree output are important. Okay, let me talk about one model which is called as black box model versus white box. What is the difference between black box model and white box? If I take an example of linear regression, tell me what kind of model it is. Is it a white box model or black box? If I take an example of random forest, is this a white box or black box? If I take an example of decision tree, it is a white box or black box model. If I take an example of ANN, is it a white box or black box model? Linear regression is basically called as a white box model because here you can basically visualize how the theta value is basically changing and how it is coming to a global minima and all those things. In random forest, I will say this as black box model because it is impossible to see all the decision tree, how it is working. So that is the reason the maths is so complex inside us. If I talk about decision tree, this is basically a white box model because in decision tree, we know how the split are basically happening. With the help of paper and pen, you will be able to do it. In the case of ANN, this is a black box model because here you don't know like how many neurons are there, how they are performing and how the weights are getting updated. So this is the basic difference between the black box and white box model. This entire thing is the agenda of today's session. So let's start. The first algorithm that we are probably going to discuss today is something called as K-means clustering. K-means clustering, and this is a kind of unsupervised machine learning. Now always remember, unsupervised machine learning basically means that the one and the most important thing is that in unsupervised machine learning, in unsupervised ML, you don't have any specific output. So you don't have any specific output. So suppose you have feature 1 and feature 2, and suppose you have different data, and based on this data, what we do, we basically try to create clusters. This cluster basically says what are the similar kind of data. So this is what we basically do from clustering, and there are various techniques like k-means, it is hierarchical clustering and all. So first of all, we'll try to understand about k-means and how does it specifically work. It's simple. Suppose you have a data points like this. Okay, let's say that this is your F1 feature, F2 feature, and based on this in 2-dimensional, probably I will be plotting these points. And suppose this is my another points. So our main purpose is basically to cluster together in different groups. Okay, so this will be my one group and probably the other group will be this group, right? So two groups, because obviously you can see from these clusters here you have two similar kind of data which is basically grouped together, right? This is my cluster 1 and this is my cluster 2. Let me talk about this and why specifically it will be very much useful. And then we'll try to understand about math intuition also. Now always understand guys, where does clustering gets used, okay? In most of the ensemble techniques, I told you about custom ensemble technique, right? So custom ensemble techniques. In custom ensemble techniques, whenever we are probably creating a model, first of all, on our data set, what we do is that we create clusters. So suppose this is my data set. During my model creation, the first algorithm we will probably apply will be clustering algorithm. And after that, it is obviously good that we can apply regression or classification problem. Suppose in this clustering, I have 2 or 3 groups. Let's say that I have 2 or 3 groups over here. For each group, we can apply a separate supervised machine learning algorithm if we know the specific output that we really want to take ahead. I'll talk about this and give you some of the examples as I go ahead. Now let's go ahead and focus more on understanding how does k-means clustering algorithm work. So let's go over here. The word k-means has this k value. This k are nothing but this k basically means centroids. K basically means centroids. So suppose if I have a data set which looks like this. Let's say that this is my data set. Now over here, just by seeing the data set, what are the possible groups you think? Definitely you will be saying k is equal to 2. So when you say k is equal to 2, that basically means you will be able to get 2 groups like this, and each and every group will be having a centroid point. Here also there will be a centroid point. So this centroid will determine, basically this is a separate group over here, this is a separate group over here. So over here you can definitely say that fine, this is 2 groups, but how do we come to a conclusion that there is only 2 groups? Okay, we cannot just directly say that okay, we will try to just by seeing the data, because your data will be having a high dimension data, right now I'm just showing you 2-dimension data. But for a high dimension data, definitely you will not be able to see the data points how it is plotted. So how do you come to a conclusion that only 2 groups are there? So for this, there is some steps that we basically perform in k-means. The first step is that we try with different k values. And which is the suitable k value? K is nothing but centroids, okay? It is nothing but centroids. We try with different centroids in this particular case. Let's say that I have this particular data point and I actually start with k is equal to 1 or 2 or 3, anyone you want. Let's say that I'm going to start with k is equal to 2. How to come up with this k is equal to 2 as a perfect value, that I'll talk about it. We need to know there is a concept which is called as within cluster sum of square. So when we try different k values, let's say that for k is equal to 2, what will happen? The first step, we try k values. So let's say that we are considering k is equal to 2. The second step is that we initialize k number of centroids. Now in this particular case, I know my k value is 2. So we will be initializing randomly. Let's say that k is equal to 2. So what we can actually do, let's say that this is my one centroid. I'll put it in another color. So this will be my one centroid. And let's say that this is my another centroid. So I've initialized 2 centroids randomly in this space. Now after this particular centroid, what we have to do is that after initializing this centroid, what we have to do is that we have to basically find out which points are near to this centroid and which points are near to this centroid. Now in order to find out, it is a very easy step. We can basically use Euclidean distance to find out the distance between the points. In an easy way, if I really want to show you that like how many points I want to in an easy way, what I can do, I can basically draw a straight line over here. Let's say that I'm drawing a straight line over here in another color. I can draw a straight line and I can also draw one parallel line like this. So this basically indicates that whichever points you see over here, suppose if I draw a straight line in between all these points, you will be able to see that, or let's say that I'm drawing one more parallel line which is intersecting together. So from this, you can definitely find out, let's say that these are all my points that are nearer to this green point. So what I am actually going to do in this particular case, all these points that you are seeing near the green, it will become green color. So that basically means this is basically nearer to this centroid. And whichever points are nearer to this particular point, that will become red point. So that basically means this belongs to this group. Okay, this belongs to this group. So I hope everybody is clear till here. Then what will happen is that this summation of all the values. Then we initialize the k number of centroids, that is done. Then we try to calculate a distance. We try to find out which all points is nearer to the centroid. Let's say that this is my one centroid, this is my another centroid. And we have seen that, okay, these all points belong to this centroid. It is near to this particular centroid. So this is becoming red. So this is based on the shortest distance. And here it is becoming green. Now the next step, let's see what is the next step after this. So I am going to remove this thing. Now the next step will be that the entire points that is in red color, all the average will be taken. So here again the average will be taken. Now third step, here I am going to write, here we are going to compute the average. The reason we compute the average is that because we need to update the centroid. So compute the average to update centroid, to update centroids. So here you will be able to see that what I am actually doing. As soon as we compute the average, this centroid is going to move to some other location. So what location it will move? It will obviously become somewhere in center. So here now I am going to rub this, and now my new centroid will be this point where I am actually going to draw like this. Let's say this is my new centroid now. Similarly, this thing will happen with respect to the green color. So with respect to the green color also it will happen, and this green will also get updated. So I am going to rub this, and this will be my new green point which will get updated over here. Then again what will happen? Again the distance will be calculated, and again a perpendicular line will be calculated. Here you can see that now all the points are towards there. Okay, again the centroid based on this particular distance, again it will be calculated, and here you can see that all the points are in its own location. So here now no update will actually happen. Let's say that there was one point which was red color over here, then this would have become green color. But since the updation has happened perfectly, we are not going to update it, and we are not going to update the centroid, right? So now you can understand that yes, now we have actually got the perfect centroid, and now this will be considered as one group, and this will be basically considered as the another group. It will not intersect, but by default here intersection is happening. So I hope everybody has understood the steps that you have actually followed in initializing the centroids, in updating the centroids, and in updating the points. Is it clear, everybody, with respect to k-means? Now let's discuss about one point. How do we decide this k value? Okay, how do we decide this k value? So for deciding the k value, there is a concept which is called as elbow method. So here I'm going to basically define my elbow method. Now elbow method says something very much important, because this will actually help us to find out what is the optimized k value, whether the k value should be 2, whether the k value is going to be 3, whether the k value is going to become 4. And always understand, suppose this is my data set, initially let's say that I have my data points like this. We cannot go ahead and directly say that okay, k is equal to 2 is going to work. So obviously we are going to go with iteration. For I is equal to probably 1 to 10, I'm going to move towards iteration from 1 to 10, let's say. So for every iteration we will construct a graph with respect to k value and with respect to something called as WCSS. Now what is this WCSS? WCSS basically means within cluster sum of square. Okay, this is the meaning of WCSS, within cluster sum of square. Now let's say that initially we start with one centroid. So one centroid, let's say it is initialized here. One centroid is basically initialized here. If we go and compute the distance between each and every points to the centroid, and if we try to find out the distance, will the distance value be greater or it will be smaller? Will it be smaller or greater? Tell me, if we try to calculate this distance from this centroid to every point, this is what is within cluster sum of square. It will always be very, very much greater. So let's say that my first point has come somewhere here. It is going to be obviously greater. Let's say that my first point is coming over here. Fine. So within k is equal to 1, initially we took and we found out the distance of WCSS, and it is a very huge value. Okay, because we are going to compute the distance between each and every point to the centroid. Now the next thing that I'm actually going to do is that now we'll go with next value, that is k is equal to 2. Now in k is equal to 2, I will initialize 2 points. Okay, I will initialize 2 points, and then probably I will do the entire process which I have written on the top. Now tell me, whichever points is nearer to this green point, if we compute the distance and whichever points is nearer to the red point, if we compute the distance like this, now this summation of the distance will be lesser than the previous WCSS or not? Obviously, it is going to be lesser than the previous WCSS. So what I'm actually going to do, probably with k is equal to 2, your value may come somewhere here. Then with k is equal to 3, your value may come somewhere here. Then k is equal to 4 will come here to 5, 6, like this it will go. So here, if I probably join this line, you'll be able to see that there will be an abrupt changes in the WCSS value. In the WCSS value, there will be an abrupt changes, and this is basically called as elbow curve. Now, why we say it as elbow curve? Because it is in the shape of elbow. And here at one specific point, there will be an abrupt change and then it will be straight. So that is the reason why we basically say this as elbow. Okay. So this is a very important thing. See, in finding the k value, we use elbow method. But for validating purpose, how do we validate that this model is performing well? We use Silhouette score that I'll show you just in some time. But understand that in k-means clustering, we need to update the centroids, and based on that we calculate the distance, and as the k value keep on increasing, you will be able to see that the distance will become normal, or the WCSS value will become normal. And then we really need to find out which is the feasible k value where the abrupt change, see over here, suppose abrupt change is there and then it is normal, then I will probably take this as my k value. So obviously the model complexity will be high because we are going to check with respect to different k values and WCSS values, and this basically means that the value that we will probably get, first of all we need to construct this elbow curve, then see the changes where it is basically happening. We'll need to find out the abrupt change, and once we get the abrupt change, we basically say that this may be the k value. So k is equal to 4 as an example I'm telling you. So unless and until, if you really want to find the cluster, it is very much simple. We take a k value, we initialize k number of centroids, we compute the average to update the centroids. Then again we try to find out the distance, try to see that whether any points has changed, and continue that process unless and until we get separate groups. Okay, so this is the entire funda of k-means clustering. So finally you'll be able to see that with respect to the k value, will we be able to get that many number of groups. If my k value is 4, that basically means I will be probably getting 4 different groups like this. 1, 2, right? 3 like this, and 4. I will be getting 4 groups like this with k is equal to 4. That basically means k is equal to 4 clusters, and every group will be having its own centroids. Okay, every group will be having, okay, centroids are very much important. Yes, I'll try to show you in the coding also, guys. Let's go towards the second algorithm. The second algorithm that we will be probably discussing is called as hierarchical clustering. Now hierarchical clustering is very much simple, guys. All you have to do is that, let's say this is your data points, this is your data points, and this is my P1, let's say P2. Now hierarchical clustering says that we will go step by step. The first thing is that we will try to find out the most nearest value. Let's say this is my x and y. Let's say these are my points, like this is my P1 point, this is my P2 point, this is my P3 point, this is my P4 point, P5 point, P6 point, P7 point. Okay, so these are my points that I have actually named over here. Let's say that this is maybe the nearest point to each other. So what it will do, it will combine this together into one cluster. This we have computed the distance, so it will create one cluster. Now what will happen on the right hand side, there will be another notation which you may be using in connecting all the points one. So suppose this is my P1, this is my P2, this is my P3, P4. Let's say that I have this many points, and probably I will also try to make P7. So these are my points P7. Now you know that the nearest point that we are having, okay, this will probably be distance 1, 2, 3. This is distance, okay, 4, 5, 6, like this we have a lot of distance. So hierarchical clustering will first of all find out the nearest point and try to compute the distance between them and just try to combine them together into one. What do? We basically combine them into one group. Okay, so P1 and P2 has been combined. Let's say then it will go and find out the other nearest points. So let's say P6 and P7 are near. So they are also going to combine into one group. So once they combine into one group, then we have P6 and P7, which will be obviously greater than the previous distance. and we may get this kind of computation, and another combination or cluster will get formed over here. Then you have seen that, okay, P3 and P5 are nearer to each other, so we are going to combine this. So I am going to basically combine P3 and P5. Okay, and let's say that this distance is greater than the previous one, because we are basically going to start with the shortest distance and then we are going to capture the longest distance. Now this is done. Now you can see that the next point that is near, right, to this particular group is P4. So we are going to combine this together into one group. So once we combine this into one group, this P4 will get connected like this. Let's say it is getting connected like this. P4 has got connected. Then what is the nearest point, whether it is P6, P7 group or P1, P2? Obviously here you can see that P1, P2 is there. So I am probably going to combine this group together. That basically means P1, P2. Let's say I am just going to combine this group together. Again, circle is coming, so I will make a dot. Let's say I'm going to combine this group together because these are my nearest groups. So what will happen? P1 and P2 will get combined to P5. Sorry, P4, P5, this one. So I will be getting another line like this. And then finally you will be seeing that P6, P7 is the nearest group to this. So this will totally get combined and it may look something like this. So this will become a total group like this. So all the groups are combined. So finally you'll be able to see that there will be one more line which will get combined like this. This is basically called as dendrogram. Dendrogram, okay, which is like bottom root to top. Now the question rises is that how do you find that how many groups should be here? How do you find out that how many groups should be here? The funda is very much clear, guys, in this is that you need to find the longest vertical line. You need to find out the longest vertical line that has no horizontal line passed through it. No horizontal line passed through it. This is very much important. That has no horizontal line passed through it. Now what this is basically meaning is that I will try to find out the longest line, longest vertical line in such a way that none of the horizontal line passes through it. What is horizontal line? Suppose if I consider this vertical line, over here, if you see that if I extend this green line, it is passing through this. If I extend this line, it is passing through this, right? If I am extending this line, it is passing through this, right? So out of this, the longest line that may be passing in such a way that no horizontal line probably is this line that I can actually see. So what you do over here is that you basically just create a straight line over this, and then you try to find out that how many clusters it will be there by understanding that how many lines it is passing through. If it is passing through this one line, two line, three line, four line, that basically means your clusters will be 4 clusters. This is how we basically do the calculation in hierarchical clustering. Again, here it may not be the perfect line. I've just drawn with some assumptions, but if you are trying to do this, probably you have to do in this specific way. Okay, I've already uploaded a lot of practical videos with respect to hierarchical clustering and all. Now tell me, maximum effort or maximum time is taken by k-means or hierarchical clustering. This is a question for you. Yes, guys, number of clusters may be 3, but here I'm just showing you that how many lines it may be passed by. How do you basically determine whether maximum time will be taken by k-means or hierarchical clustering? This is an interview question. The maximum time that will be taken is by hierarchical clustering. Why? Because let's say that I have many data points. At that point of time, hierarchical clustering will keep on constructing this kind of dendrograms, and it will be taking many time, lot time, right? So hierarchical clustering will take more time, maximum time that it is going to basically take. So it is very much important that you understand which is basically taking more time. So if your data set is small, you may go ahead with hierarchical clustering. If your data set is large, go with k-means clustering. In short, both will take more time, but k-mean will perform better than hierarchical clustering. See guys, you will be forming this kind of dendrograms, right? And just imagine if you have 10 features and many data points, how you are going to do it? It will be a cumbersome process. You will not be even able to see this dendrogram properly, and manually obviously you cannot do it. So this was with respect to k-means clustering and hierarchical mean clustering. I hope everybody is understood. Now the next topic that we will focus on is that how do we validate. See, how do we validate a classification problem? We use performance metrics like confusion matrix, accuracy, different true positive rate, precision, recall. But how do we validate clustering models? We are going to use something called as, so we are going to basically use something called as Silhouette score. I'll show you what Silhouette score is. I'm going to just open the Wikipedia. So this is how a Silhouette score looks like. A very amazing topic. Okay. How do we validate whether my model basically has perfect 3 or 4 model? Perfect 3, suppose if I find out my k value is 3, how do we find out? Now see, one more issue with k means, which I forgot to tell you. Let's say that I have a data point which looks like this. And suppose I have some data points like this, I have some data points which looks like this. Let's say I have like this. Now in this, one issue will be that suppose I try to make a cluster over here. Obviously, you'll be saying my k value will be 2. Okay. In this particular case, suppose this is one cluster, this is my another cluster, right? Because of my wrong initialization of the points. Okay. Understand? Because suppose if I initialize just randomly some centroids like this, then what may happen is that there is a possibility that we may also have 3 clusters like this kind of clusters. One cluster will be here, one cluster will be here, one cluster will be here. So this initialization of the centroids, one condition is that it should be very far. If we initialize our centroids very far, at that point of time we will be able to find the centroid exactly in the center, because it will keep on updating, it will keep on going ahead, right? But if we don't initialize that very far, then there will be a situation that probably if I wanted to get only, the real thing was to get only 2 centroids, I was probably getting 3 centroids, right? So this is a problem. So for this, there is an algorithm which is called as k-means plus plus. And what this k-means plus plus will do, which I will probably show you in practical, this will make sure that all the centroids that are initialized, it is very far. Okay, all the centroids that is basically there, it is initialized very far. We'll see that in practical application where specifically those centroids are basically used. Now let me go ahead and let me show you with respect to Silhouette clustering. Now, what is this Silhouette clustering? I'm going to explain you in an amazing way. This is important. If someone says you, how do we validate cluster model? Then at that point of time, we basically use this Silhouette. It will be used with respect to k-means. It can be used in hierarchical mean, right? If you want to validate, how do we validate? Okay, that is what we are basically going to see over here. Now, in k-means clustering, what are the most important things? The first and the most important thing is that we will try to find out A of I. Now, what is this A of I? See, this A of I that you basically see. A of I is nothing but, see, 3 major steps happens in order to validate cluster model with the help of Silhouette. First thing is that I will probably take one cluster. Okay, there will be one point which will be my centroid, let's say, and then what I'm going to do, I'm just going to, whatever points are there inside this cluster, I'm going to compute the distance between them. So I'm going to do the summation, and I'm also going to do the average of all this distance. So here you can see that when I say distance of I comma j, I basically means this point, j basically means all these points. I is nothing but it is the centroid. So here is nothing but this is the centroid. Let's say that I am having this centroid. So I am going to compute all the distance over here which is mentioned by this, and this value that you see that I am actually dividing by C of I minus 1. In short, I am actually trying to calculate the average distance. So this is the first point where I am actually computing the A of I. Now similarly, what I will do is that the next point will be that suppose I have computed A of I. The next So next thing that we need to compute is B of I. Now what is B of I? B of I is nothing but there will be multiple clusters in a k-means problem statement. We will try to find out the nearest cluster. Okay, suppose let's say that this is the nearest cluster, and in this I have all the variety of points. Then B of I basically says that I will try to compute the distance between each point and the other point in this centroid. Sorry, in this cluster. So this is my cluster 1, this is my cluster 2. So what I am actually going to do is that here I am going to compute the distance between this point to this point, then this point to this point, then this point to this point, this point to this point, this point to this point, this point to this point. Every point I am actually going to compute the distance. Once this point is done, we will go ahead with the next point and we'll try to compute the distance. And once we get all this particular distance, what we are going to do? We are going to do the average of them. Average. Now tell me, if I try to find out the relationship between A of I and B of I, if my cluster model is good, will A of I will be greater than B of I, or will B of I will be greater than A of I? If I have a good clustering model. If I have a good clustering model, will A of I is greater than B of I, will be greater than B of I, or whether B of I will be greater than A of I? Out of this, if we have a really good model, obviously the distance between B of I will be greater than A of I in a good model. That basically means if I talk about Silhouette clustering, the values will be between -1 to +1. The more the value is towards +1, that basically means the good the model is, the good the clustering model is. The more the value is towards -1, that basically means this condition is getting applied. Now what does this condition basically say? That basically means that this distance is far than the cluster distance. This is what this information is getting portrayed. And this is the importance of Silhouette clustering. Finally, when we apply the formula of Silhouette clustering, you will be able to see that Silhouette clustering is nothing but, let me rub this everything guys for you. Let me just show you what is Silhouette clustering. Silhouette clustering formula will be something like this. B of I, so here you have Silhouette clustering. This is the formula. B of I minus A of I, max of A of I comma B of I, if C of I is greater than 1. Right? So by this, you will be getting the value between -1 to +1. And more the value is towards +1, the more good your model is. More the value is towards -1, more bad your model is. Because if it is towards -1, that basically means your A of I is obviously greater than B of I. So this is the outcome with respect to Silhouette clustering. If S is equal to 0, that basically means still your model needs to be basically the clustering needs to be improved. What is I over here? I is nothing but one data point. You can just read this guys. Data point in I in the cluster C of I. So I hope everybody has understood this. Now let's go ahead and let's discuss about the next topic. We have obviously finished up Silhouette clustering over here. Let's discuss about something called as Dbscan. So for Dbscan clustering, this is an amazing clustering algorithm. We'll try to understand how to actually do DB clustering, and probably you'll be able to understand a lot of things from this. Now in Dbscan clustering, what are the important things? So let's start with respect to Dbscan clustering, and let's understand some of the important points over here. The first point that you really need to remember is something called as score points. I'll also talk about when do you say core points or when do you say other points as such. So the first point that I will probably discuss about is something called as min points. The second point that I will probably discuss about is something called as score points. The third thing that I will probably discuss about is something called as border points. And the fourth point that I will definitely talk about is something called as noise point. Okay guys, now tell me, in k-means clustering, if I have this kind of groups, don't you think with the help of two different clusters, I may combine this two like this? With the help of two different clusters, I may combine something like this, right? But understand over here, what problem is basically happening with the second clustering? This is actually an outliers. Let's say one thing very nicely I will put. Okay, let's say I have one point over here I have one point over here. So if I do clustering, probably I will get one cluster here and I may get another cluster which is somewhere here. Now understand one thing, this point is definitely an outlier. Even though this is an outlier, with the help of k-means, what I'm actually doing, I'm actually grouping this into another group. So can we have a scenario wherein a kind of clustering algorithm is there where we can leave the outlier separately? And this outlier in this particular algorithm, and this is basically we will be using Dbscan to relieve the outlier, and this point will be called as a noisy point. Noisy point, or I can also say it as an outlier. So this will be a noise point. For this kind of algorithm where you want to skip the outliers, we can definitely use Dbscan. That is density based spatial clustering of application with noise. A very amazing algorithm, and definitely I have tried using this a lot. Nowadays I don't use k-means or hierarchical means, instead I use this kind of algorithm. Now see this, what are the important things over here? First of all, you need to go ahead with min points. Min points. So first thing is that you need to have min points. This min points is a kind of hyperparameter. This basically says, what does hyperparameter says? And there is also a value which is called as epsilon, which I forgot. I will write it down over here. This is called as epsilon. Now what does epsilon mean? Epsilon basically means if I have a point like this, and if I take epsilon, this is nothing but the radius of that specific circle. Radius of that specific circle. Okay, so epsilon is nothing but radius over here in this specific thing. What does minimum points is equal to 4 mean? Let's say that I have taken a point over here. Let's say that this is my point, and I have drawn a circle which looks like this, and let's say that this is my epsilon value. Okay, this is my epsilon value. If I say my min point is equal to 4, which is again a hyperparameter, that basically means I can, if I have at least 4 points over here near to this particular circle based on this epsilon value, then what will happen is that this point, this red point, will actually become a core point. A core point, which is basically given over here. If it has at least that many number of min points inside or near to this particular, within this epsilon, okay, within this particular cluster. Suppose this is my cluster, with the help of epsilon I have actually created it. Is there a particular unit of epsilon, or we simply take the unit of distance? No, epsilon value will also get selected through some way. I'll show you in the practical application, don't worry. Now the next thing is that let's say I have another point over here. Let's say that I have another point over here, and this is my circle. With respect to epsilon, I have created it. Let's say that here I have only one point. I have only one point inside this particular cluster. At that point, this point becomes something called as border point. Border point also we have discussed over here, right? So border point is also there. So here I am saying that at least one, if it is only one, it is present, then it will become a border point. If it has 4, definitely this will become a core point, like how we have this red color. So, and there will be one more scenario. Suppose I have this one cluster, let's say this is my epsilon, and suppose if I don't have any points near this, then this will definitely become my noise point. And this noise point will nothing be but this will be a cluster. Okay, so here I have actually discussed about the noise point also. So I hope everybody is able to understand the key terms. Now what is basically happening is that whenever we have a noise point, like in this particular scenario, we have a noise point and we don't find any points inside this, any core point or border point, if we don't find inside this, then it is going to just get neglected. That basically means this is basically treated as an outlier. I hope everybody is able to understand here. This point will be treated as an outlier, or it can also be treated as a noise point. And this will never be taken inside a group. Okay, it will never be taken inside a group. Suppose I have this set of points which you see basically over here, red core and all, and there is also a border point. By making multiple circles over here, you can definitely say that how we are defining core points and the border points, and this can be combined into a single group. Okay, this can be combined into a single group, because how the connection is, now see this yellow line is basically created by this yellow point is basically created by one epsilon, and we have one core point over here. Remember, over here, it should be at least one core point, okay? Not one point, but one core point at least. If it is having one core point, then it will become a border point. This will become a border point. That basically means, yes, this can be the part of this specific group. So what we are doing, whenever there is a noise, we are going to neglect it. Wherever there is a border and core points, we are going to combine it. So I'll show you one more diagram, which is an amazing diagram, which will help you understand more in this. A k-means clustering and hierarchical mean clustering. Now see this, everybody. Now the right hand side of diagram that you see is based on Dbscan clustering. And the left hand side is basically your traditional clustering method. Let's say that this is k-means. Which one do you think is better? Over here you see this, these all outliers are not combined inside a group. But whichever are nearer as a core point and the broader point, separate groups are actually created. Right? So this is how amazing a Dbscan clustering is. A Dbscan clustering is pretty much amazing. That is basically the outcome of this. Here in k-means clustering, you can see this, all these points has also been taken as blue color as one group, because I'll be considering this as one group. But here we are able to determine this in amazing groups. So I'm saying you guys directly use Dbscan without worrying about anything. So now let's focus on the practical part. I'm just going to give you a GitHub link, everybody. Download the code, guys. I've given you the GitHub link. Quickly download and keep your file ready. I'm going to open my Anaconda prompt. Probably open my Jupyter notebook. We'll do one practical problem. I've given you the link, guys. Please open it. So this is what we are going to do today. This will be amazing. Here you will be able to see amazing things. How do you come to know that overfitting or underfitting is happening? You don't know the real value, right? So in clustering, there will not be any underfitting or overfitting. So what all things we will be importing? First is that we'll try k-means clustering. We'll do Silhoutte scoring, and then probably we'll see the output. And we'll do Dbscan also. Let's say Dbscan is also there. So what are the things we have basically imported? One is the k-means clustering. One is the Silhoutte samples and Silhoutte scores. These all are present in the sklearn, and it is present in the metrics. That basically means we use this specific parameter to validate clustering models. Okay. Now we'll try to execute this, and apart from that, matplotlib, we are just trying to import, numpy we are trying to import and all. Here we are executing it perfectly. The next thing is that here the next step is that generating the sample data from make_blobs. First of all, we are just trying to generate some samples with some 2 features, and we are saying that okay, it should have 4 centroids or C centroids itself. With some features, I'm trying to generate some X and Y data randomly. And this particular data set will basically be used in performing clustering algorithms. Okay. Forget about range_n_clusters, because we need to try with different clusters and try to find out the Silhouette score. So right now I've just initialized with 2, 3, 4, 5, 6 values. It is very simple. So if I go and probably see my X data, so my X data will look something like this. So this is my X data with 2 features, and this is my Y data with 1 feature, which is my output, which belongs to a specific class. Okay. So that you can actually do with the help of make_blobs. Let's say how to apply k-means clustering algorithm. So as I said that I will be using WCSS. WCSS basically means within cluster sum of square. So I'm going to import k-means over here for I in range 1,11. That basically means I'm going to use different k values or centroid values and try to see which is having the minimal WCSS value, and I'll try to draw that graph which I had actually shown you with respect to elbow method. So here I will basically be also using k-means. Number of clusters will be I, and initialization technique I will be using k-means plus plus, so that the points, the centroids that are initialized, those points are very far. And then you have random state is equal to 0. Then we do fit, and finally we do WCSS.append k-means.inertia. Okay, this dot inertia will give you the distance between the centroids and all the other points, and this is what I'm going to append in this WCSS value. And finally I'll just plot it. Now here you can see that I'm just plotting it. Obviously by seeing this graph looks like an elbow. Okay, this graph looks like an elbow. So the point that I'm actually going to consider over here, see which is the last abrupt change. So if I talk about the last abrupt change, here I have the specific value with respect to this. Okay, I have one specific value with respect to this. This is my abrupt change. From here, the changes are normal. So I'm going to basically select k is equal to 4. Now what I'm actually going to do with the help of Silhouette, plus score, we are going to compare whether k is equal to 4 is valid or not. So that is what we are going to do, valid or not. So here we are going to do this. Now let's go ahead and let's try to see it, how we are going to do it. So here you can see n cluster is equal to 4, then I'm actually able to find out the prediction, and this is specifically my output. Okay, this is done. Now see this code. Okay, this code is a huge code. I have actually taken this code directly from the sklearn page of Silhouette. If you go and see this code is directly given over there. But I'm just going to talk about like what are the important things we need to see over here. With respect to different clusters, see this clusters 2, 3, 4, 5, 6. I'm going to basically compare whether the k value should be 4 or not with the help of Silhouette scoring. So let's go over here, and here you can see that I'm applying this one. First, I will go with respect to for loop. For n underscore clusters in range underscore clusters, different cluster values are there. First, we'll start with 2. So here you can see initialize the cluster with n cluster value and a random generator seed of 10 for reproducibility. So n underscore clusters, first I took it as 2, and then I did fit predict on x. After I did fit predict on x, I am using this score on x comma cluster label. Now what this is going to do? Understand in Silhouette, what did we discuss? It will try to find out all the clusters over here like this, and it will try to calculate the distance between them, which is the a of I. Then it will try to compute the b of I. Then finally it will try to compute the score. And if the value is between -1 to +1, the more the value is towards +1, the more better it is, right? So these all things we have already discussed, and that is what this specific function will do. And this will give my Silhouette average value over here. Silhouette value will be over here. Okay, this we have done, and then we can continuously do it for another things. You can actually find it over here, and this value that you see, this code that you see, is nothing so complex. Okay, this is just to display the data properly in the form of graphs. Okay, in the form of graphs. So again, I'm telling you, I did not write this code. I've directly taken it from the sklearn page of Silhouette. Okay, so just try to see this particular plotting diagrams and all that you can definitely figure out. But let's see, I will try to execute it and try to find out the output. Now see, for n underscore cluster is equal to 2, the average Silhouette score is 0.70. I told you the value will be between -1 to +1, and I'm actually getting 0.704, which is very good. And then for n underscore cluster is equal to 3, 0.588. Then n underscore cluster is equal to 4, I'm getting 0.65, which is pretty much amazing. And then for n underscore cluster is equal to 5, the average score is 0.563, and n underscore cluster is equal to 6, you are saying 0.45. Here directly you can actually say that, fine, for n underscore cluster is equal to 2, I'm getting an amazing score of 0.704. Obviously you're getting the highest value over this. So should we select n underscore cluster is equal to 2? Okay, we should not directly conclude from it, because here we need to also see that any feature value or any cluster value is also coming as negative value. That also we need to check. So here we will go down over here. You will see the first one. Over here with respect to the first one, you see that I'm getting the value from 0 to 1. It is not going to -0.1. So definitely 2 clusters was able to solve the problem. So I'll keep it like this with me. I definitely have a chance that this may perform well. I may have a chance that this k is equal to 2 may perform well. Okay, so I may have a chance. Let's see to the next one. To the next one over here, you can see that for one of the cluster, the value is negative. If the value is negative, that basically means the AI is obviously greater than B of I. So I'm not going to refer this because it is having some negative values. Even though my cluster looks better, but again, understand what is the problem with respect to this cluster is that if I take this cluster and probably compute the distance between this point to this point, and if I probably compute from this point to this point or this point to this point is obviously nearer to this, right? It is obviously nearer to this. So that is the reason why I'm getting a negative value over here. Okay, negative value over here. This is my output, my score. This point that you see dotted points, this is my score. 0.58, whatever it is, this is basically my score. So obviously this basically indicates that this point is nearer, the other cluster point is nearer to this, so I'm actually getting a negative value, right? So this you really need to understand. Okay, now similarly, if I go with respect to n underscore cluster is equal to 4, this looks good because here I don't have any negative value, and here you can see how coolly it has basically divided the points amazingly with the help of k is equal to 4, right? And similarly, if I go with 5, obviously you can see some negative values are here, some dotted line negative value are there. With respect to 6, you also have some negative values. So definitely I'll not go with 6. I may either go with 4 or I may either go with 2. Now whenever you have these options, always take a bigger number. Instead of 2, take 4 because 4 is greater than 2, because it will be able to create a generalized model. So from this, I am actually going to take n is equal to 4, k is equal to 4. Now, should we compare with this with the elbow method? Here also I got 4, right? So both are actually matching. So this indicates that with the help of this clustering, this silhouette score, we can definitely come to a conclusion and validate our clustering model in an amazing way. So I hope everybody is able to understand, and this way you basically validate a model. And definitely you can try it out, you can understand this code. Definitely but till here you have understood that here I am going to get the average value. Then for I in underscore clusters, whatever cluster this is matching, it is just mapping over there and it is basically giving. So this was the session, and yes, in today's session we efficiently covered many topics. We covered k-means, hierarchical clustering, silhouette score, Dbscan clustering. In tomorrow's session, the topics that are probably pending is, first I'll start with SVM and SVR. Second, I will go ahead with Xgboost, and third, I will cover up PCA. Let's see whether I'll be able to complete this session. One amazing thing that I want to teach you guys, because many people ask me the definition of bias and variance. So guys, many people get confused when we talk about bias and variance, because let's say that I have a model for the training data set. It gives us somewhere around 90% accuracy. Let's say I'm getting a 90% accuracy. For the test data, I may probably getting somewhere around 70% accuracy. Now tell me which scenario is basically this. Most of the people will be saying that, okay, fine, it is overfitting. Now when I say overfitting, I basically mention overfitting by low bias and high variance, right? So many people get confused. Krish, tell me just the exact definition of bias and variance. Low bias, obviously you are saying that because the training is performed, like the model is performing well with the help of training data set. But with respect to the test data set, the model is not performing well. With respect to training data set, why do we always say bias? And with respect to test data set, why do we always say variance? So for this, you need to understand the definition of bias. So let me write down the definition of bias over here. So here I can definitely write that bias, it is a phenomena that skews the result of an algorithm in favor or against an idea. Against an idea. I'll make you understand the definition, but understand what I have actually written over here. It is a phenomena that skews the result of an algorithm in favor or against an idea. Whenever I say this specific idea, I will just talk about the training data set initially. Now, when we train a specific model, suppose if I have this specific model over here, and I'm training with this specific training data set. So this is my training data set. Now, based on the definition, what does it basically say? It is a phenomenon that skews the result of an algorithm in favor or against an idea or this specific training data set. So, even though I'm training this particular model with this training data set, it may be in favor of that or it may be against of that. That basically means it may perform well, it may not perform well. If it is not performing well, that basically means the accuracy is down. If the accuracy is better, at that point of time, what we'll say? See, if the accuracy is better, that time what we'll say, we'll come up with two terms from here. Obviously, you understand, okay? There are two scenarios of bias now here. If it is in favor, that basically means it is performing well with respect to the training data set. I will basically say that it has high bias. If it is not able to perform well with the training data set, then here I will say it as low bias. I hope everybody is able to understand in this specific thing, because many people has this kind of confusion. Now similarly, if I talk about variance, let's say about variance, because you need to understand the definition. A definition is very much important. Okay, if I just talk about the definition of variance, I'm just going to refer like this. The variance refers to the changes in the model when using different portion of the training or test data. Now let's understand this particular definition. Variance refers to the changes in the model when using different proportion of the training data or test data. We obviously know that whenever initially, if I have a model, understand from the definition, everything will make sense. I am basically training initially with the training data. Okay, because we divide our data set. See, our data set, whenever we are working with, we divide this into two parts. One is our train data and test data. Okay, because this is a test data is a part of that particular data set, right? And suppose in this particular training data, it gets trained and performs well. Here I'm actually talking about bias. But when we come with respect to the prediction of this specific model, at that point of time, I can use other training data. That basically means that training data may not be similar, or I can also use test data. Now in this test data, what we do some kind of predictions. These are my predictions. And in this prediction, again, I may get two scenario, which is basically mentioned by variance. It refers to the changes in the model when using different portion of the training or test data. Refers to the changes basically means whether it is able to give a good prediction or wrong predictions. That's it. So in this particular scenario, if it gives a good prediction, I may definitely say it as low variance. That basically means the accuracy with respect to the test data is also very good. If I probably get a bad accuracy, at that time I basically say it as high variance. So if I talk about three scenarios over here, let's say this is my model 1, and this is my model 2, and this is my model 3. Now in this scenario, let's consider that my model 1 has the training accuracy of 90% and test accuracy of 75%. Similarly, I have here as my train accuracy of 60% and my test accuracy of 55%. Now, similarly, if I have my train accuracy of 90% and my test accuracy of 92%. Now tell me what things you will be getting. Here, obviously, you can directly say that fine, your training accuracy is better. Now you're talking about bias. So this basically indicates that this has low bias. And since your test accuracy is bad, because it is when compared to the train accuracy, it is less. So here you are basically going to say high variance. Understand with respect to the definition. Similarly over here, what you will say? High bias, high variance, because obviously it is not performing well. This is another scenario. The last scenario is that this is the scenario that we want because it is low bias and low variance. Okay, many people have basically asked me the definition with respect to bias and variance, and here I've actually discussed, and this gives me a generalized model, and this is what is our aim when we are working as a data scientist. So I hope you have understood the basic difference between bias and variance, and I was able to give you a lot of examples, lot of understanding with respect to this. So I hope you have actually got this particular understanding of this two terms which we specifically talk about: high bias, low bias, high variance, low variance, right? So this was it from my side, guys, and I hope you have understood this. Okay. So let's consider a data set, credit, and let's say this is a approval. So we are going to take this sample data set and understand how does Xgboost work. Suppose salary is less than or equal to 50 and the credit is bad. So the loan approval will be 0. That basically means he or she will not get. If it is less than or equal to 50, if the credit score is good, then probably approval will be 1. If it is less than or equal to 50, if it is good again, then it is going to get 1. If it is greater than 50 and if it is bad, then obviously approval will be 0. If it is greater than 50, if it is good, we are going to get it as 1. If it is greater than 50k and probably if it is normal, then also we are going to get it. So this is my data set. So how does Xgboost classifier work? Understand the full form of Xgboost is extreme gradient boosting. Extreme gradient boosting. So we will basically understand about extreme gradient boosting. Now, extreme gradient boosting will be actually used to solve both classification and the regression problem statement. So first of all, let's understand how it is basically Xgboost. Basically, how it actually, if you just talk about Xgboost, you understand that it is a boosting technique, and internally it tries to use decision tree. So how does this decision tree is basically getting constructed in the case of Xgboost, and how it is basically solved? We are going to discuss about it. So whenever we start Xgboost classifier, understand that first of all we create a specific base model. Suppose if I say this is my base model, and this base model will be a weak learner, okay, and this base model will always give an output of probability of 0.5 in the case of classification problem. So suppose if I say this is probability is 0.5, then I will try to create a field over here. This field is called as residual field. So first base model, what I'm going to do, any data set that you give from here to train, it will always give you the output as 0.5. So this is just a dummy base model. Now tell me, if my probability output is 0.5, if I want to calculate the residual, that basically means I need to subtract approval minus this particular value. So what will be the value over here? 0 minus 0.5 will be minus 0.5. 1 minus 0.5 will be 0.5. 1 minus 0.5 will be 0.5. And 0 minus 0.5 will be minus 0.5. And this 1 minus 0.5 will be 0.5, and this will also be 0.5. Let's consider that I have one more record, and this specific record can be anything because I want to keep some more records over here. So let's consider that I have one more record which is less than or equal to 50k, and if the credit score is normal, you are going to get 0. So here also if I try to find out the residual, it will be minus 0.5. Now the first step, I hope everybody is understood, we have to create a base model. Okay, this base model is very much important because we have to create all the decision tree in a sequential manner. So the first sequential base tree, which is again, this is also a decision tree kind of thing you can consider, but this is a base model which takes any inputs and gives by default the probability as 0.5. Now let's go ahead and understand what are the steps in constructing decision tree after creating the base model. The first step is that create a binary decision tree. So I'm going to write it down, all the steps. Please make sure that you note it down. So create a binary tree, binary decision tree using the features. Second step, we basically define, we say it as, okay, second step what we do, we actually calculate the similarity weight. We calculate the similarity weight. I'll talk about this similarity weight, what exactly it is. If I want to use this a formula, it is summation of residual square divided by summation of probability 1 minus probability plus lambda. I'll talk about this, what is exactly lambda. It is a kind of hyperparameter again, so that it does not overfit. The third thing is that we calculate the information gain. Okay, information gain. So these are the steps we basically use in constructing or in solving, in creating an Xgboost classifier. The first step is that we create a binary decision tree using the feature. Then we go ahead with calculating the similarity weight, and finally we go ahead and calculate the information gain. So how does it go ahead? Let's understand over here and let's try to find out. Okay. Now let's go ahead and let's try to construct the decision tree. As I said that let's consider that I am considering salary feature. So based on using salary feature, what I'm actually going to do, I am going to take this as my node and I'm going to split this up. And remember, whenever we are creating decision tree, in this particular case, it will be a binary decision tree. Let's say that in salary, one is less than or equal to, one is greater than 50. So this two you obviously have in the case of binary. In case of credit, where there are three categories, I'll also show you how that further split will happen and how that will get converted into a binary tree. So here you have less than or equal to 50k and greater than 50k. Now let's go ahead and understand how many values are there in this salary. So if I see before the split, you can definitely see that I'm going to use this residual and probably train this entire model. Now if I really wanted to find out the residual, initially these are my residuals over here. So one residual is minus 0.5, then I have 0.5 over here, then I have 0.5, then again I have minus 0.5, then again I have 0.5, then again I have 0.5, and finally I have minus 0.5. So these are my total residuals that are there. Suppose if I make this split less than or equal to 50, first less than or equal to 50, the residuals, what are things are there? So here I'm going to have minus 0.5, then less than or equal to 50, again I'm going to have 0.5, then again less than or equal to 50, I'm going to have 0.5, and less than or equal to, again one more 0.5 is there. I'm just going to remove this, the last 0.5, which is nothing but minus 0.5. So I hope you understood this split. So half of the things came over here, the remaining half will be greater than or equal to greater than 50. So you have one value here, one value here, one value here. So it will be minus 0.5, then you have 0.5, and then finally you have 0.5. Residuals, how do we get it, guys? See, from the base model, which is by default giving 0.5, first my data goes over here. By default probability, I'm going to get 0.5. So residual is basically calculated from this probability and approval. So this probability minus approval. So if you subtract 0 minus 0.5, sorry, I'm just going to rub this. So if you subtract 0 minus 0.5, you're going to get minus 0.5. 1 minus 0.5, you're going to get 0.5. 1 minus 0.5, you're going to get 0.5. So everybody, I hope, is very much clear with respect to this. So this is the first step. We constructed a binary tree. Now in the second step, it says calculate the similarity weight. Now how to calculate the similarity weight? Similarity weight formula is sum of residual square. Now what is residual square? Let's say that I'm going to calculate I'm going to calculate for this, okay, similarity weight. Now in this particular case, if I go and calculate my similarity weight, it will be summation of residual square. This is my residual values. This is my residual value. So I'm going to do the summation of this square, okay, this value square. You can see over here, sum of residual square. Everybody, you can see sum of residual squares. So what do you think sum of residual squares will be in this particular case? How I have to do it? I will just take up this all values like minus 0.5 plus 0.5 plus 0.5 and minus 0.5 whole square, right? I'm just going to do the squaring of this, divided by, understand what it is divided by? It is divided by probability of 1 minus probability. Now where do we get this probability value? Where do we get this probability value? We get this probability value from our base model, right? So here I'm basically going to say that we are going to do the summation of probability of 1 minus probability. 1 minus probability, that basically means for each and every point, for each and every point, what is the probability? See, probability is basically coming from the base model. So for each point, I'm going to compute two things. One is the probability and then 1 minus probability. And this I'm going to do the summation. Like this, I will do it 4 times. 1 minus 0.5, then 0.5 multiplied by 1 minus 0.5. And finally, you'll be able to see one more will be there, which is plus 0.5, 1 minus 0.5. So this will be your total things with respect to this. So I hope you have understood till here, where you are able to understand that what we have done. This is summation of uh, residual square, and this is the remaining probability multiplied by 1 minus probability. Now tell me, what are you able to find out from this? If you cancel this and this and this value is going to become 0. So this entire value is going to become 0, because 0 divided by anything is 0. So here I hope everybody has understood what is the similarity weight of this specific node. If I want to write, it is nothing but 0. Now you may be considering, where is lambda value? Okay, we will initialize lambda by 1. I'll talk about this hyperparameter. Let's consider it as 1. So here plus 1 or plus 0. Let's consider lambda value 0, let's say, for right now. Okay, I'm just going to make it lambda is equal to 0. I'm just going to talk about it because it is a kind of hyperparameter. भाई 0 नहीं होगा ये, -0.5 plus -0.5 plus 0.5 plus 0.5. If I do the summation here, you will be able to see that I'm going to get 0. So this calculation we have done, and we have got the summation of weight is equal to 0. And let's go ahead and calculate the summation of the weight of the next node. No, it's not first square, it is whole square. So here also if I do, so it is 0.5 plus 0.5. Now let's do it for this. If I want to find out the similarity weight, again see, I'm going to repeat it. 0.5 plus 0.5 whole square. And since there are 3 points, so I'm going to basically use probability 1 minus probability for 1 point, then plus probability 1 minus probability second point, and then probability and 1 minus probability for the third point. And lambda is 0, so I'm not going to write anything. Now let's go and do the calculation for this node. So -5 it becomes 0, then 0.5 whole square, right? So here I'm going to get 0.25. Here if you do the calculation, here you are going to get 0.75. So this value is going to be 1 by 3, and which is nothing but 0.33. So the similarity weight for this node is 0.33. So here you can see probability of multiplied by 1 minus probability. Okay, now the next step that we do is that calculate the information gain. Now you know how to calculate the information gain, but before that, let's do the computation for this also. For this root node also, go ahead and calculate the similarity weight of this. Okay. Debabrata, why the base model probability is 0.5? Because it is, just understand that it is a dummy model. I have just put a if condition there saying that it is going to give 0.5. Now do it for this one, guys, root node. What it will be? See, I can calculate from here only. -1 gone. This is also gone. This is also gone. This will be 0.25 divided by something. Now tell me, guys, what should be for the root node? What is the similarity weight? What is the similarity weight for this? Do this calculation, everyone. Up 1, I know it will be 0.25 divided by, this will be 1.75. Are you getting this? Similarity weight, which will be nothing but 1 by 7. And if I divide 1 by 7, if I say what is 1 by 7, it is 0.142. So it is nothing but 0.14. If I want to calculate the root node, similarity weight over here is 0.14. So I know 0.14, here 0, here 0.33. Now see over here, we calculate the information gain. Next step, the third step, what we do is that we calculate the information gain. Now information gain is nothing but, in this particular case, the root node similarity weight we'll try to add up. So I will be getting 0.33 minus this particular top root node. Whatever split has happened, that similarity weight I'll take 0 plus 0.33 minus 0.14. So minus 0.14. And if I do it, it is nothing but, just open your calculator again, and 0.33 minus 0.14. So it is nothing but 0.19. I'm getting 0.19 as my information gain. The information gain of this specific tree, I got it as 0.19. Obviously, you know how the features will get selected based on the information gain. But let's say that the highest information gain that is given by salary. Okay. Now we will go ahead and do the further split. Let's go ahead and do the further split. So I know my information gain now, it is 0.19. Okay. And information gain is basically used to select that specific node through which the split will happen. Now I'll further go and do the split. Let's say that I'm going to do the further split with the next feature, that is which one? Credit. So I'm going to take credit over here. I'm going to take credit over here. And again, I have to do a binary split again. But you may be considering, Krish, here are only 3 categories. How we are going to basically do this particular split, right? Because we don't know how to do a split because we have 3 categories over here. So in this case, what I will do is that what we can definitely do is that in this particular case, the split that we are probably going to do is that let's consider 2 categories like good and normal at one side, bad at one side. So here it becomes a binary split again. Now let's go ahead and let's try to see that how many data points will fall here and how many data points will fall here. So for writing down the data points, let's say if it is less than or go to the path. If it is less than or equal to 50, it will go this path. And if it is B, then we are probably going to get, how much is the residual? We are going to get 1 residual over here. First of all, so this is my 1 residual, that is minus 0.5. Then similarly, if I see less than or equal to 50, good is there, right? Good or normal is there. So here again 0.5 will come. I hope everybody is able to understand. See the second record. Less than or equal to 50, we go in this path, but it is good, we come over here. Again less than or equal to 50, good. Again we are going to get 1 more 0.5. Then go with respect to greater than or equal to 50, which is coming over here. Will not worry about it right now. Again less than or equal to 50, normal. Again it is minus 0.5. Right? So this many records are definitely coming over here. Only 1 record is basically coming over here. Then again we will start the same process. Again we will start the same process. Now for the same process, what we are going to do, again try to calculate the similarity weight. Now in order to calculate the similarity weight, what I will do, I will basically say this is my similarity weight. This will become 0.25 divided by 0.25. Why? Because this whole square, right? This whole square, residual square, right? Summation of residual square. But here I have only 1 residual. So this square it will become. And then what I'm actually going to do, I'm going to basically write 0.5 minus 1 minus 0.5. This is nothing but only for 1 data point. So this is nothing but 0.5 multiplied by 0.5, which is nothing but 0.25. Right? Now in this particular case, I will get similarity weight as, I hope everybody, I'm getting it as 1. Now what about this similarity weight if you want to compute? It is again very, very simple. This and this will get cancelled. Then again it will be 0.25 divided by, if I say 1 like this, 0.25, then again it will be 0.75. Then this will also be 1 by 3, that is nothing but 0.33. So similarity weight will be 0.33. Then again I have to calculate the information gain of this node. What I will do, I will add this up. See 1 plus 0.33, I'll add like 1 plus 0.33 minus 0. Why 0? Because the information gain, the similarity weight of this, the up one is basically 0, right? For this particular credit node, similarity weight is 0. So 1 plus 0.33 minus 0, this will be 1.33. So like this, further split will again happen over here with different node, and we will only be getting a binary split. But we will be comparing based on information gain, which one is coming good. Now let's say that I have created this path. I have developed my entire binary decision tree, which is a specialty in Xgboost. Now what I'm going to do over here is that, see everybody, what I'm going to do, let's consider the inferencing part. Let's say this record is going to go. How we are going to calculate the output? So this first of all went to this base model. Now let's go ahead and see how the inferencing will happen. Suppose this record is going, right? So first of all, this record will go to this base model. The base model is giving the probability as 0.5. So the first base model is basically giving 0.5. Now based on this 0.5, how do we calculate the real probability? How do we calculate the real probability in this? Okay, so we apply something called as log. So we basically say log of P divided by 1 minus P. So this is the formula we basically apply in only the case of base model. So if we try to see this, it is nothing but log of 0.5 divided by 0.5, which is nothing but 0. Log of 1 is nothing but 0. So in the first case, whenever any record goes, I will be getting the 0 value over here. Okay, 0 value over here. Then plus. Why plus I am doing? Because it will now go to the binary decision tree. Now this record will go to my binary decision tree. Whatever value I am getting from this, I am actually adding that up, and now it will go over here. Now when it goes over here, first of all, let's see which branch it is following. It is following less than or equal to 50 branch, first branch over here. Then this is bad, it will go and follow here. So here I can see that the similarity weight is 1. Now the similarity weight is basically 1 in this case. So what we do in the case of this, we pass it to a learning rate parameter. So this specifically is my learning rate multiplied by 1. 1 because why? Similarity weight is 1 over here. So this will basically be my first references, and alpha over here is my learning rate. It can be a very small value based on the learning parameter that we use, like how we have defined learning parameters elsewhere. On top of this, we apply an activation function which is called as sigmoid. Since this is a classification problem, we apply an activation function which is called as sigmoid, and I hope you know what is the use of sigmoid. Based on this, based on the alpha value, based on this, the output will be between 0 to 1. Now I hope you are getting it, guys. This is how the entire inferencing will probably happen. Now similarly, what I will do, I will try to construct this kind of decision tree parallelly. So we can also write our entire function will look something like this. Alpha 0 plus alpha 1, and this will be your decision tree 1 output. Then alpha 2, your decision tree output. Alpha 3, your decision tree output. Like this, alpha 4, your decision tree output. Fourth decision tree, like this, it will be alpha n, your decision tree n output. And this will be your output finally when you are trying to inference from any new record. Now the reason why we say this as boosting, because see, understand, we are going to add each and every decision tree output slowly to finally get our output. With respect to the working of the decision tree, this is how Xgboost actually work. Don't credit further needs to be simplified? Yes. See, like this, similarly, we can split credit with the help of, like, we can make blue, green one side, normal at one side. But whichever will be giving the information gain more, that will be taken into consideration, right? And this is how your entire Xgboost classifier works. It is very, very difficult to basically calculate all those things. So that is the reason we say that Xgboost is also a black box model. So this is basically a black box model. Is it prone to overfitting? See, at one stage, we also need to perform hyperparameter tuning. In this, we specifically say pre-pruning. We tend to do pre-pruning, and since we are combining multiple decision trees, this decision tree is this one, this independent decision tree which I have created. Now parallelly after this, what I'll do, I'll create one more decision tree. So it will be looking like this. See finally how it will look. So this is my base model, then my data will go to this decision tree, which I have actually done as a binary split on different records. Then again we will make another decision tree which will again be a binary tree. The splits will look like this. Then this is my base model where I'm getting the value as 0. This will be alpha 1 multiplied by decision tree 1, which is this. Then this is alpha 2 multiplied by decision tree 2, which is this. And like this, we will keep on continuously adding more decision trees unless and until this entire thing becomes a very strong learner. So this is how we basically do the combination of all these things. So I hope everybody is able to understand about the Xgboost classifier. Now you may be thinking, how does regressor work? Do you want a regressor problem statement also? The decision tree will get constructed based on independent features. And again, lambda value is a hyperparameter. We basically set up lambda value with the help of cross validation. Now let's go ahead and discuss about Xgboost regressor. The second algorithm that we will probably discuss about is something called as Xgboost regressor. And how does Xgboost regressor actually work? Some fundamentalists follow in random forest. No, in random forest it is completely different. There bagging happens. So over here, let's go ahead with the regressor. So here I'm going to take some example. Let's say that I have this many experience, this many gap, and based on that, we need to determine the salary. My salary is my output feature. Let's say the experience is 2, 2.5, 3, 4, 4.5. Okay. Now in this gap, let's say it is yes, yes, no, no, yes. And let's say that the salary is somewhere around 40K. It is 41K, 52K, and let's see some more data set over here, 60K and 62K. Now the first step in classifier, we created a base model. Here also we'll try to create a base model first of all. This base model, what output it will give? It will give the average of all these values. What is the average of all these values? Okay, what is the average of all these values? 40, 81, 52, 60, 62. If I just do the average, it is nothing but 51K. So by default, I will create a base model which will take any input and just give the output as 51. This is the first step. Now based on this, I will try to calculate my residual. Now how do I calculate my residual? I will just subtract 40 by 51K. So this will basically be minus 11K, and this will be 10K minus 10K minus 10, and this will be 1, this will be 9, and this will be 11. I hope everybody is able to get this. Let's say that I make this as 42K, okay, for just making my calculation a little bit easy. So I have 9 over here. So this is my residual. Then again, the first step is that I construct my decision tree. Now let's say that I'm going to use the experience over here. So this is my experience node, and based on this experience node, I have my features over here. So here I will take up all my residuals, minus 11, 9, 1, 9, 11. And then how do I do the split based on experience? This is a continuous feature. So I have to basically do split with respect to continuous feature, which I have already shown you in decision tree. How do we do? So here is my residual. Here it is 40 minus this is minus 11K minus 9K. This is 1K. This is 9K and 11K. यही बोल रहे थे ना minus 9K. So now I will just take up my first node. Here I'm going to use my experience feature. I know my values, what all things are going to come. 11K in the root node, minus 9, 1, 9 and 11. Now what we are going to do over here is that, so I'm going to do again a binary split over here. Now the binary split will happen based on the continuous feature, that is experience. So two types of records I may get. One is less than or equal to 2 and one is greater than 2. Less than or equal to 2 and one is greater than 2. Now less than or equal to 2, when I do the split, let's see how many values we are getting. Less than or equal to 2, I will get only one value, that is minus 11. And here I'm actually going to get all the other values, minus 9, 1, 9, 11. Now what we are going to do after this is that calculate the similarity weight. Now here the similarity weight will little bit, the formula will change with respect to regression. So similarity weight is nothing but summation of residual squares divided by number of residuals plus lambda. Again here we are going to consider lambda as 0 because this is a hyperparameter tuning. More the value of lambda, that basically means more we are penalizing with respect to the residuals. So this will be the formula that we are going to apply. Okay, so let's see for the first number that we want to apply, so how this will get applied. Again I'm going to write this formula here, it will be better. Let's say here similarity weight is equal to summation of residual square, and here you have number of residuals plus lambda. See, previously we were using probability and then all those things we are using. So if you want to calculate the similarity weight of this, this will become 121 divided by number of residual is 1 plus lambda is 0. So this is going to be 121. So here we are going to calculate the similarity weight, which is nothing but 121. See, if we probably take alpha, let's do one thing. Okay? If we probably take alpha is equal to 1, then what will happen? If we take alpha is equal to 1, just think over here. What may happen? We may directly penalize the similarity weight, right? By just adding 1. Okay, so let's do that also. Suppose I say I'm going to take alpha is equal to 1. So what will happen? This will not be the formula now. Now what will become? 121 divided by number of residual is 1 plus 1. This is nothing but 65.5. So let's say that I now have 65.5 as my similarity weight. Now similarly, I will go ahead and compute the similarity weight for the next one. So here it will become minus 9 plus 9 plus 9 plus 11 whole square divided by 4 plus 1. So this and this will get subtracted. 12 square is nothing but 144. 144 divided by 5. So if I go ahead and calculate 144 divided by 5, it is nothing but 28.5. So here I get 28.5. So the similarity weight for this is 28.5. Similarly, I can go ahead and calculate the similarity weight for this, for the top one. So it will be nothing but what it will be 11 plus, sorry, minus 11 minus 11 minus 9 plus 1 plus 9 plus 11 divided by 1, 2, 3, 4, 5. 5 plus 1 is 6. So this is getting subtracted. This will be 1 by 6. Anyhow, this will be whole square, right? So anyhow, it will be 1 by 6 only. So 1 by 6 will be my similarity weight over here. Okay, 28.8. It's okay. Now finally, the information gain that we need to compute will be very much simple. What will be the information gain? 65.5 plus 28.8 minus 1 by 6. So try to get it, whatever we are trying to get it over here. Just tell me what will be the output. Is it 98.34? So we are probably going to get 98.34. So 98.34 information gain is with respect to this record when we split it. We'll try to compare with the split of each and every one, and whichever will be the better, we'll try to use and split it. So like this, the entire splitting will happen and sequentially the decision tree will be added. It's 60.5. Oh yeah, sorry. 60.5, 60.5 plus 28, 88. Then this will change. Just a second. 89.13. Understand, you don't have to worry about calculation. Automatically that things will be doing it. Okay. So you don't have to worry. Now see, we have now further the decision tree can be splitted into any number of times. Probably the next split, what we can do is that we can do next split something like this. This will be my experience. The two splits that may happen with respect to less than or equal to 2.5, less than or equal to 2.5 or greater than 2.5. Now, if this probably gives the information gain better, then the split will happen like this. Otherwise, whichever gives the better information gain, the split will basically happen like this. I hope, like, let's say that this is the split that is required. Minus 11 is 9 is over here, and then we have 1, 9, 11. Okay, because less than or equal to 2.5, these two records will definitely go over here, and this record will definitely go over here. Now, if I try to calculate the similarity weight for this, it will be nothing but minus 11 minus 9. Minus 11 minus 9 whole square divided by 2 plus 1, right? Now, in this particular case, it will be minus 20 whole square divided by 3, which is nothing but 400. 20 into 20 is 400, which is nothing but 3. So if I go and probably use a calculator and show it to you, 400 divided by 3, which is nothing but 133.33. So the similarity weight for this is 133.33. Similarly, I can go ahead and compute for this. It will be 1 plus 9 plus 11 whole square divided by 3 plus 1, right? So it will be 10 plus 11. 10 plus 11 is nothing but 21 whole square divided by 4. So what it is 21 whole square? If I open my calculator, 21 whole square, 21 multiplied by 21, which is nothing but 441 divided by 4. Divided by 4. So this will probably 110. 110.2.25. And similarly, I can go ahead and compute for this. So if I want to compute for this, what it will be? The same thing that we have got over here, that is 1 by 6. So this will basically be 1 by 6. So finally, if I compute the information gain, it will be what it will be? 133.3 plus 110.25 minus 1 by 6. Obviously, this value will be greater than the previous one what we have got, that is 89.13. So definitely we are going to use this split, which is better than the previous split, right? Let's say that this split has been considered. Finally, how do we see the output? Okay, I hope everybody is able to understand, right? Let's say that this split has worked well. So I'm going to rub all these things. 110.25 is there. Now, suppose I want to do the inferencing. How the inferencing will be done? 110.25. Here, 110.2. Now, suppose any record comes from here. First of all, any record that will go, it will go to the base model. So, the base model, whenever it goes, the value is 51. 51 plus alpha 1. This is my learning rate 1. Suppose if it goes in this route, then what we have minus 11, minus 9. Whenever we go in this route, which has minus 11 and minus 9, the average of both these numbers will be considered. What is average of both these numbers? Minus 11 minus 1, 9 divided by 2. This is nothing but minus 10, right? So minus 10 will get multiplied here. Suppose if it goes in this route, then here what will happen? Here will 1 plus 9 plus 11 divided by 3. Average will be taken. So 21 divided by 3, 7 will be there. So this will get replaced by 7. So similarly, anything that you are doing, this is with respect to decision tree 1. Like this, we will again construct decision tree separately, and again it will become alpha 2 by decision tree 2, alpha 3 by decision tree 3, and like this you will be doing till alpha n decision tree n. And once you calculate this, this will be your specific output in a regression tree. So in this particular case, what will happen? You are just trying to play with parameters and you are trying to use in a different way to compute all this thing. Everybody clear? But again, it is a black box model. You cannot visualize all this thing. Now let's go to the third algorithm, which is called as SVM. See, SVM is almost like decision logistic regression. Okay. So the major aim of SVM is that suppose if I have do data points like this, okay, we obviously use logistic regression to split this data points, right? Like this. We try to create a best fit line which looks like this, and probably based on this best fit line, we try to divide the point. Now in SVM, what we do is that we not only create a best fit line, but instead we also create a point which is called as marginal planes. So like this, we create some marginal plane. So this is your hyperplane and this is your marginal plane. And whichever plane has this maximum distance will be able to divide the points more efficiently. But usually in a normal scenario, whenever we talk about hyperplane or whenever we talk about marginal plane, there will be a lot of overlapping of points, right? Suppose if I have some specific points, I have one point which looks like this. I may also have another points which may overlap. So it is very difficult to get an exact straight marginal planes and split the point based on this. Now this specific marginal plane should be maximum because we can create any type best fit line and probably use this marginal plane. Now if we have this overlapping, right, if for what do we call for this kind of plane? This kind of plane is basically called as hard marginal plane. So this is basically called as hard marginal plane. Okay. And similarly, if any points are overlapping, suppose this yellow points can also get overlapped over here and there may be some kind of errors. So for this particular case, we basically say as soft marginal plane, because here we will be able to see that errors will be there. Now in SVM, what we focus on doing is that we focus on creating this marginal plane with maximum distance. Even though there are some errors, we consider it in solving it by providing some kind of hyperparameter. Now, how do we go ahead and basically create this all marginal planes, and how do we go ahead with this? It's very much simple. Just imagine in this specific way that initially let's consider that I have this data point. Suppose this is my best fit line. How do we give this best fit line as equation? We basically say y is equal to mx plus c, right? We basically say this equation as y is equal to mx plus c. No, hard marginal, it is impossible in a normal data set. Obviously, you will not be able to get it, but definitely we go ahead with creating a soft marginal plane. Now, y is equal to mx plus c. What does this m indicate? M is nothing but slope and c indicates nothing but intercept. Can I say that this both equations are same? Ax plus by plus c is equal to 0. Can I also say that this is the equation of a straight line? Can I say that this is also the equation of straight line? I will say that both of them are equal. Can I say both of them are equal? See, if I try to prove this to you, if I take this equation and try to find out y, it will be nothing but minus c minus ax, and this will be divided by b, this will be divided by b, this will be divided by b. So here you can see that it is almost the same. In this particular case, my m value will be minus a by b and my c will basically be minus c by b. So both the equation are almost same. So let's consider that this is my equation and I am actually, and whenever I say y is equal to mx plus c, can I also write something like this? Y is equal to w1 x1 plus w2 x2 plus like this plus c or plus b. Same thing, no? So here also we can write y w transpose x plus b, same equation, right? We are basically using same equation. Yes, We can also write it in a different way, but at the end of the day, we are also treating something like this. Let's say that this slope is in this direction. If this slope is in this direction, then I can basically say that let's consider that the slope is -1. Let's say that this slope is -1. See, it is in the negative direction. Let's say that this slope is -1. I'm just trying to prove that this slope is negative value. Let's consider this. Now, suppose this is one of my point, -4, 0. And obviously this particular equation is given by, this particular line is given by this equation. Now, if I really want to find out the y value, let's say that this is my x1, this is my x1, and this is my x2. Let's say that I want to find out this W transpose x plus b, the y value based on this line. If I want to compute the y value based on this line, how will I compute? W transpose x basically means what? W value, what all things will be there? One value is b, right? B is intercept. Right now, intercept is passing from origin. Can I say my b will be 0? Obviously, I can assume that b will be 0. Now, in this particular case, if I talk about W in this case is -1, which I have initialized over here. So if I want to do this matrix multiplication, it will be W transpose can be written as like this, and this x value can be written as -4, -4 and 0, -4 and 0, right? So I can basically write like this. Now if I do this multiplication, what will my value I get? I will basically get 4, right? So this is a positive value. This is a positive value. Now understand, since this is a positive value, any points that are below this line, any points that I consider below this line, and if I try to calculate the y, can I say that it will always be positive? Yes or no? Similarly, if I could probably consider one point over here as 4, 0, 4, 4. Now tell me, in this 4, 4, if I calculate the y value, what will you get? Whether you will get a positive value or a negative value. If I try to calculate the y value in this case, because here only positive values will be getting, right? So if I calculate the y value, will the y value be negative or positive? Just try to calculate. How do you calculate? Again, I will use y equation. This time again, my slope is -1, my intercept is 0, and here I will have 4, 4. Now here -4, and then this is +0. This will be -4, right? So this will be a negative value. Negative value, guys. Negative. See, -4 plus 0. Negative. So any points that I will probably have in top of this, any points above this plane, right? And if I try to calculate the y value, it will always be negative. So what two things you are able to get, positive and negative. So you can consider this entirely one category, this another category. At least these two things you can basically consider. Guys, I hope everybody is able to understand this. So this will be my one category, and this will be my another category, obviously. So that basically means I can definitely use a plane and split this point. I hope everybody is able to understand. Now let's go ahead and let's see how this marginal plane will get created. And what is the cost function to basically do this, or what is the cost function in making sure that the marginal plane will definitely work, right? It becomes difficult, right? So suppose let's consider an example. Suppose I say that this is my lines. Let's say I want to basically create a kind of, I have two variety of points. One is this point. Let's say I have all these points like this, and the other points I have somewhere here. Let's consider I am just using directly good number of points so that I can split it, okay? Because I will try to talk about it, what I'm actually trying to prove. So obviously this is my best fit line that splits. And apart from that, what I will do is that I'll also create a marginal points. So in order to create the marginal point, I may use some different color. Let's see which color. This will be my one marginal point. Remember, it will be to the nearest point over here. And basically we will construct like this. And similarly here, we will be constructing like this. I've already told you guys, this equation can be mentioned at W transpose x plus b equal to 0, right? I can definitely say this because ax plus by plus c is equal to 0. So this I can also write it as W transpose x is equal to 0. Sorry, plus b equal to 0. So both are same, okay? This I don't have to prove it. I hope everybody is clear with this. Now what I'm going to do, let's represent this line also with some equation. So this line, if I want to represent, this will be W transpose x plus b what value will come over here, positive or negative? See, from this line, anything above this plane, right? Any distance that we try to find out, it will always be negative. So let's say that I'm using it as -1 to just treat as it is a negative value. And this line that I am going to mention it, it will be W transpose X plus B is equal to +1. -1 above, +1 below. Because we have already discussed from this point, if you are trying to calculate the Y value, it is always going to be +1. This is going to be -1. Here, I should definitely say this as K, okay? But I'm not mentioning K. In many articles, you'll see it as -1. Many research paper also, they use it as -1. But I would like to specify minus and plus K. But here, let's go and write -1 and plus. Now, my aim is to increase this distance. Okay, this distance. I really want to increase this distance. Now, in order to increase this, if I increase this distance, that basically means my model is performing well. So let's say I want to find this distance first of all. So if I write W transpose X plus B is equal to 1, and here I will write W transpose X plus B is equal to -1. So what I'm going to do, I'm going to do the computation and subtract it like this. So here obviously this will be my X1, this will be my X2, okay, because these are my another points, X2 and X1. So I can write W transpose X1 minus X2, B and B will get cancelled, and here I will be writing 2, right? So from here we can definitely write two different things. Let's see what all things we can write. So here this is nothing but the difference between my this plane and this plane, which is given by like this, okay? Now always understand, whenever we consider any vectors, right? Any vectors, right? It also has something called as magnitude. So if I want to remove this magnitude, I can divide this by W. This magnitude of W, then only my vector will remain, which is indicated like this. So I'm going to basically divide by this particular operation. Both the side I'm dividing by this magnitude of W, and I don't care about the directions over here right now. We just care about the vectors. Now when I write like this, what is our aim? Our aim is to, can I say, our aim is to maximize 2 by W. Can I say this, guys? Yes or no? What is our aim? Our aim is to basically maximize this, right? By updating W comma B value, I need to maximize this. Yes? Everybody's clear with this? Can I say that? Yes, I want to maximize this. Yes or no? Everybody. I want to maximize this. If I maximize this, that basically means my marginal plane will become bigger. My marginal plane will be bigger. Okay. Now, can I write along with this that such that y of I, my output, will be dependent on two different things. One is, I can say that my y of I is +1 when W transpose X plus B is greater than or equal to 1. Everybody see in this equation what I am actually trying to specify, such that y of I is +1 when W transpose X plus B is greater than 1, and when it is -1, that basically means W transpose of X is B is less than or equal to -1. Now what does this basically mean? See, all my values, whenever I compute W transpose X plus B is greater than or equal to 1, I'm obviously going to get this +1. When W transpose X plus B is less than or equal to 1, I'm always going to get the output as -1. I hope that is the reason why I have actually written like this. So this too, we have already discussed why we are specifically writing. We want to increase the marginal plane, which is this. This is my marginal plane. And I'm writing one condition that my yi value will be +1 when W transpose X plus B is greater than or equal to 1. Otherwise, when it is less than or equal to -1, it is going to be very much clear. With this transpose condition, we have already done it. Everybody clear with this? Now, on top of it, we can add one more very important point. Instead of writing such that and all, you can also say that our major aim is that if I multiply yi multiplied by W transpose X of I plus B, if I multiplied this two, this will always be able greater than or equal to 1 for correct points, right? For correct points. Because understand, if it is -1, if I'm multiplying with this and if it is a correct point, minus into minus will obviously be greater than or equal to 1 only, right? Similarly for this, it will be greater than 1. So I can also definitely say that my major aim, if I multiply y of I with this, it will be always greater than or equal to +1. which is definitely saying that it will be a positive value. So this is just a representation, guys, but understand what is the minimized cost function. This is my minimized cost function, maximized cost function. Now I'm going to again write it down. Maximize w comma b, maximize w comma b, 2 by magnitude of w. I can also write something like this: minimize w comma b, and I can just inverse this, which looks like this. Are this both are same or not? Because always understand, in machine learning algorithm, why do we write minimize things? Because we are trying to minimize something. Okay, both are equivalent. This both are equivalent. And why we specifically write minimization? Because in the back propagation, when we are continuously updating the weights of w and b, so we can definitely write like this. So here my main target is to minimize this particular value by changing w and b, and I will start adding some more parameters over here. This is fine. Till here, I think everybody has got it. This is our aim and we are going to do this. But I'm going to add 2 more parameters in this optimizer. One is C of I and one is summation of I is equal to 1 to n. And here I will use something called as eta of I. First of all, I'll tell what is C of I. See, if I have this specific data point, let's say if some of my points are over here, then is it a right prediction or wrong prediction? If some of my points are over here, is it a right prediction or wrong prediction? Obviously, it is a wrong prediction if my points are somewhere here. Is it a right prediction or incorrect prediction, right? So this C value basically says that how many errors we can have. How many errors we can have. If it says that fine, we can have 6 errors or 7 errors. How many errors we can have? Even though we are using the marginal plane, how many errors we can have. So here I am specifically writing how many errors we can have. This is what is specified by C of I. Eta of I basically says that what is the summation of, I'm going to write it down. Since we are doing the summation, this entire term basically mentions that summation of the distance of the values, distance of the wrong points. And how do we calculate the distance? From here to here, suppose this is a wrong point, I will try to calculate the distance from here to here. I will do the summation of this, I will do the summation of this, I will do the summation of this. Similarly, for the green point, another summation will happen from here to here, like this, here to here, and we are going to do that specific summation. So we are telling that, fine, if you are not able to fit properly, try to apply these 2 hyperparameters and try to make sure that this many errors are also there. It is well and good, no problem. We will go ahead with that. Try to do the summation of the data points, and based on that, try to construct the best fit line along with the marginal plane like this. Even though there are some errors over here or errors over here, we are good to go with respect. One more thing is there, which is called as alpha SVR. SVR, only one thing is getting changed. In SVR, only this value will get changed. So I want you all to explore and just let me know. This will be one assignment for you. Only this value will be changing, remaining everything are same. So just try to, if you change this particular value, that becomes an SVR. Just try to explore and just try to find out and just try to let me know. So overall, did you like the entire session, everyone? Okay, in this, one more thing is there, which is called as kernel matrix, SVM kernel. We say it as SVM kernel. Now in SVM kernel, what happens? Suppose if I have a specific data points which looks like this, So we obviously cannot use a straight line and try to divide it. So what we do? We convert this 2 dimension into 3 dimensions, and then probably we push our point like this. One point will go like this, and the white point will go down, and then we can basically use a plane to split it. So I have uploaded a video around that, and you can definitely have a look onto that, and I have also shown you practically how to do it. That is the reason I have created that specific video. So great, this was it from my side. I hope you like this session. So thank you everyone, have a great day, keep on rocking, keep on learning, and never give up.